Cada novo dia abre portas para novos descobrimentos e compreensões. Quando você for se deitar para dormir, deixe suas reflexões sobre como a história da humanidade se entrelaça com as gerações futuras e pense nas enigmas ainda à espera de serem revelados nas profundezas de nosso planeta. 8.000 anos atrás, nossos antepassados começaram a domesticar plantas, e esse processo levou à criação das primeiras cidades e civilizações. Our planet, Earth, formed approximately 467 million years ago, and its age can be compared to a vast book, where each page is an epoch. Over this time, Earth has undergone colossal changes, from the formation of continents to the appearance of the first oceans. Inside the planet, processes similar to explosive volcanoes occurred, which ejected lava and gases, forming the first atmosphere suitable for life. Scientists assert that life on Earth has existed for more than 3 billion years, considering geological processes that shaped the planet's surface, created mountain ranges like the Himalayas, and eroded valleys such as the Grand Canyon. During this time, life on the planet consisted of single-celled organisms that inhabited the waters of primitive oceans. These tiny creatures, devoid of consciousness, became the foundation for further evolution, leading to the emergence of numerous forms of life, including simple multicellular organisms, algae, and eventually more complex life forms such as fish and amphibians. Now imagine that humanity, in the form of our ancestors, appeared on this stage as a mere drop in the ocean of time, no more than a few 100,000 years ago. It was during this period, when dinosaurs and mammals already existed on Earth, that our ancestors began to master the skills of hunting and gathering. These early humans, using stone tools, began to explore the world around them, relying on instincts and observations. They lived in caves, such as the famous Chauvet Cave in France, where remarkable cave paintings have been preserved, depicting the life and hunting of our ancestors. Interestingly, these paintings date back to a time when complex ecosystems, such as forests and savannas, where diverse animal species coexisted, already existed on the planet. Humanity, starting as simple gatherers and hunters, gradually developed, mastering agriculture and animal husbandry, which became the basis for the formation of the first civilizations. Looking at this, one can see that over the billions of years of Earth's existence, humanity has only briefly entered this endless history. In this short period, humanity has created magnificent architectural structures, such as the pyramids in Egypt, and developed complex writing systems, such as cuneiform in Mesopotamia. But all this is merely a small part of a vast mosaic consisting of geological epochs, climate changes, and evolutionary processes. This historical context underscores the importance of realizing that we are an integral part of this planetary history, and that our existence is just a fleeting moment in the face of billions of years of evolution. Thus, while Earth continues to rotate around its axis, we remain only temporary inhabitants, exploring and altering the world around us. There are millions of years when other forms of life dominated the planet, and it was only with the appearance of Homo sapiens that a new chapter began, which may not yet be over. It is interesting to note that regardless of how events unfolded, Earth continues to remain unchanged, and we, humanity, are merely temporary passengers on this complex journey. The age of Earth is approximately 4.5 billion years, and this period can be likened to an endless sea of time, where each wave represents a significant stage in the evolution of our planet. At the very beginning, when Earth was just forming, its surface was molten and unstable. During this time, active processes occurred, ultimately leading to the formation of the crust, and the temperature on the surface gradually decreased. Around 700 million years after its formation, water vapor began to condense on Earth, forming the first oceans. These oceans became the cradle of life, which was soon to appear. The formation of the atmosphere, primarily composed of carbon dioxide, ammonia, and hydrogen, was due to volcanic activity and photosynthesis by simple organisms such as cyanobacteria, which appeared around 3.5 billion years ago. This was the period when the planet began to breathe and fill with oxygen, which ultimately changed its appearance and made the development of more complex forms of life possible. Over long millions of years, oceans and the atmosphere transformed, creating conditions for the diversity of ecosystems. As a result of intense geological activity, continents began to shift, forming the modern land masses that did not exist at the time and creating diverse climatic zones. This process, known as plate tectonics, continues to this day, demonstrating the dynamic nature of the planet. Over millions of years, various species evolved, from simple organisms to multicellular ones, including dinosaurs, which dominated Earth around 160 million years ago. However, even they could not escape the catastrophe caused by the impact of an asteroid, which led to their extinction around 65 million years ago. This moment was a turning point, opening the way for mammals, among which appeared Homo sapiens. Humanity, with its intelligence and cultural development, emerged only in the context of this colossal period of time, raising questions about our significance in the history of Earth. We are but a fleeting moment in the vast ocean of time, which continues to flow, and each second that passes adds another stroke to this endless picture of life. Humanity, with its skills and mistakes, is just a small part of a broader picture where billions of years have shaped the conditions for its existence. Ultimately, Earth, like the entire universe, is full of mysteries yet to be revealed, and each new discovery adds layers to our understanding of this incredible planet. In this context, the age of Earth is not just a number, but a symbol of the infinite possibilities that could arise over billions of years. Deep time is a concept that allows us to visualize the scale of time intervals spanning billions of years of Earth's history. For clarity, it is often compared to a 24-hour day, where each hour represents several 100 million years. If Earth had existed for exactly 24 hours, the first appearance of multicellular organisms would have occurred just 3 hours before midnight, and dinosaurs would have begun to dominate the planet about an hour before the start of the new day. Humans, on the other hand, appeared on this time scale only in the last few seconds before midnight, emphasizing their short existence compared to the long process of planet formation. Establishing this scale helps not only to grasp the vast time intervals, but also to see how quickly humanity has become a significant part of the ecosystem, despite its brief history. The geological timescale, which divides Earth's history into eons, eras, periods, and epochs, also illustrates this concept. For example, the Paleozoic era, which began around 540 million years ago, lasted until about 250 million years ago, and includes events such as the emergence of the first fish and plants. Meanwhile, the Mesozoic era, during which dinosaurs dominated, spanned the period from 250 to 65 million years ago. It is important to note that the last epoch, known as the Cenozoic, began only 65 million years ago and continues to the present day. Humanity, with its cultures, wars, and discoveries, is merely a bright flash in this vast temporal perspective. Over the last 300,000 years, which is the period of existence for Homo sapiens, humanity has achieved such heights as the invention of writing, the development of agriculture, and globalization, but this is only a fleeting moment in the context of billions of years of evolution. Looking at the geological timescale, it becomes clear that all our achievements occur against the backdrop of constant changes on the planet, such as plate tectonics, climatic changes, and mass extinctions. Approximately 75% of all species that ever existed on Earth have gone extinct, highlighting the fragility of our position. Comparing Earth's history to a 24-hour day helps us understand how insignificant human existence is in the context of geological time, where each new fossil testifies to the continuity of life and its ability to adapt to changes. From a geological perspective, time is not a linear process, but a complex network of interactions and events that have shaped not only our planet, but also all living organisms on it. For example, the formation of mountain ranges like the Himalayas resulted from the collision of the Indian and Eurasian tectonic plates, which began around 50 million years ago. This process continues to this day, making Earth a living and changing system where every moment has significance. It is important to remember that human existence is just one episode in the long history of Earth, and it can be as quickly forgotten as it was formed. The Fermi paradox is a puzzle that challenges the obvious. If the universe contains countless stars and potentially habitable planets, why do we not observe any signs of intelligent life? This question became relevant in the mid-20th century as astronomers began discovering exoplanets. Currently, astronomers have identified more than 4,000 exoplanets orbiting stars similar to our Sun, and scientists estimate that there could be billions of such planets in our Milky Way galaxy. Given this, it is logical to assume that some of them might support life. Nevertheless, despite active searches for signals from extraterrestrial civilizations, such as the SETI project, no compelling evidence has been found. The question becomes even more intriguing when considering the age of the universe, which is approximately 13.8 billion years. During this time, it is assumed that numerous civilizations could have emerged and disappeared, leaving traces that we might have detected. Instead, we encounter silence. One possible explanation is that highly advanced civilizations might face self-destruction or catastrophic events before they can establish contact with other intelligent beings. This suggests that technological progress may be linked to high risks, and therefore, most civilizations do not survive to the stage where they can actively explore the cosmos or send signals. Another possible reason is that we might not know how to properly search for these signals. Intelligent beings might use technologies that we cannot recognize, or they might communicate on frequencies that we do not track. Furthermore, there are theories that intelligent beings might consciously avoid contact with less advanced civilizations, similar to how we avoid interfering with the lives of wild tribes on Earth. This hypothesis implies the existence of ethical norms that might limit the desire of more advanced civilizations to interact with us. Additionally, in the vastness of the universe, time and distance become critical factors. Even if intelligent beings exist, they might be so far away that communication between us and them is impossible. Imagine two ships sailing across an ocean, but due to fog and the vast distance, they never meet and never see each other. These musings do not make the paradox any less intriguing. We continue to seek an answer to the question, are we truly alone in this boundless universe, or do other civilizations exist, but simply not within our range of perception? As of now, over 130 planetary systems have been discovered in space, but no signs of intelligent life have been found. The Silurian hypothesis, proposed by scientists Gavin Schmidt and Adam Frank, has sparked immense interest among researchers and science enthusiasts. This concept is based on the assumption that a technologically advanced civilization could have existed on Earth long before the emergence of humans. Schmidt and Frank, working in the fields of astronomy and ecology, in their book The World Without Us, published in 2008, raised the question of how life on the planet might have looked if there had been highly developed civilizations during the period when life was just beginning to develop. They explore the Silurian geological period, which lasted from 448 to 420 million years ago, when complex marine ecosystems already existed on Earth, but terrestrial life was just starting to develop. They consider the possibility that highly developed organisms capable of creating technologies, such as ancient precursors to humans, could have existed during this time, but left no traces that could be discovered. Within this hypothesis, researchers analyze what technologies could have existed in those conditions, and how they might have influenced the ecosystem and the planet's climate. For example, if such organisms had developed technologies similar to modern ones, they could have significantly altered the level of carbon dioxide in the atmosphere, or even influenced climate changes that occurred during this period. This opens up new horizons for discussing and understanding the evolution of life on Earth. The hypothesis also challenges traditional views on progress and the development of civilizations. Perhaps civilizations that could have existed in the distant past did not leave any artifacts because their technologies were more organic and did not leave a physical trace. In this context, it is worth noting that even if such a civilization had existed, it could have faced ecological catastrophes or other factors that led to its disappearance. For instance, rapid climate changes similar to those that occurred during the Silurian period could have wiped out all forms of life, including highly developed organisms. This raises another interesting question. If such civilizations existed, what is the probability of their emergence in the future? Research shows that stars and planets similar to Earth are formed in galaxies every day, and the chances of the existence of intelligent life in our universe remain high. In 2018, scientists from the University of California, Berkeley, conducted a study in which they analyzed data on more than 7,000 exoplanets, confirming that conditions necessary for life are encountered much more frequently than previously thought. This means that on other planets at different stages of development, civilizations similar to the hypothetical predecessors on Earth could have existed, never leaving any traces. An example of such an approach is the use of astrophysics and paleoclimatology methods to study climate change and its impact on the development of life. Research shows that changes in the level of carbon dioxide and temperature in the atmosphere that occurred during the Silurian period could have influenced the ecosystem, creating conditions favorable for the emergence of new forms of life. This is important for understanding not only our past, but also our future, as we ourselves may be on the path to creating technologies that could change the climate and ecosystem of the planet. Thus, the Silurian hypothesis opens up new horizons for studying the history of Earth and the evolution of life, emphasizing that we are in a constant process of change and development. In this context, it is important to understand that even if highly developed civilizations had existed previously, they could have disappeared without a trace, leaving behind only questions and mysteries about how life on Earth might have looked if it had developed under different conditions. Geological processes represent a complex of natural phenomena that alter the Earth's surface, exerting a significant influence on all living things and, in particular, on the material traces of human activity. These processes can last for millions of years, and their consequences can sometimes become irreversible. For example, over time, layers of soil and sediments can cover artifacts, absorbing them and altering the landscape beyond recognition. As a result, even the most advanced civilizations that once left vivid traces on the surface can be completely erased from the memory of future generations. Archaeologists and geologists assert that due to the constant movement of the Earth, including tectonic processes, many artifacts can be hidden under the thickness of mountain rocks or be found at significant depths, making their further study difficult. Processes of erosion caused by wind and water can destroy and wash away even the most robust constructions, leaving only fragments that become indistinguishable against the background of the surrounding landscape. Thus, various geological phenomena can both physically destroy material traces and change their original location, leading to the fact that even the most magnificent monuments can be buried under a layer of earth or lost in natural conditions. The time frames of these changes can vary from tens to millions of years, making it impossible to predict which civilization traces will be discovered and which will disappear forever. Geological processes not only shape the relief, but also create new conditions for the growth of flora and fauna, which can also affect the preservation of historical objects. For example, a change in sea level can flood coastal settlements, while volcanic activity can bury entire cities under a layer of lava, as happened with Pompeii in the 1st century AD, which was buried under volcanic ash and preserved for future research, while many other cities and settlements, struck by natural disasters, were lost forever. The scale of such processes has no parallels in human history, and they can occur in a very short time, highlighting the fragility of cultural heritage. Considering all these factors, it is important to understand that even if the material traces of the existence of previous civilizations are found, their interpretation may be difficult due to changes in the geological structure and natural catastrophes that could have affected their preservation. As a result, many mysteries of the ancient world remain unsolved and may be forever lost in the depths of the earth, demonstrating that history, like the planet itself, is subject to changes that are not always predictable. It is worth noting that the existence of certain civilizations can be confirmed only by indirect data, such as the remains of tools or fragments of pottery, which could have been lost due to geological processes. Scientific research shows that even small changes in ecosystems can have significant consequences for cultural heritage, making this topic particularly relevant for archaeologists and historians striving to preserve the memory of human history. Ultimately, geology and history are interconnected, and understanding this interaction opens new horizons for the study of the past. The depth at which artifacts can be located can reach several meters, and sometimes even tens of meters, making their discovery a complex and resource-intensive process. Erosion is a powerful geological process that can completely transform landscapes and even destroy the most robust structures over millions of years. It occurs due to the influence of various factors such as water, wind, and temperature. For instance, under the influence of atmospheric precipitation, which gradually penetrates into the cracks of rocks, their destruction occurs. Water freezes in winter, expanding and causing cracks in rocks. As a result of such cycles of freezing and thawing, limestone formations can be destroyed over tens of thousands of years. In this context, it is worth mentioning the ancient Greek city of Ephesus, which was built of marble. Over time, its magnificent temples and statues have been subjected to erosion, and today, we see only fragments that remind us of its former glory. Moreover, wind also plays a significant role in the erosion process. Sand dunes move under the influence of strong winds, which can carry small particles and gradually remove the upper layers of soil or even rocks. In the Sahara Desert, for example, wind creates enormous sand dunes that can reach heights of up to 100 meters and move at speeds of up to 30 kilometers per hour. This process takes hundreds of years, and in the end, it can lead to the complete destruction of even the most robust constructions. Temperature fluctuations also affect erosion. In areas with significant temperature changes, such as mountainous regions, rock formations undergo thermal expansion and contraction, leading to their destruction. For example, in the Himalayas, where temperatures can range from -50 to +30 degrees Celsius, rock formations are destroyed faster than in more stable climatic conditions. Chemical erosion, on the other hand, occurs due to the influence of acid on rock formations. For instance, karst formations such as caves and underground rivers are formed as a result of the dissolution of limestone by carbonic acid contained in rainwater. This process can take thousands of years, but eventually leads to the formation of extensive underground systems. In the United States, in the state of Kentucky, there is the famous Mammoth Cave, which is the longest cave system in the world and was formed precisely due to chemical erosion. Metals contained in construction materials are also subject to erosion. For example, rust, which forms on iron, is a result of the interaction of metal with oxygen and moisture. This process can lead to the destruction of metallic structures over several decades. In cities like New York, old bridges and buildings made of steel often require constant maintenance and repair to prevent corrosion. Thus, erosion is not just a slow process of destruction. It is a complex mechanism that changes the appearance of our planet. It can turn rocks into sand and metals into oxides, and it leaves behind traces that testify to the past. For example, the Great Wall of China, built in the 5th century BC, is today being destroyed not only by human activity, but also by natural elements that reduce its size each year. The reduction in wall height in some places reaches several centimeters per year. Tectonic movements of the Earth's crust represent powerful forces that shape the landscape of our planet and influence the fate of civilizations. The Earth's crust consists of continental and oceanic plates that are constantly moving, albeit very slowly, only a few centimeters per year. These movements occur due to convection in the mantle, where magma rises to the surface, cools, and then sinks back down. When two continental plates collide, they do not simply form mountains, but also subduct one another, carrying away any traces of civilizations. For example, when the Indian plate collided with the Eurasian plate around 50 million years ago, it led to the formation of the Himalayas, the highest mountains on Earth, and their uplift continues to this day. As a result of this collision, ancient marine deposits and even traces of life that existed on these territories were buried under multi-layered mountains. While continental plates can collide, oceanic plates have their own dynamics. When one oceanic plate subducts beneath another, it creates what is known as a subduction zone. A classic example is the Japan Sea, where the Pacific plate is subducting beneath the Eurasian plate. This process not only causes powerful earthquakes, but also tsunamis, which can destroy entire cities, as happened in Fukushima in 2011. The forces generated in this process can destroy any structures built by humans, leaving only geological traces. There is also a process in which plates diverge, creating new oceanic crust, as occurs on the Mid-Atlantic Ridge. This ridge, which stretches over more than 8,000 kilometers, is a testament to how new sections of the Earth's crust are formed while old ones sink into the planet. In this process, traces of civilizations that once existed on these lands are also lost. It is known that tectonic movements can cause significant changes in climate and ecosystems. For example, when millions of years ago continents were united in the supercontinent Pangaea, the climate was entirely different, leading to a diversity of flora and fauna. Over time, as Pangaea began to break apart, the climate changed, and many species went extinct, leaving behind only fossil remains that we find today. Understanding tectonic processes is vital for assessing risks associated with earthquakes and volcanic eruptions. Scientific research conducted by organizations such as the U.S. Geological Survey allows for the prediction of possible earthquakes based on the analysis of historical data and plate movements. For example, in 2008, a magnitude 8.8 earthquake struck Chile, causing the deaths of more than 30 people and causing widespread destruction. These events highlight how tectonic movements can impact humanity, carrying away not only buildings, but entire cultures. Tectonic processes continue to be active, and their influence on our planet never ceases. Powerful volcanic eruptions, such as the eruption of Vesuvius in 79 AD, which engulfed Pompeii, serve as a reminder that nature can be both beautiful and destructive. Modern technologies, such as satellite observation systems, help scientists better understand these processes and their consequences. For instance, using GPS, it is possible to track plate movements with an accuracy of a few millimeters, allowing for the prediction of future changes in the landscape. Each year, numerous earthquakes occur, and around 1 million of them are recorded on Earth, but only some of them can cause significant destruction. This geological activity not only shapes the landscape, but also influences biological diversity. For example, on Hawaii, where an oceanic plate moves over a hotspot, volcanic islands are formed that become home to unique ecosystems. These islands are also the result of tectonic processes that continue to create new lands while carrying old ones into the mantle. Tectonic movements are not just geological changes, but also a history that continues over millions of years. Osatkonakaplenie, это процесс which represents an important stage in the formation of mountain rocks, and, consequently, in the history of our planet. It begins when particles such as sand, clay, and limestone are transported by water, wind, or ice, and settle at the bottom of bodies of water or on land. This process occurs over millions of years and is the cause of the accumulation of layers of sedimentary rocks. For example, in the Mississippi River, approximately 1 million tons of sediment are deposited annually, gradually settling on the bottom and forming multi-layered deposits. Over time, as new layers of sediment cover older ones, pressure increases, and the lower layers begin to compress. The compression process includes not only the physical compression of particles, but also chemical reactions that lead to the formation of cementing substances that bind the particles into a single rock. In practice, this can be observed, for example, in the famous deposits of the Florida Formation, where limestone is formed from the shells of marine organisms buried under layers of other sediments. These deposits can reach thicknesses of several thousand meters. Over millions of years, depending on the conditions of the surrounding environment, sedimentary rocks can undergo metamorphism, transforming into more dense and stable rocks, such as gneiss or marble. For example, limestone subjected to high pressure and temperature transforms into marble, which can then be used in construction and sculpture. Layers accumulated as a result of sediment accumulation can contain not only minerals and organic substances, but also evidence of life on Earth. Fossils of ancient organisms, traces of their activity, and even traces of human civilizations. In particular, in sedimentary deposits found in the region of Babylon, archaeologists have discovered artifacts and tools used by ancient Mesopotamians, which were buried under layers of clay and sand over more than 4,000 years. Each layer of sediment represents a temporal capsule that preserves information about the climate, flora, and fauna of that time, allowing scientists to reconstruct the history of our planet. This process of sediment accumulation and compression clearly demonstrates how nature creates and destroys, leaving behind not only geological monuments, but also evidence of the existence of civilizations. Findings made in various corners of the planet confirm that sedimentary rocks formed as a result of sediment accumulation can serve not only as building materials, but also as important sources of historical information, opening doors to the past. Layers can have various compositions and colors, indicating changes in ecosystems and climatic conditions that existed during different periods. For example, red sandstones indicate a dry climate, while black mudstones may indicate the presence of rich organic substances in wet conditions. Such a diverse composition of sediments accumulated over millions of years makes them true archives of Earth's history. Temporary windows for the development of civilizations represent specific historical moments when conditions conducive to rapid growth of cultures, technologies, and societies have emerged. During these windows, events overlap, creating a favorable backdrop for new ideas and innovations. For instance, in the first millennium BCE in the Eastern Mediterranean, there were numerous significant changes. The development of trade between Greece and Mesopotamia led to the exchange not only of goods, but also of knowledge, which accelerated cultural exchange. At this time, in ancient Egypt, under the reign of Pharaoh Thutmose III, architecture reached new heights. Grand temples and pyramids were built, symbolizing the power and wealth of the state. Meanwhile, in India, philosophy began to emerge, which later influenced entire generations, including Buddhism, which arose in the 6th century BCE through the teachings of Siddhartha Gautama. In this context, temporary windows become not just frames, but true catalysts that open doors to innovative thinking and social changes. One such example is the Renaissance, which began in Italy in the 14th century and initiated a new perspective on art and science, reviving interest in ancient knowledge and cultures. During this time, artists such as Leonardo da Vinci and Michelangelo created works that not only captivate, but also demonstrate the depth of human experience. This was a period when science and art became interconnected, and scientists like Galileo Galilei began to develop the foundations of modern scientific method. Temporary windows allow us to see how one civilization can influence another, creating a chain of events that changes the course of history. For example, the Great Silk Road, which became actively used in the 1st century CE, opened new trade routes and facilitated cultural exchange between the East and West, leading to the spread of technologies such as paper and gunpowder from China to Europe. Temporary windows do not always coincide. While one part of the world is flourishing, another may be declining. For example, during this time in Europe, wars and epidemics were raging, reducing the population and slowing development. This underscores that temporary windows can be both positive and negative, each with its unique characteristics and consequences. Contemporary research shows that such windows can be determined not only by cultural and historical events, but also by ecological changes that affect resources and living conditions. For instance, global warming or changes in sea level can become catalysts for migrations and conflicts, as was the case with the collapse of the Maya civilization, where climate changes led to water and food shortages. Temporary windows are the result of the interaction of various factors that develop over time and space, creating unique conditions for the growth or decline of civilizations. The 18th century is another striking example, when the Enlightenment gave birth to new ideas about rights and freedoms, leading to revolutions in various countries, from America to France. These changes were made possible by the accumulation of knowledge, the discovery of new lands and resources, which in turn led to the creation of new economic systems and political structures. Research shows that temporary windows can last from several decades to several centuries, and their impact on society can be felt for many generations. Looking at history, one can identify numerous such windows, each of which had a significant impact on the course of civilizations, from the fall of the Roman Empire to the Industrial Revolution, which changed the world in the 19th century when mechanization and new technologies raised human productivity to a new level, changing the structure of society and way of life. The Silurian period, which lasted from 443 to 419 million years ago, was a unique epoch in Earth's history, during which conditions on the planet could have facilitated the development of complex life. During this time, the climate was warmer than it is now, with global temperatures likely being several degrees higher than they are today. The level of oxygen in the atmosphere significantly increased, reaching approximately 21%, which contributed to greater biodiversity, especially among marine organisms. The oceans were teeming with diverse forms of life, including trilobites, brachiopods, and other marine invertebrates, which actively evolved and filled ecosystems. On land, mosses and the first vascular plants began to colonize new ecological niches, creating conditions for increased biodiversity in ecosystems. The land area increased, forming large continents, which facilitated the migration of organisms and their adaptation to various conditions. During this time, there was a significant increase in biomass, indicating high ecosystem productivity. The appearance of the first land plants created new sources of food and shelter for animals, which could have led to the development of more complex life forms. The development of ecosystems on land and in the oceans led to the formation of new ecological relationships and interactions between species. Additionally, the geological activity of the time resulted in the formation of new mountain ranges and reefs, which also contributed to the diversity of biomes. Mineral and nutrient reserves were abundant, providing sufficient resources for the growth and development of organisms. During this period, there were no large land predators, which could have allowed for the evolution of larger and more complex life forms. The Silurian period laid the foundation for the development of fauna and flora, which later became the basis for further evolution. The level of carbon in the atmosphere was significantly higher than it is now, creating conditions for plant growth and, ultimately, contributing to the production of oxygen through photosynthesis. These factors created an ideal environment for the emergence of more complex life forms, which could have led to the development of intelligent beings in the future. The Silurian period was a crucial stage in Earth's history, when conditions could have been optimal for the emergence of life as we know it. During this time, complex ecosystems already existed, which may have served as the foundation for the development of more highly organized life forms that evolved later. As a result, the Silurian period was a time when life on the planet reached new heights, setting the stage for future evolutionary changes. The Carboniferous period, which lasted from 359 to 299 million years ago, was a true epoch of greenery and oxygen on Earth. The atmosphere at that time was rich in oxygen, reaching up to 30%, which not only facilitated the survival, but also the rapid development of various forms of life. On Earth, giant forests consisting mainly of tree ferns, conifers, and other plant forms grew, reaching heights of up to 40 meters. These forests created unique ecosystems. During the Carboniferous period, the first higher plants appeared, such as Lepidodendron and Sigillaria, which not only enriched the atmosphere with oxygen, but also became the basis for the formation of coal deposits that we use today. Insect populations also experienced a rapid growth, and this period saw the appearance of the first large insects, such as Meganeura, a dragonfly with a wingspan of around 70 centimeters. The first amphibians, such as labyrinthodonts, began to venture onto land, using the richly forested and watery ecosystems for food and reproduction. Predatory reptiles, such as diapsids, began to occupy their ecological niches, making the ecosystem even more diverse. Additionally, the formation of coal deposits began during this period, which continue to serve as a significant source of energy for humanity. Regions such as the Appalachians in North America and the Urals in Russia became true coal basins. The formation of coal occurred under the influence of pressure and temperature on the remains of vegetation that accumulated in swamps. As a result, the Carboniferous period became a crucial stage in the evolution of life on Earth, creating the necessary conditions for further changes in ecosystems and the appearance of new groups of organisms. By the end of this period, the diversity of life reached its peak, which determined the further development of the biosphere. Scientific research, such as the work of geologist Don Blake and paleobotanist Stephen Curtis, has shown that it was during this period that life on land reached unprecedented scales. The coal formed during this time became the primary source of coal that we use today. The Permian period, which lasted from 299 to 252 million years ago, was an era of flourishing terrestrial ecosystems, during which significant changes occurred in the biosphere. During this time, the climate was predominantly warm and humid, fostering the development of diverse ecosystems. On land, reptiles, including the ancestors of modern dinosaurs, as well as various amphibians and mammals, began to dominate. For instance, members of the mammalian class, such as synapsids, started to develop their adaptations, which drove further evolutionary progress. The Permian period is renowned for its ecosystems, which included both forests and vast bodies of water inhabited by diverse fish and aquatic organisms. Paleontological research, such as that conducted by Dr. Robert S. Bakker, has shown that during this time there were enormous forests of conifers and ferns that covered extensive areas, creating unique conditions for the formation of complex food chains. These forests were home to numerous insect species, including the first butterflies and beetles, which began to play their ecological roles. Another significant aspect of the Permian period was the appearance of the first seed-bearing plants, which colonized the land, providing new sources of food and shelter for many animals. Fossil finds, such as seeds and leaves, have been discovered in places like the Perm region of Russia and southern Africa, indicating the wide distribution of these plants. During this time, there was also a significant increase in biomass. According to scientists, it reached unprecedented levels, creating conditions for the potential emergence of complex ecosystems similar to modern ones. It is worth noting that during this period, Earth had conditions that theoretically could have facilitated the development of highly organized civilizations. There was enough warmth, a diverse flora and fauna, and abundant resources such as coal and oil, which could have formed the basis for the development of complex societies. However, despite all these achievements, the Permian period was coming to an end, and around 252 million years ago, one of the most massive mass extinctions occurred, known as the Permian-Triassic extinction event, in which approximately 95% of all species on the planet perished. Scientific research shows that this extinction was caused by multiple factors, including global warming, oxygen crises, and volcanic activity, which forever changed the appearance and evolutionary trajectory of life on Earth. Mass extinctions are catastrophic events that have fundamentally altered the biosphere of Earth, leading to the disappearance of a vast number of species over short periods of time. There are 5 main global mass extinctions, each of which has left a profound mark on the history of life on the planet. These events typically occur in the context of rapid climate changes, sea level fluctuations, volcanic activity, and even asteroid impacts. The first known mass extinction occurred around 500 million years ago, at the end of the Ordovician period, when approximately 85% of all marine species went extinct. The cause of this extinction is believed to be a sudden cooling of the climate and a drop in sea level, which led to the demise of many marine organisms, particularly brachiopods and trilobites. The second mass extinction occurred around 260 million years ago at the end of the Devonian period, when about 75% of species perished. This extinction was also linked to climate changes and the deterioration of living conditions on land and in the ocean. The third mass extinction, known as the Permian-Triassic, occurred around 250 million years ago and was the most severe, wiping out about 95% of all species. It was caused by intense volcanic activity in the region of present-day Ural, which led to the release of carbon dioxide and global warming. The fourth mass extinction occurred around 70 million years ago at the end of the Cretaceous period and eliminated not only dinosaurs, but also many other species. It was linked to the impact of an asteroid in the region of present-day Yucatan Peninsula, which resulted in global climate changes and the disappearance of most terrestrial and marine species. The fifth mass extinction, currently underway, is known as the Anthropocene extinction because it is caused by human activity. Deforestation, environmental pollution, climate change, and hunting are leading to a rapid decline in the number of species. These events demonstrate how fragile the ecosystem of the planet is and how quickly it can change under the influence of both natural and anthropogenic factors. As a result, mass extinctions serve as a significant reminder that Earth, as a living organism, is constantly changing, and we are merely a part of this complex and interconnected world. Scientific research continues, but some estimates indicate that currently around 1 million species are at risk of extinction, which is a cause for serious concern among ecologists and biologists. The Permian-Triassic extinction event occurred around 252 million years ago and was the most catastrophic mass extinction in Earth's history. According to paleontologists, during this event, approximately 96% of all marine species and about 70% of terrestrial animal and plant species went extinct. The primary causes of this catastrophic event are believed to have been rapid climate changes that led to global warming, as well as intense volcanic activity that caused ocean acidification and changes in the chemical composition of the atmosphere. Research indicates that during this period, enormous volumes of lava were ejected in the regions of present-day Ural and Siberia, leading to the formation of basaltic plateaus known as the Siberian Traps. These traps released massive amounts of carbon dioxide and sulfur dioxide into the atmosphere, contributing to rapid climate change and acid rain. Evidence of this extinction is confirmed by geological layers, where paleontologists found a sharp decrease in biodiversity and an increase in the proportion of extinct organisms, such as trilobites and many coral species. This catastrophe led to a complete reset of life's evolution on Earth, opening new ecological niches for the surviving groups of organisms. For instance, it was after the Permian extinction that dinosaurs began to flourish, dominating the planet during the Triassic and Jurassic periods. It is important to note that this extinction was not instantaneous, but rather occurred over several million years, allowing some species to adapt to the changing environmental conditions. Scientific research, including the work of paleobotanists and paleozoologists, continues to refine the details of this event and its impact on subsequent stages of biological evolution. For example, the emergence of the first mammals occurred precisely due to the changes that took place in ecosystems after this mass extinction. As a result, only small groups of species that survived this catastrophe remained, and they became the foundation for the new biodiversity of life. In the modern world, studying the Permian extinction helps scientists understand which factors could lead to similar events in the future, given that human activity is already affecting Earth's ecosystems. Paleontologists emphasize that studying this extinction helps us realize how vulnerable life on Earth is and how easily it can be subjected to destructive changes. In the geological record corresponding to this period, one can clearly see layers that separate the extinct species from those that appeared later, providing a vivid illustration of the profound changes in biodiversity. The magnitude of the extinction was so catastrophic that the newly forming ecosystems differed significantly from the previous ones, leading to the emergence of new forms of life that we can observe today. The Cretaceous-Paleogene extinction event occurred approximately 66 million years ago and is considered one of the most massive mass extinctions in Earth's history, wiping out about 75% of all species on the planet. Known as the Cretaceous-Tertiary extinction event, this event destroyed not only dinosaurs, but also a multitude of other flora and fauna, including marine animals like ammonites and marine reptiles. The primary cause of this catastrophic event, according to most scientists, was the impact of an asteroid with a diameter of approximately 10 kilometers on the territory of the present-day Gulf of Mexico, resulting in the formation of the Chicxulub crater. This crater, with a diameter of about 180 kilometers, was discovered in the late 1980s, and its age coincides with the time of the extinction. The impact of the asteroid caused powerful earthquakes, tsunamis, and the release of a vast amount of dust and gas into the atmosphere, which in turn led to a sharp decrease in global temperature. Studies indicate that the temperature could have dropped by 10 degrees Celsius or more, creating conditions in which most plant and animal species could not survive. As a result of this cataclysm, significant changes occurred in ecosystems that previously supported dinosaurs, leading to the disappearance not only of large reptiles, but also of other forms of life. It is interesting that the extinction occurred so quickly that many species did not have time to adapt to the new conditions. For example, a study conducted in 2006 showed that some marine organisms could not survive changes in water composition. On land, not only dinosaurs but also many mammals and plants disappeared, completely transforming ecosystems. From an anthropological perspective, if civilizations similar to those we know today had existed during that period, they too could have been destroyed. For instance, if highly developed societies similar to those of today had existed on Earth, they would have faced the same challenges as other species. It is important to note that not only large species but also many small organisms, which played a critical role in ecosystems, became extinct. Studies show that this extinction paved the way for new forms of life, including mammals that later became dominant on the planet. In conclusion, the Cretaceous-Paleogene extinction event was a turning point in Earth's history, changing not only the appearance of life, but also the ecosystems as a whole. The Chicxulub crater, which has become a symbol of this event, is still being studied by scientists to understand the consequences of this catastrophic impact. Geological markers are specific traces left by technological civilizations in the geological layers of Earth, which can help scientists determine the time and nature of their existence. These markers manifest in various forms, including changes in mineral composition, remnants of construction materials, and traces of resource processing. For instance, in layers of sedimentary rocks, one can find structures reflecting human activity in the form of altered soils or specific deposits created as a result of industrial activity. Studies show that such markers can serve as evidence not only of the presence of a civilization, but also of its level of technological development. Over time, these traces can be buried under younger layers, making them difficult to detect. But with the help of modern technologies such as ground-penetrating radar and radiocarbon dating methods, scientists can more accurately determine the age of these markers and their connection to specific historical periods. The importance of geological markers lies in the fact that they do not merely record human presence, but also reflect the impact of human activity on the environment. Specifically, such changes can indicate agricultural practices, the use of fossil fuels, and even climate change resulting from anthropogenic activity. This opens new horizons for understanding how technological civilizations interacted with nature and how their legacy is preserved in geological time. Scientific research in this area, conducted by scholars such as Dr. Emily Davis from the University of California, shows that the analysis of geological markers can help not only in studying ancient civilizations, but also in understanding the consequences of our present for future generations. One significant aspect is that these markers can persist for millions of years, thus providing insights into how we will appear in geological time. Geological markers can be associated with processes such as infrastructure creation, carbon emissions, and even changes in the biosphere, making them valuable tools for researchers seeking to understand not only history, but also the ecological consequences of human activity. These studies can lead to important conclusions about how technological civilizations adapted to environmental changes and influenced climate change. There is evidence that some civilizations left more pronounced geological traces due to intensive agriculture, deforestation, and mineral extraction, which also confirms the link between technological progress and ecological changes. Understanding and analyzing these markers provide unique opportunities for studying not only past civilizations, but also for recognizing current ecological problems that humanity faces today. Geological markers are important evidence of how humanity leaves its mark on the planet and can help in the search for answers to questions about the future of our civilization and its interaction with nature. Ultimately, geological markers represent more than just artifacts. They are keys to understanding the relationship between technology and ecology. In the geological layers of the Earth, unusual concentrations of rare metals have been discovered, which has sparked interest among scientists studying potential traces of ancient resource mining by intelligent beings. For instance, in the vicinity of the ancient city of Ur in Mesopotamia, archaeologists found high concentrations of gold and silver, leading them to hypothesize that these metals could have been mined and processed by humans between the 3rd and 2nd millennia BCE. Analysis of soil samples showed that the content of these metals in certain layers exceeded natural backgrounds by tens of times. This discovery is linked to the work of a group of geologists, led by Professor John Taylor of London University, who studied geochemical anomalies in this region in 2017. They concluded that such concentrations could indicate ancient mines used for the extraction of these metals. In other regions, such as Peru, researchers found anomalous levels of copper and tin in layers dating back to the Inca period, which also suggests their mining and processing. A group of archaeologists led by Dr. Ana Castro conducted excavations in the region of Chavín de Huántar in 2018, where traces of metallurgical furnaces used for smelting copper were found. Notably, in some places like California, scientists discovered concentrated layers of rare earth metals such as lanthanum and neodymium in layers dating back to prehistoric times, indicating that ancient cultures might have possessed knowledge of mining and utilizing these resources. In the 12th century BCE, in the vicinity of modern Iran, archaeologists found remnants of metallurgical complexes where, according to radiocarbon dating, active work with copper and tin was conducted, confirming the existence of advanced metalworking technologies. These findings suggest that humanity may have had more advanced mining and processing skills than previously thought. A detailed analysis of the geochemistry of these layers suggests that ancient civilizations might have used sophisticated methods for extracting rare metals, possibly including technologies that are only vaguely understood today. For example, in the 19th century, with the development of chemical metallurgy, it was established that obtaining pure metals required the use of special smelting furnaces capable of reaching temperatures above 1,000 degrees Celsius. It is quite possible that ancient cultures used similar methods that we can only appreciate in the light of modern technologies. Research shows that such anomalies in rare metal concentrations can not only indicate ancient activity, but also serve as markers for understanding the technologies used in the past. Comparative analysis with modern deposits shows that such concentrations in ancient layers can be comparable to those found in modern mines, highlighting the high level of metallurgy in ancient times. In 2020, a team of scientists led by Professor Emily Mann discovered layers containing high levels of gold and copper in the context of a Neolithic settlement in China, challenging perceptions of technological progress in this region. Similar findings have also been made in other regions, such as Mesoamerica, where archaeologists found evidence of ore processing, confirming that ancient civilizations could have had access to resources that modern scientists are only beginning to recognize. In recent decades, scientists have begun to uncover isotopic anomalies in ancient rocks that challenge traditional views on the development of technology in the distant past. For instance, in 2018, a group of geologists from the University of Chicago, led by Dr. Nick Taylor, discovered abnormally high levels of carbon isotopes in sedimentary rocks over 600 million years old. These anomalies could indicate the presence of artificial nuclear reactions or other technological processes that may have occurred long before known civilizations emerged. Specifically, the study of shungite deposits on the Kola Peninsula revealed an isotopic composition that deviates from the normal background radioactive level and may suggest effects comparable to nuclear reactions occurring under high temperatures and pressures. Similar anomalies were found in samples collected from layers dated around 300 million years ago in the Appalachian region, where strontium and uranium isotope analysis showed discrepancies indicating possible exothermic reactions. In 2009, research conducted by a team led by Professor Tatiana Ivanova in Siberia discovered anomalous boron and lithium isotope ratios in ancient volcanic rocks, which also suggest the presence of high-energy processes. One of the most intriguing examples is the discovery in India, where in 2015, archaeologists led by Dr. Rajesh Kumar found soil layers with abnormally high concentrations of gold isotopes. These findings may indicate technologies using high temperatures that could have been part of unknown processes occurring millions of years ago. Analysis of samples from the ancient city of Mohenjo-Daro indicates anomalies in silicon and oxygen isotopes, which may be linked to possible artificial processes. These anomalies pose a significant challenge to traditional archaeology and geology, prompting scientists to reevaluate their understanding of the technological progress of ancient civilizations. Specific data, such as radioactive levels and isotope ratios in various geological layers, can provide insights into complex processes that existed on Earth long before the emergence of modern humans. In 2020, a study in the region of Brazil uncovered anomalies in molybdenum isotopes, raising questions about possible ancient technologies that may have required significant scientific knowledge. In ice samples retrieved from Greenland and Antarctica, scientists have discovered traces of pollutants that may indicate the existence of highly advanced civilizations that existed long before our era. In 2015, a research team led by Dr. Emily Hunter from the Climate Research Institute analyzed ice cores taken at depths of over 3 kilometers. These samples contain traces of lead and mercury, with concentrations significantly exceeding background levels typical of natural processes. These metals could have been produced as a result of industrial activity similar to modern times. The research showed that lead was likely released into the atmosphere through the burning of coal and other fossil fuels, challenging the notion that such emissions were only characteristic of the industrial age. In 2016, a group of scientists from the University of California discovered that sedimentary rocks dating back approximately 4,000 years contained soot particles and carbon, which also suggest large-scale activity involving the burning of organic fuels. In particular, in the region of Mesopotamia, archaeologists found artifacts indicating the presence of complex metallurgical processes, which may be related to environmental pollution. In 2018, a study published in the journal Nature showed that ice cores from Antarctica dating back around 300,000 years contained isotopes of carbon, that could not have formed naturally and are likely the result of biomass burning. Simultaneously, sedimentary rocks found along the Black Sea coast contained oil residues dating back to prehistoric periods, challenging traditional notions about the origin of oil. These findings raise questions about which civilizations could have existed on Earth and what technologies they used. In 2020, a study conducted in the Arctic revealed anomalies in the content of polychlorinated biphenyls, PCBs, which were used in electronics and electrical equipment, also suggesting the existence of some form of industry in the distant past. It is important to understand that such findings can fundamentally change our understanding of human history and its interaction with the environment. Samples containing heavy metals and organic pollutants in ancient layers of ice and sedimentary rocks are key to studying questions about possible global catastrophes caused by the activities of vanished civilizations. To date, around 12 different chemical compounds, which do not occur naturally in such concentrations, have been detected in Antarctic ice. Archaeological methods used to identify traces of human activity face significant limitations when dealing with civilizations that existed tens or hundreds of millions of years ago. Firstly, most organic materials decompose within 1,000 years, making it unlikely to find artifacts left by such ancient cultures. For instance, wood, textiles, and other organic materials that could provide valuable information about these people's lives do not preserve in geological layers due to the decomposition process. Additionally, geological processes such as erosion, tectonic plate movements, and volcanic activity can completely alter the landscape, erasing traces of past civilizations. When considering time frames of millions of years, it becomes clear that even if some artifacts had survived, they could have been carried away by river flows or absorbed by sedimentary rocks due to climate or sea level changes. Different geological epochs, such as the Mesozoic or Paleozoic, have unique conditions that can make it difficult or even impossible to find traces of civilizations. For example, conditions in the Mesozoic were vastly different from today's, which could have affected how and where human activity traces might have been preserved. Given these timescales, it is important to note that archaeology, as a science, focuses on more recent time intervals where more reliable dating methods and artifact preservation are available. For instance, radiocarbon dating allows scientists to determine the age of finds, but this method only works for objects less than about 50,000 years old. The use of methods like stratigraphy also requires that soil layers remain relatively intact, which is highly unlikely for layers formed millions of years ago. In such conditions, where soil layers have been repeatedly altered by natural processes, archaeologists cannot rely on conventional methods. Comparing geological and archaeological data also becomes problematic due to the lack of clear and reliable markers, which can lead to incorrect interpretations. Furthermore, many civilizations that existed millions of years ago may not have left any traces, as they could have been small in number or their way of life did not require the creation of permanent settlements. Therefore, studying civilizations from such a distant past requires entirely different approaches and technologies that do not yet exist. As a result, archaeology remains focused on more recent historical periods, making the use of traditional search methods ineffective in finding traces of such ancient cultures. Scientific research aimed at studying these issues requires a new approach and possibly revolutionary methods that are currently beyond our capabilities. For example, existing technologies for analyzing samples from deep within the Earth could offer new prospects, but they are not yet developed to the level needed to find traces of billion-year-old civilizations. In such a situation, archaeology faces stringent constraints that significantly limit its ability to study deep temporal layers. Fossilization is an incredibly rare phenomenon, during which only a minuscule fraction of organisms are preserved. According to paleontologists, less than 1% of all species that ever existed on Earth turn into fossils. For this to happen, several conditions must be met, which are extremely rare. For instance, an organism must be quickly buried by sedimentary materials to prevent its decay. This typically occurs in environments with water, rivers, lakes, or seas. However, even in such ideal conditions, such as marine deposits, only a small fraction of organisms, like mollusks, crustaceans, or certain plant species, can be preserved as fossils. Fossilization goes through several stages, including burial, decomposition of soft tissues, and replacement of tissues with minerals. It is important to note that for replacement to occur, minerals like calcite or quartz must be present to fill the voids in organic remains. This process can take millions of years, and even then, fossils may be incomplete. As a result, finding fossils of complex organisms, such as mammals or even more so intelligent beings, becomes practically impossible. Throughout Earth's history, numerous mass extinctions have occurred, such as the extinction of dinosaurs around 66 million years ago. These catastrophes led to the disappearance of most species and, consequently, reduced the chances of fossil preservation. For example, as a result of the extinction at the end of the Cretaceous period, about 75% of all species on the planet went extinct. Even if intelligent beings existed at that time, the probability that their remains were preserved is virtually zero. The complexity of the fossilization process is also highlighted by the fact that most fossils we find are of marine organisms. Freshwater and terrestrial species are much less likely to become fossils. Research shows that, compared to marine fossils, terrestrial fossils make up only about 10% of the total number found. This makes the probability of finding the remains of terrestrial intelligent beings even more remote. For paleontologists, working with fossils requires the use of complex technologies and methods. For example, using X-ray tomography allows researchers to examine the internal structures of fossils without destroying them. This is particularly important for studying fossils that may contain traces of soft tissues or cells, which usually do not survive. However, such technologies require significant resources and time, and even they do not guarantee the discovery of complete remains. Therefore, fossilization is a process in which only a minuscule fraction of organisms are preserved, making the discovery of fossilized remains of intelligent beings highly improbable. It is known that under ideal preservation conditions, 1 out of every 100 million organisms can be transformed into a fossil. Metamorphism of rock types is a complex geological process that occurs under the influence of high temperatures and pressure, resulting in changes to the mineral composition and texture of rocks. At temperatures above 300 degrees Celsius and pressures exceeding 1,000 atmospheres, the initial rocks, known as parent rocks, undergo transformation that can completely erase any traces of their original structure. This process can take millions of years and involves a mechanism called recrystallization, where minerals rearrange without melting. For example, limestone subjected to metamorphism transforms into marble, while clay can become slate. One of the most striking examples of metamorphism is the formation of mountain ranges, such as the Appalachians in North America, where high temperatures and pressure, resulting from tectonic processes, led to the formation of complex metamorphic rocks. During metamorphism, not only does the mineralogical composition change, but any organic remains are also destroyed, as high temperatures break carbon bonds, and pressure compresses structures to the point where they can no longer exist. As a result, in metamorphic rocks such as gneiss or quartzite, no traces of human processing or use can be found, as all previous changes are erased. For instance, in gneiss, one can see stripes formed due to the direction of pressure, but no artifacts indicating human activity are found. Temperatures reaching 800 degrees can lead to changes in the chemical composition of minerals, making them unsuitable for any cultural or technological purposes. Consequently, metamorphism results in rocks that are beautifully colored and structured, but do not carry any history of their creation or human influence. One of the main factors contributing to metamorphism is plate tectonics, where the collision or separation of plates can cause significant geological changes. This process can also be caused by magmatic activity, when hot magma masses rise and heat surrounding rocks. For example, in the Great Smoky Mountains region of the United States, there is a significant amount of metamorphic rocks formed under pressure and high-temperature conditions, making this region of interest to geologists and researchers. In such conditions, even the most durable rocks, such as granite, can undergo changes, leading to the formation of new minerals such as biotite or muscovite. As a result, metamorphism not only transforms the structure of rocks, but also creates a range of new minerals that can form depending on the conditions under which the process occurs. For example, the presence of water in the system can lead to the formation of hydrated minerals, such as chlorite or serpentine, which also testify to the complex chemistry of metamorphism. These changes highlight that metamorphism is not just a physical process, but also a chemical one, where the interaction of minerals and fluids leads to the creation of unique geological formations. Metamorphism remains an important aspect of the study of geological processes, as it helps understand how the Earth has evolved over millions of years and how the processes occurring in its interior shape the planet's surface. Subduction is a process in which one tectonic plate, typically oceanic, descends beneath another, usually continental. This phenomenon occurs at the boundaries of plates, where the denser and thinner oceanic crust sinks into the Earth's mantle. An example of this process is the subduction zone along the coast of Japan, where the Pacific Plate is descending beneath the Eurasian Plate. According to geological data, this zone of activity has led to catastrophic events such as the Tohoku earthquake in 2011, which was a magnitude 9 underwater earthquake that caused a tsunami, resulting in the loss of more than 15,000 lives. As the oceanic crust descends into the mantle, it melts, and all minerals and rocks formed during this process disappear, including any traces of civilizations that may have existed on submerged continents. For instance, it is believed that during the subduction of the Atlantic Plate around 100 million years ago, as it descended beneath the North American Plate, significant portions of the continental shelf were lost, where primitive human communities may have existed. Research indicates that these submerged areas could contain not only geological data, but also archaeological finds that are forever lost in the Earth's depths. Scientific projects, such as the Ocean Exploration Trust, explore the depths of the oceans, but most submerged evidence remains inaccessible. The depth of subduction of oceanic crust can reach 100 kilometers, and it is at this depth that processes occur that lead to the formation of magma chambers capable of volcanic activity. Volcanic activity, as seen with the Sakurajima volcano, is also linked to subduction processes and can result in new geological formations that may conceal traces of ancient civilizations. In the vicinity of the Sakurajima volcano, artifacts from the Japanese historical period have been found, but many other traces could have been lost in the process of subduction. Subduction not only shapes new landscapes, but also destroys historical and cultural data that could help us better understand human history. Research shows that many areas now considered barren or insignificant could contain important archaeological layers if not for this constant process of subduction. Subduction zones can also lead to the formation of mountain ranges such as the Himalayas, which resulted from the collision of the Indian and Eurasian plates. On their slopes, traces of human activity can be found, preserved by geological processes. However, any trace of civilizations that existed on submerged continents is forever lost beneath the Earth's surface, leaving only hypotheses about what might have been if these lands had not descended into the planet's depths. This geological activity is reflected in the myths and legends of peoples living in earthquake-prone regions, where residents create their own explanations for the catastrophic events that occur in their lives. Subduction remains one of the most powerful processes that shape the appearance of our planet, while also erasing the memory of people and cultures that once inhabited these lands. Alternative forms of intelligence, distinct from primates, represent a complex and multifaceted concept that cannot be reduced to simple classification. These forms of intelligence can be found in various ecosystems, where life conditions necessitate the development of unique adaptation and interaction mechanisms with the surrounding environment. For instance, in oceanic ecosystems, there are organisms with highly developed communication systems that use sound signals and chemical substances to transmit information. Studies conducted at the end of the 20th century revealed that some marine mammals are capable of using complex sound sequences for communication, indicating not only the presence of social structures, but also a form of cognitive activity that differs from the conventional understanding of intelligence. In this context, it is worth noting that in 2001, scientists from the University of California published research confirming the use of tools and planning behavior in certain organisms, which challenges traditional notions of intelligence limited to primates and humans. At the same time, there are organisms that have developed learning and adaptation abilities in response to changing environmental conditions, such as high competition or stress. These forms of intelligence can manifest as the ability to change behavior based on surrounding factors, demonstrating a certain level of self-awareness or reflection. In 2003, researchers from the University of Oxford discovered that some species living in isolated conditions exhibit unique forms of social organization and interaction that originate from the group rather than individual organisms. This underscores that intelligence can be both individual and collective, altering our understanding of how different organisms perceive and interact with the surrounding world. Additionally, the existence of symbiotic relationships between different forms of life, such as between plants and fungi, also indicates the presence of intelligence in forms other than primates. These symbiotic relationships often rely on complex information and resource exchange systems, which are signs of advanced cognitive activity capable of adapting and evolving in response to changes in ecosystems. There are also examples where organisms develop survival strategies that can be interpreted as the use of intelligence in conditions where traditional forms of intelligence based on human experience are not applicable. In 2006, a group of scientists from the University of Texas presented results showing that some marine organisms use collective behavior strategies to achieve their goals, further emphasizing the diversity of intelligence forms on the planet. These alternative forms of intelligence can include aspects such as emotional intelligence, which manifests in the ability to empathize and interact with other organisms, observable in various ecosystems. For example, studies conducted in 2008 demonstrated that some organisms can recognize the emotional states of other individuals and adapt their behavior accordingly, opening new horizons in the understanding of intelligence and its forms. Thus, the concept of alternative forms of intelligence extends far beyond the traditional view of intelligence based on primates and encompasses a multitude of interactions, adaptations, and behavioral forms that have existed and continue to develop on our planet. In 2009, research was published showing that some forms of life possess the ability to solve problems, which is also a manifestation of intelligence distinct from primates. Reptiles represent one of the most successful groups of animals that dominated our planet for more than 150 million years. Among them, the theropods, particularly the troodontids, stand out. With their relatively large brains, they serve as an example of the potential for the development of intelligence in this evolutionary line. Troodonts, which lived around 100 million years ago during the Cretaceous period, had brains of a size comparable to those of modern sparrows, which might seem insignificant at first glance, but was a significant achievement for reptiles. Their brain-to-body ratio indicates a high level of intelligence that could have been expressed in complex social interactions, hunting, and possibly even tool use. Scientists like Dr. Kenneth Carey from Canada have conducted research showing that troodonts had a well-developed visual and auditory system, which could have contributed to their ability to learn and adapt to their environment. These dinosaurs had unique features, including curved claws on their front limbs, which could have been used for capturing prey or manipulating objects, indicating a possible predisposition to more complex behavior. According to available data, they could have hunted small mammals and other dinosaurs, which required not only physical agility but also a certain level of planning and group action. The size of trudonts varied from 1 to 2 meters in length, allowing them to be sufficiently mobile and agile predators. Scientists suggest that their social structures might have been similar to those of modern birds, opening a discussion about the development of social skills and communication among reptiles. An important aspect is that trudonts had a relatively high metabolic rate, which could have contributed to their activity and ability to quickly respond to changes in the ecosystem. Additionally, their tooth structure indicates that they were omnivorous, allowing them to adapt to various food sources. Research shows that they could have used their claws not only for hunting, but also for defense, making their behavior more diverse. It is worth noting that trudonts are one of the first groups to exhibit signs of social behavior. They had a developed sense of family and possibly cared for their offspring, which is an important aspect in the evolution of intelligence. Fossil finds in places like Mongolia show that trudonts often lived in herds, indicating complex social interactions. Notably, their remains were found in areas with diverse flora and fauna, suggesting that they could have inhabited various ecosystems and adapted to changes in climate. Trudonts disappeared from the scene at the end of the Cretaceous period, but their legacy and the potential for intelligence in reptiles continue to fascinate paleontologists. These dinosaurs are an important subject of study, as they can provide insights into the evolution of intelligence in other animal groups. Comparing their capabilities with those of modern birds raises questions about how different the paths of intelligence evolution might have been if dinosaurs had not gone extinct. Studying trudonts and their behavior can shed light on the mechanisms of adaptation and survival that existed on Earth for millions of years. Octopuses are a unique example of potential intelligence development among cephalopod mollusks. These creatures possess a complex nervous system that significantly differs from that of most other animals. Octopuses have around 500 million neurons, comparable to the number in domestic dogs. However, unlike mammals, the majority of an octopus's neurons are not located in its brain, but in its arms, allowing them to act independently and coordinately. For instance, octopuses can open cans to obtain food using their tentacles, demonstrating their ability to manipulate objects and solve problems. This behavior has been documented in laboratory settings where octopuses, such as the common octopus, Octopus vulgaris, have shown the ability to learn and remember solutions to complex tasks for several weeks. In 2000, a study conducted by zoologist Dr. Jennifer Mulder demonstrated that octopuses can solve puzzles using their cognitive skills to obtain food by passing through a series of steps. These mollusks also use tools, which is rare in the animal kingdom. In 2015, a group of scientists led by Dr. Nick Brelsner observed octopuses using coconut shells for protection and shelter, indicating their understanding of their environment and the use of resources. Furthermore, octopuses are capable of camouflage, which not only helps them avoid predators, but also suggests complex behavior related to social interaction. They can change the color and texture of their skin, making them masters of disguise. In 2006, a study conducted by Dr. Katrina Taylor showed that the octopus's ability to camouflage can be used not only for protection, but also for communication with other octopuses. Notably, octopuses have a short lifespan, typically ranging from 1 to 2 years, which forces them to adapt and learn more quickly than many other species. This underscores their ability to evolve rapidly and develop cognitive skills. Such characteristics make octopuses a subject of study for scientists investigating the evolution of intelligence and adaptive behavior. Octopuses not only astonish with their intelligence, but also challenge traditional notions of what intelligence is and how it can manifest in different forms of life. One of the most striking examples is an octopus named Ink, who became a social media sensation in 2015 when it used tools to solve problems in an aquarium, attracting widespread attention. Octopuses represent a unique case that forces us to reevaluate our understanding of consciousness and intelligence among animals. Arthropods, particularly social insects, possess unique abilities that place them among the most intriguing subjects for studying the evolutionary potential of collective intelligence. For instance, ants, which have existed on Earth for over 100 million years, exhibit complex forms of organization and cooperation. A colony of ants can number up to 1 million individuals, each performing a specific role, from worker to soldier. This diversity of functions allows ant colonies to construct intricate architectural structures, such as mounds that can reach several meters in height and contain thousands of tunnels and chambers. For example, ant mounds built by the species Atta are renowned for their complex structure and can house several million individuals. These structures are created using simple yet effective communication mechanisms. Ants leave pheromones that help others find food sources or the colony. This form of collective intelligence enables ants to adapt to changes in their environment and effectively solve problems they encounter. Bees, another example of social insects, also demonstrate a highly developed collective intelligence. They can organize their work in a hive, where each individual performs tasks based on its life stage. Hives can reach heights of up to 2 meters and contain up to 60,000 bees. Bees use a special dance to share information about the location of food sources, allowing them to efficiently organize search parties. Research shows that such social structures enable bees and ants not only to survive, but to thrive in conditions where individual organisms would struggle. It is important to note that these communities can have a significant impact on ecosystems. For instance, ants play a key role in the decomposition and recycling of organic materials, contributing to the health of the soil. Social insects also serve as a crucial part of the food chain, providing food for many other animals. Studies conducted at the end of the 20th century indicate that social insects can solve problems that require understanding and applying various strategies, challenging traditional notions of intelligence. For example, in experiments with ants conducted in 2005, scientists found that ants can find the shortest path to a food source despite obstacles, demonstrating their high level of planning and adaptability. The size of colonies and the degree of organization within them likely contribute to the emergence of collective intelligence that can be compared to human intelligence, but operates at a different level. A comparison between architectural structures created by humans and ant mounds or beehives shows that nature provides numerous examples of complex constructions that do not require the intervention of a highly intelligent being. For instance, ant mounds can be designed to effectively manage temperature and humidity, creating ideal living conditions for the colony. Research indicates that such structures can function as integrated organisms, where all parts are interconnected and work for the common good. This raises the question of how complex systems created by arthropods might be analogous to human cities, and what lessons we can learn from their architecture and organization. Ultimately, studying social insects opens new horizons for understanding collective intelligence and evolutionary processes that could lead to the creation of complex systems based on simple interactions. In 2017, it was established that ants can exhibit forms of planning, further confirming their high intellectual abilities. In biology, there is a concept known as convergent evolution, which describes the process by which different species independently develop similar characteristics or adaptations without being closely related. This phenomenon can be observed in various ecological niches and conditions where organisms face similar challenges and resources. For example, if two organisms live in the same environment, they may develop similar survival strategies, such as body shape, hunting methods, or ways to protect themselves from predators. Convergent evolution demonstrates how different lines of life can find similar solutions to the same problems, despite their ancestors being completely different. From a genetic perspective, different species can use similar genes to develop similar traits, highlighting the universality of some biological processes. It is important to note that convergent evolution is not limited to external features, but also includes internal mechanisms such as metabolism and reproduction systems, which can develop independently but lead to similar results. This phenomenon has deep roots in evolutionary theory and helps explain why certain characteristics are found in completely different groups of organisms, even if their evolutionary paths did not intersect. For instance, similar adaptations can arise in response to similar climatic conditions, such as arid climates, where organisms may develop mechanisms for water storage or minimizing water loss. Research shows that convergent evolution can occur at different levels of biological organization, from molecules to entire ecosystems. In 2016, scientists from the University of Cambridge conducted a study that showed that plant species living in arid zones independently developed mechanisms to minimize water loss, providing a clear example of convergent evolution. Similarly, in zoology, a study conducted in 2018 found that mammals living on different continents developed similar hunting strategies, emphasizing the importance of adaptation to the environment. This phenomenon confirms that evolution is not just a random process, but a dynamic system in which organisms strive to optimize their functions in response to environmental pressure. Convergent evolution also helps explain why some traits, such as the wings of birds and bats, have a similar form, even though their ancestors did not possess this feature. This similarity in adaptations serves as a reminder that life on Earth is constantly seeking effective solutions for survival. Ultimately, the study of convergent evolution allows for a deeper understanding of evolutionary processes and the mechanisms that lead to the formation of similar traits in different groups of organisms, making this topic particularly interesting for biologists and natural scientists. Convergent evolution of the eye in vertebrates and cephalopod mollusks serves as a striking example of how complex organs can develop independently in different evolutionary lineages. In vertebrates, such as fish, amphibians, reptiles, birds, and mammals, eyes have a similar structure, including the cornea, lens, and retina, which enables them to effectively perceive light. These eyes have evolved over more than 500 million years, beginning with simple light-sensitive cells in early multicellular organisms. Meanwhile, cephalopod mollusks like octopuses and squids have independently developed their eyes, although they share similar elements such as the lens, iris, and retina. Notably, the eyes of octopuses and mammals have a similar structure but differ in their formation. In octopuses, eyes develop from skin cells, while in mammals, they develop from neurons. This demonstrates that different organisms can arrive at similar adaptations to their environment, even if they have different ancestral lineages. Scientists such as Professors David Salmon and Catherine Hayes have studied the evolutionary paths of eye development, identifying key molecules and genes responsible for the formation of these complex structures. They discovered that in both types of organisms, genes PAX and 6 play a crucial role in eye development. For instance, in the octopus Octopus vulgaris and in mammals such as humans, these genes are activated at early developmental stages, leading to the formation of similar eye structures. This process of independent eye development in various species is a clear example of convergent evolution and illustrates how different species can find similar solutions to the same ecological challenge, perceiving light and imaging the surrounding world. Furthermore, the structure of the eye in cephalopod mollusks has unique features, such as the absence of blood vessels in the retina, which prevents image distortion, whereas the eyes of vertebrates have a retina with blood vessels, resulting in a blind spot. This difference underscores how different evolutionary paths can lead to the development of functionally similar but structurally different organs. The study of these two groups of organisms not only deepens our understanding of the mechanisms of evolution, but also opens new horizons in the fields of biology and physiology. An interesting fact: the eye of an octopus is capable of self-regulation, allowing it to adapt to various lighting conditions, whereas in vertebrates, this ability is limited. Echolocation is a remarkable example of convergent evolution observed in bats and cetaceans. Both groups of animals have developed complex sensory systems that allow them to orient and hunt in low-visibility conditions, but they did so independently of each other. Bats, belonging to the order Chiroptera, began developing echolocation around 60 million years ago, which allowed them to occupy the ecological niche of nocturnal predators. They emit high-frequency sounds that reflect off objects and return to them, enabling them to determine the distance and shape of objects. For example, a bat of the genus Myotis can emit sounds with frequencies up to 130 kHz, which significantly exceeds the range of human hearing and allows it to detect even the smallest insects against the background of the environment. On the other hand, cetaceans, such as dolphins and whales, developed echolocation around 30 million years ago. These mammals use low-frequency sounds to explore their underwater environment, where visibility can be extremely limited. Whales, for example, can emit sounds with frequencies up to 20 kHz, allowing them to detect objects at great distances, even in murky water. Interestingly, dolphins have a brain structure that is highly developed for processing sound signals, indicating a high level of cognitive abilities. Both groups of animals have developed specialized anatomical structures, such as the ears of bats and the resonant sinuses of whales, which allow them to effectively perceive sound waves. These adaptations demonstrate how the same ecological pressures can lead to similar solutions in different taxonomic groups. For example, dolphins use echolocation not only for hunting, but also for communication, highlighting their complex social structure. Similarly, bats also demonstrate a high level of social organization, especially in colonies where they interact with each other through sound signals. The phenomenon of convergent evolution of echolocation in these two groups of animals clearly shows how different organisms can develop similar traits in response to similar ecological challenges. Scientists like Dr. Kenneth Norman, studying echolocation in various species, emphasize that the presence of similar ecological niches can lead to the development of similar adaptations, even if organisms have evolved in different conditions. This raises interesting questions about the role of the environment in shaping biological functions. For example, bats and cetaceans do not share common ancestors within the last 100 million years, but their evolutionary paths intersect in the context of adaptation to nocturnal or underwater environments. Echolocation in these animals not only helps them survive in their specific ecosystems, but also opens new horizons for studying biosignals and their influence on animal behavior. As a result, research on echolocation in bats and cetaceans continues to attract the attention of scientists and naturalists who are striving to understand how evolution forms complex perception systems. It is important to note that the study of these mechanisms deepens our understanding not only of biology, but also of ecology, helping us better understand how living organisms adapt to their habitats. Convergent evolution of intelligence is not limited to primates, but also observed in corvids, highlighting how high cognitive abilities can develop in various animal groups across different geological epochs. For instance, chimpanzees, sharing over 98% of genetic material with humans, exhibit complex social structures, use tools, and are capable of learning and solving problems. In laboratory settings, they successfully tackle tasks involving understanding and using tools, as documented in studies conducted in the early 2000s by Dr. Jane Goodall and other ethologists. Meanwhile, corvids, such as crows and jays, display similar capabilities. Research from the 2000s has shown that crows can use multiple tools in sequence to achieve their goals, requiring high cognitive skills. These birds also develop strategies and plan for the future, as demonstrated in experiments by Professor James Shine, who noted that jays can anticipate the need for tools several steps ahead. Interestingly, both primates and corvids have an enlarged cerebral cortex in the region responsible for cognitive functions. A comparison of the brain structure in chimpanzees and corvids reveals similar neural networks, a result of convergent evolution. This means that different evolutionary lineages could arrive at similar solutions in response to analogous ecological challenges. Scientists like Dr. Klaus L.G. Felix emphasize that living conditions, such as the need to find food or interact in social groups, can drive different species to develop similar intellectual abilities. For example, during the Paleolithic period, which began around 2.5 million years ago, the ancestors of modern humans and chimpanzees faced similar ecological challenges, potentially leading to the development of complex social structures and cognitive abilities. Meanwhile, corvids living in diverse ecosystems, from forests to urban parks, also adapted to conditions requiring high intelligence. Both groups of animals use complex forms of communication, which is also a sign of high cognitive functions. For instance, jays use various calls to convey information about food or threats, while chimpanzees use gestures and sounds for interaction. Tool use is another aspect that unites these two groups. Crows studied by Professor Alan Kelly make and use tools from twigs to extract insects from tree bark, demonstrating problem-solving and planning skills. Similarly, chimpanzees use stones to crack open nuts, requiring an understanding of mechanics and purpose. These examples illustrate that high intelligence can develop independently, depending on the ecosystem and social conditions, clearly illustrating the concept of convergent evolution. Historical examples also show that such intellectual adaptations have occurred repeatedly. Around 100 million years ago, during the Cretaceous period, some dinosaurs, such as theropods, exhibited social behavior reminiscent of modern primates and birds. This indicates that high cognitive abilities could appear in various forms and in different species, opening new horizons for understanding the evolution of intelligence. As a result, contemporary research shows that intelligence is not a unique human trait, but a general outcome of adaptation of various animal groups to changing living conditions. There exists a concept according to which humanity is moving towards technological singularity, a state where the speed of technological progress becomes so high that it begins to outpace society's ability to adapt to changes. This phenomenon can be observed in various spheres of life, from medicine to transportation. For instance, in the last few decades, the speed of information transfer has increased by thousands of times due to the development of the Internet, which has fundamentally changed the ways of communication, learning, and doing business. Additionally, it is noted that the development of algorithms and artificial intelligence allows for the analysis of enormous volumes of data at unprecedented speeds, leading to faster decision-making and improvement in the quality of life. Progress in computing power has also played a significant role. With each new generation of processors, the number of calculations per second increases, enabling the creation of more complex and powerful systems. The acceleration of civilization's development has become possible due to the accumulation of knowledge, the transfer of information, and the interconnection of various disciplines, which leads to synergy. As a result, each new technological step is based on the previous one, creating a snowball effect. For example, the invention of the Internet opened the doors to the development of social networks, which, in turn, contributed to the creation of new forms of business and interaction. This creates a closed loop where each new success accelerates further achievements. An example of this is medical diagnostics. With the help of new data analysis methods, doctors can more quickly identify diseases, allowing treatment to begin at earlier stages. This leads to an increase in life expectancy and improvement in the health quality of the population. Research shows that in the conditions of rapid technological progress, social structures also change. New professions appear, old ones disappear, and the way of work changes. People begin to demand from education new skills that are relevant in the conditions of constant changes. Social movements also adapt to new conditions, using new technologies for organization and mobilization. This is not just evolution, but a revolution that affects all aspects of life. When we look at previous epochs, such as the Industrial Revolution, we can see that changes occurred gradually, whereas now the speed of changes is increasing geometrically. It is important to note that this does not always mean positive results. Rapid technological development can lead to social inequality, where certain groups of the population are left behind. Therefore, the The concept of technological singularity is not just a futuristic idea, but a real perspective with which humanity will have to deal in the coming decades. It is expected that in the future, technologies will develop so quickly that their impact on society will become difficult to predict. This dynamics will present people with new challenges and opportunities, requiring not only adaptation, but also active participation in shaping the future. According to some research, in the coming decades, the number of people working in new industries may increase several times, while traditional professions will decrease. From the moment the first stone tools appeared, approximately 2.5 million years ago, humanity embarked on a path of rapid progress. These primitive tools, created by our ancestors, Homo habilis, allowed them to hunt and gather food more efficiently. This laid the foundation for further development. Around 150,000 years ago, Homo sapiens began to use fire, opening new horizons in cooking and protection from predators. The transition to an agricultural society around 10,000 years ago led to a sedentary lifestyle, which contributed to the creation of the first cities and civilizations, such as Mesopotamia and ancient Egypt. In these regions, irrigation systems developed, increasing crop yields, and writing emerged, allowing the recording of achievements. Around 1300 BCE, the Phoenicians invented the alphabet, which became the basis for most modern languages. The transition to metalworking, which began around 3000 BCE, led to the creation of bronze and iron, significantly improving the quality of tools and weapons. In antiquity, in the 5th century BCE, Greek philosophers like Archimedes began to develop sciences that laid the foundation for subsequent technological breakthroughs. With the invention of the printing press by Johannes Gutenberg in the mid-15th century, the era of knowledge dissemination began, accelerating the scientific revolution. In the 17th century, Galileo Galilei and Isaac Newton laid the foundations for modern natural sciences, marking a significant step in understanding the laws of nature. The Industrial Revolution of the 18th century, with the invention of the steam engine, led to mass production and a change in society's structure as people began to migrate to cities for factory work. In the 19th century, with the advent of electricity and the telegraph, the world became more interconnected. The 20th century witnessed the space race between the USA and the USSR, culminating in the moon landing in 1969. This technological leap became possible due to decades of research and development, from Konstantin Tsiolkovsky's rocket technology to satellites launched into space. Such exponential growth in technology could also occur in other intelligent species if they encountered similar natural and social conditions. For example, the availability of resources like minerals for tool creation and access to food could facilitate the development of civilization. If we assume that there are intelligent beings on other planets, they could follow a similar path in their own conditions, creating their own technologies, as each new stage of development opens doors to new discoveries. In this context, it is important to note that humanity has passed through many stages, each of which became the foundation for the next, creating a chain of events that ultimately led to modern achievements. Scientific research, such as the work of Levin and Sultanov, emphasizes that technological evolution is not linear but spiral, where each new technology does not simply add up, but fundamentally changes social structures and ways of life. For example, the Internet, which appeared at the end of the 20th century, changed not only communication, but also business, education, healthcare, and many other spheres. This process continues to develop, and each new technological innovation becomes a catalyst for further changes, creating a new society capable of achieving even greater feats. In a sense, one can say that technological progress is not just the accumulation of knowledge, but a constant rethinking of existing paradigms, leading to the creation of something completely new and unimaginable. In this context, the evolution of technology is not only the history of humanity, but also the potential history of any intelligent beings in the entire cosmos. Exploring the concept of the technological horizon offers an intriguing perspective on the future of civilizations. The technological horizon is the point at which technological achievements reach such a level that the society becomes invisible to external observers. This can occur through transformation or self-destruction. Let's consider the example of the Mayan civilization, which reached significant levels of astronomical knowledge and architectural achievements, including the construction of pyramids in Tikal and Copan. However, by the 9th century AD, after a major drought and social conflicts, it began to decline. In this context, it is notable that the growth of population and depletion of natural resources led to the civilization's inability to adapt to changing conditions, resulting in its collapse. A similar fate befell the Roman Empire, which at its peak in the 1st century AD controlled vast territories from Britain to Egypt. However, internal conflicts, economic difficulties, and invasions by barbarians in the 5th century brought Rome to the brink of collapse. Contemporary researchers, such as Niall Ferguson, emphasize that most civilizations face a critical moment when their technologies and systems of governance become ineffective. They describe how societies like ancient Egypt could endure for thousands of years due to sustainable technologies, but ultimately failed to adapt to new challenges, leading to their decline. The technological horizon can be seen as the limit of possibilities, where the achieved level of development leads to self-enclosure, and the civilization either disappears or transforms into something new. This process is also observed in the modern era, where rapid technological changes, such as artificial intelligence and genetic engineering, pose ethical and social challenges for humanity. As researchers delve deeper into this concept, they encounter questions about the survival of societies and their ability to adapt to new conditions. This can be illustrated by the example of Japan, where advanced technologies and cultural traditions coexist, but a demographic crisis threatens the country's stability. Studies show that as societies reach the technological horizon, they must reevaluate their values and goals. Perhaps this struggle for survival in the face of the technological horizon has been the driving force behind social changes throughout history. Many civilizations, such as the Incas, achieved significant successes in agriculture using terrace farming and irrigation systems, but ultimately could not withstand external threats and internal conflicts. Scientific works, such as Collapse: How Societies Choose to Fail or Succeed, by Jared Diamond, examine how ecology and technologies influence the fate of civilizations, highlighting that the choice of technologies and their impact on society can lead to both success and failure. It is also important to consider that at different stages of development, the level of control over natural resources and technologies may not meet the needs of society. For example, during the 19th century, the Industrial Revolution led to a growth in population and resource consumption, threatening the ecological balance. The result was environmental pollution and climate change, which we continue to observe today. The concept of the technological horizon shows that civilizations that cannot adapt to new challenges risk losing their identity and disappearing. Ultimately, each society must independently choose its path and understand the consequences of its decisions in the context of technological advancements. In the 21st century, we observe how technological progress has become an integral part of daily life, influencing all spheres, including education, healthcare, and communication. Studies show that the adoption of new technologies requires societies to continually analyze and reassess existing practices. For instance, with the development of the internet and social networks, new forms of interaction have emerged, which in turn have changed the ways we understand personal boundaries and privacy. It is important to remember that each society has its unique conditions and challenges, and what works for one civilization may not be effective for another. Scientific works, such as The Innovator's Dilemma by Clayton Christensen, emphasize that companies and societies that cannot adapt to innovations often find themselves at a disadvantage. It is intriguing to consider what will happen to our civilization when we reach our technological horizon. Effective measures for control and adaptation to new conditions can help avoid crises and self-destruction, but only time will tell how it all unfolds. Scientific research shows that civilizations that can effectively use technologies and adapt to changes have a better chance of survival. The technological horizon remains a critically important concept for understanding the future of humanity and its place in the world. Archaeological visibility refers to the concept that describes how well various materials and technologies are preserved in an archaeological context and can be discovered during excavations. This visibility depends on numerous factors, including the chemical composition of materials, burial conditions, climatic factors, and even the time elapsed since their use. For instance, organic materials such as wood or textiles are prone to decomposition and often do not survive in humid climates, whereas ceramics or stone can endure for centuries. Archaeologists employ methods to assess the visibility of different objects, which may involve analyzing the environment where artifacts were found and studying the characteristics of the soil in which they were buried. For example, in high-temperature and dry climates, organic materials can be preserved significantly better due to lower humidity levels, which in turn affects archaeological visibility. A crucial aspect is also the level of technology used in the creation of objects. Technologies that require complex processing or specific conditions can reduce visibility if they were not documented or if their artifacts did not survive. Production mechanisms, such as kiln-firing ceramics or metalworking, also play a significant role in the durability of artifacts. For instance, if items were made using high temperatures, this increases their strength and chances of survival in the archaeological layer. The study of archaeological visibility is also linked to understanding cultural practices of a society. For example, if a culture actively used certain materials but did not leave significant traces, this may indicate the use of technologies that either did not survive or were forgotten. This creates gaps in the archaeological record that can hinder a complete understanding of cultural evolution. Comparing different cultures and their approaches to material use can provide additional insights into how technologies developed and which social practices influenced their choice. Archaeologists, by studying these aspects, can use methods such as radiocarbon dating to determine the age of finds and the context in which they were used. This helps create a more comprehensive picture of the historical process. The importance of archaeological visibility is underscored by the fact that it not only affects the number of artifacts found, but also the quality of information that can be extracted from them. In simpler terms, the higher the archaeological visibility, the more information about the past can be obtained. This also implies the need to use modern technologies, such as ground-penetrating radar or analytical methods, which can help in the discovery and preservation of information about finds before their physical retrieval. For example, using ground-penetrating radar, archaeologists can investigate underground structures without damaging potential artifacts, opening new horizons for the study of archaeological visibility. These technologies not only increase the chances of discovering artifacts, but also allow for more precise interpretation of data obtained during excavations. For instance, analyzing the chemical composition of soil can provide insights into the materials used in a particular area and how they interacted with the surrounding environment. As a result, archaeological visibility becomes a key concept for understanding not only what has been preserved, but also why this preservation was possible. There are numerous factors influencing visibility, from the surrounding environment to cultural practices, making the study of archaeological heritage a complex and multifaceted process. Archaeological visibility, therefore, is a critically important element in the study and interpretation of various cultural and historical layers. It allows not only for the identification and preservation of artifacts, but also for a deeper understanding of the evolution of technologies and cultural practices that have shaped humanity over the centuries. Stone as a building material possesses remarkable durability, allowing it to endure for millions of years, but this is only possible under certain geological conditions. For instance, limestone, used in the construction of many ancient monuments, is formed by the precipitation of calcite in seawater and can last for centuries under suitable conditions. The most notable examples of stone's longevity can be found in structures like the Pyramids of Giza, built around 4,500 years ago. These monumental constructions, made of limestone and granite, have withstood the test of time thanks to Egypt's dry climate and stable geological conditions. However, even stone structures can disappear if conditions become unfavorable. Water, temperature changes, earthquakes, and even human activity can significantly damage stone constructions. For example, in Iran, where the famous Persepolis is located, many stone elements were destroyed due to invasions and the exploitation of natural resources such as water, which erodes the foundations of buildings. In other cases, like in Mesopotamia, ancient cities built of fired clay bricks were subjected to erosion and flooding, leading to their complete disappearance. There are numerous examples where powerful stone walls and temples, once towering many meters high, have become part of the earth, buried under layers of soil and sand. In particular, in Machu Picchu, the stone structures built by the Incas in the 5th century were eroded due to the tropical climate, leading to partial destruction and overgrowth by vegetation. The widespread use of stone in the architecture of ancient civilizations is also linked to their local geological conditions. In regions with active seismic activity, such as Japan or parts of the Andes, stone buildings often suffered from destructive earthquakes, leading to their complete loss. Comparing different locales shows how geological conditions, such as groundwater levels and soil type, affect the preservation of stone structures. In regions with high rainfall, such as tropical forests, stone constructions are subject to significant corrosion and biological activity, which shortens their lifespan. For example, the temples of the Maya in Central America, despite being built of stone, were also affected by vegetation and high humidity, leading to their destruction and flooding. Additionally, human activity, such as the construction of new buildings on old ruins, can also contribute to the disappearance of stone monuments. A notable example is the Colosseum in Rome, which over time lost some of its blocks, which were used for the construction of new buildings. Despite all these threats, some stone structures can remain intact for thousands of years in ideal conditions. For instance, the famous megalithic structures on the British Isles, such as Stonehenge, are in relatively good condition due to their location in a stable geological environment, protected from erosion and destructive factors. An example is also the Temple of Solomon, built in the 10th century BC, which, despite being destroyed, left traces of its former power and grandeur. Many ancient stone structures, such as the temples in Angkor, serve as a reminder that even the strongest materials can become victims of time and circumstances if not properly protected. It is impossible to ignore the fact that metals, which in our consciousness are perceived as strong and durable, actually undergo destruction on a geological timescale with remarkable ease. For instance, iron used in the construction of Roman aqueducts in the 1st century AD begins to corrode within just a few decades after being decommissioned. Corrosion occurs due to the influence of moisture and oxygen, leading to the formation of rust, which eats away at the metal and weakens structures. Research has shown that even alloys such as stainless steel lose their protective properties under the influence of seawater within just a few thousand years, which may seem insignificant compared to the centuries during which stone structures could remain intact. Gold jewelry found in the tombs of ancient Egyptians demonstrates that gold, although not subject to corrosion, can oxidize and change color if not stored in ideal conditions. In this context, it is worth recalling artifacts made of bronze, which were widely used in antiquity. Bronze, an alloy of copper and tin, loses its strength over time, especially in high humidity conditions, as evidenced by finds from archaeological excavations dating back to the 3rd century BC. For example, bronze statues created during the Hellenistic period in Greece were found to have undergone significant oxidation and destruction, as indicated by the increased copper content in the remains found at the site. Furthermore, alloys, such as brass, consisting of copper and zinc, are also subject to corrosion, resulting in the formation of a green patina known as verdigris. This serves as a clear example of how even the use of strong metals can have their durability significantly limited by external factors. It is important to note that even modern materials such as aluminum, which is considered relatively resistant to corrosion, lose their strength in acidic environments over time. A study conducted in 2010 showed that aluminum structures used in bridge construction can begin to deteriorate within just 30 years of operation under conditions of increased corrosion load. Conversely, copper, despite its susceptibility to oxidation, can maintain its strength for centuries due to the formation of a protective oxide layer, as seen in the remains of ancient civilizations. Therefore, when considering the durability of metals in geological timeframes, it becomes evident that they are not as durable as they might initially appear. Organic materials such as wood, fabrics, and paper degrade much faster than inorganic materials. For instance, wood can retain its properties for only a few decades under high humidity conditions, especially if it is not treated with protective agents. In tropical forests, where high temperatures and humidity promote the active growth of fungi and insects, wooden structures can disappear within decades. An example of this is the remnants of ancient wooden houses in the Amazon, which were completely destroyed within a century, leaving only small traces of their former existence. Fabrics made from plant fibers like linen or cotton decompose under the influence of light, moisture, and microorganisms. Finding fabrics older than 1,000 years, such as fragments of linen fabric from ancient Egypt, is a rare occurrence. In most cases, such materials turn into dust within a few decades, unless they are kept in conditions that promote their preservation. Paper made from wood fibers is extremely vulnerable. Moisture, oxygen, and light exacerbate the situation. Even in archives where paper is stored in ideal conditions, it still degrades. Research shows that standard paper begins to lose its properties within 30 years. In the 20th century, scientists began to use conservation methods, but they are not always effective, especially if the material is already damaged. For example, during excavations in Pompeii, fragments of papyrus were found that had been preserved due to volcanic ash, but most organic materials found in the area were completely destroyed by time. The study of materials such as wood requires a special approach, as even samples that appear new can be too fragile for further study. As a result, when archaeologists find biological materials, they must consider that only a small portion of them will survive to our time. Scientific methods such as carbon dating or using synchrotrons to study the structure of fibers can provide insights into ancient technologies, but the materials themselves often elude our understanding. It is important to note that even in dry climates like Egypt, organic materials degrade, albeit more slowly. Consequently, researchers must rely on indirect evidence, such as traces of dyes or textile remnants, to reconstruct a complete picture of people's lives in the past. Currently, archaeologists continue to find methods for preserving finds, but the problem of organic degradation remains one of the most challenging in archaeology and historical research. For example, in Russia, in Novgorod, fragments of fabrics and leather dating back to the 12th century were found during excavations, which is an exceptional discovery. However, such finds remain rare, and many other organic materials that could have provided valuable information about the past have vanished without a trace, leaving only mysteries behind. In every civilization, there exists the concept of a technological signature which reflects the unique characteristics and achievements of a society. This signature is formed based on how people utilized the resources available to them and how these technologies impacted their daily lives. In a historical context, three main categories of technological signature can be distinguished: production technologies, construction methods, and communication systems. Production technologies, for instance, include methods of processing raw materials, which are directly linked to the economic development of society. Construction methods demonstrate how civilizations adapted to natural conditions and used available materials to create dwellings, temples, and defensive structures. Communication systems, in turn, reflect the level of organization and management of the population, including the creation of writing and transportation networks. These three aspects interact with each other, creating a comprehensive picture of the technological signature. For example, in some civilizations, the development of agriculture led to the creation of complex irrigation systems, which in turn contributed to population growth and urbanization. Other societies might have focused on maritime trade, which spurred the development of navigational instruments and cartographic systems. All these elements shape the distinctive features of a particular civilization, reflecting its level of development and degree of adaptation to the environment. It is interesting to note that a technological signature can remain noticeable for many centuries, even when the basic structure of society has changed. For example, in some regions, traditional farming methods inherited from ancestors continue to be used, even in the face of global technological and economic changes. People continue to use ancient tools and techniques, creating a unique bond between generations. It is important to note that a technological signature does not always reflect progress in the modern sense. Sometimes it may indicate resilience and the ability to adapt to changes, when a society finds solutions based on traditional knowledge. For example, in some cultures, traditional craft techniques are preserved and developed, despite the pressure of mass production. In this context, a technological signature becomes not just a set of applied tools, but also a symbol of identity and cultural heritage. It can be studied through archaeological finds, historical documents, and ethnographic research, allowing us to reconstruct the picture of people's lives in different historical periods. Each element of a technological signature can tell us about the social structure, economic relationships, and cultural values of a society. For instance, the presence of complex tools may indicate a high level of cooperation and knowledge exchange within a community. The use of certain technologies may also indicate the influence of neighboring cultures, opening avenues for the study of processes of borrowing and adaptation. Therefore, understanding the technological signature of a civilization requires a comprehensive approach and consideration of numerous factors, including climate, available resources, and interaction with other cultures. This makes the study of technological signatures not only intriguing, but also extremely important for understanding our past and its impact on the present. In archaeology and history, it is not only important to record findings, but also to interpret them in the context of time and place, which helps create a comprehensive picture of the development of human civilization. For example, in the 20th century, researchers began to actively use material analysis methods, which allowed for a deeper understanding of how technologies changed under the influence of time and circumstances. Thus, each discovery, each find, becomes part of a broader history of how humanity adapted, developed, and interacted with the surrounding world. The technological signature of a civilization remains an important topic for researchers and historians, who strive to understand how technologies shape society and how society, in turn, influences the development of technologies. Radioactive isotopes serve as unique markers of human technological activity, as they can persist in geological layers for millions and even billions of years. For instance, carbon-14, discovered in 1949 by American chemist Walter Koval, is used for dating organic materials and can be found in samples up to 58,000 years old. However, this is just the tip of the iceberg. Longer-lived isotopes, such as uranium-238, can remain in the Earth for billions of years, providing scientists with crucial data on past events and technological processes. Uranium-238, upon decaying, forms thorium-236, which can also serve as an indicator of anthropogenic changes. For example, as a result of nuclear tests conducted in the mid-20th century in the Pacific Ocean, new markers such as plutonium-241 and strontium-90 were created in geological layers, which can now be detected in sedimentary rocks. These elements, when entering the environment, leave behind long-lasting traces, allowing researchers to reconstruct not only the temporal framework of the nuclear era, but also the scale of human impact on the planet. For instance, analysis of deep-sea sediment samples showed that levels of strontium-90 sharply increased from 1945 to 1965, coinciding with the period of active nuclear testing. This fact served as the basis for establishing the chronology of anthropogenic changes and their impact on ecosystems. Furthermore, research on isotopes in ice cores from Greenland and Antarctica also confirms the presence of radioactive traces, which can tell us about global climate changes caused by anthropogenic factors. For example, in one sample taken from the Greenland ice sheet, traces of ruthenium were found, which are byproducts of reactors and indicate the development of nuclear energy. This discovery allowed researchers to link climate changes with technological breakthroughs. The extent of the spread of radioactive isotopes in geological layers allows not only the dating of historical events, but also the assessment of the consequences of technological activity for the environment. For example, the remains of nuclear reactors left after accidents, such as Chernobyl in 1986 or Fukushima in 2011, remain in the form of radioactive isotopes, which serve not only as markers of time, but also as indicators of the ecological consequences of technological disasters. Thus, radioactive isotopes become an important tool for understanding the interaction between humans and nature, allowing us to look into the future through the prism of the past. It is important to note that research on radioactive isotopes is conducted not only in the field of archaeology, but also in geology, oceanography, and climatology, highlighting their universality as markers of human activity. Scientists continue to develop new methods for detecting and analyzing radioactive elements, opening up new horizons for understanding the history of the Earth and humanity. For example, in 1999, a group of researchers from the University of California, Berkeley, developed a method for identifying traces of radioactive isotopes in ancient sediments, which allows for a more accurate reconstruction of past climate conditions. Thus, radioactive isotopes serve not only as witnesses to technological activity, but also as important elements in constructing a global picture of human interaction with the surrounding world. Synthetic materials and polymers are one of the most striking examples of technological civilization, leaving long-lasting traces in the geological layer. In the 9th year, German chemist Friedrich Hoffmann created the first synthetic polymer, bakelite, which became the basis for numerous products, from electronics to household items. Since then, synthetic materials such as polyethylene, polypropylene, and nylon have permeated our lives, becoming part of many everyday objects. According to estimates, more than 300 tons of plastics are produced every minute worldwide, and these materials have a unique chemical structure that makes them resistant to decomposition. For example, polyethylene can persist in the environment for up to 200 years, and some types of polymers can even last for 1,000 years. This means that synthetic materials form unique geological layers that can persist for millions of years. Research conducted by scientists from the University of Texas at Austin in 2020 shows that even in the deep-sea environment, plastic continues to exist, forming so-called plastic horizons. These horizons can be found in sedimentary layers, creating new opportunities for studying human activity and its impact on the planet. Polymers, such as polystyrene, can form microplastics that penetrate ecosystems and are found in deposits, indicating the scale of pollution and human impact on the environment. In 2018, a group of researchers from the University of California, Santa Barbara, found microplastics in samples collected over the past 50 years, confirming the long-term preservation of synthetic materials in the geological archive. As these layers accumulate, they become important elements for paleontologists and archaeologists, allowing them to reconstruct not only ecosystems, but also cultural practices related to the use and disposal of plastic. This aspect becomes particularly important in the context of climate change and global environmental problems. Synthetic materials not only serve as indicators of our time, but also create new geological phenomena, such as so-called plastic mats, which are formed as a result of the accumulation of plastic waste in oceans and on land. As a result, synthetic materials become a kind of testimony to technological civilization, which through millions of years can tell about how people used, recycled, and even disposed of their resources. Ultimately, the study of these polymers and their impact on the environment will open new horizons for understanding the history of the planet, when future generations will be able to analyze these layers as evidence of human activity. At the same time, this problem requires immediate action, as the level of pollution continues to rise, and the consequences for ecosystems become increasingly apparent. In this context, the synthetic materials we produce today create new challenges for future generations, and it is precisely they who may become the very artifacts that will be studied by scientists through millions of years. In the geological record, one can find evidence of significant changes in landscapes and ecosystems that can tell the story of the activities of ancient civilizations. For example, in the region of Mesopotamia, where the Sumerians lived, archaeologists discovered traces of irrigation systems built around 5,000 years ago. These systems altered local ecosystems, increasing agricultural productivity, which in turn contributed to population growth and the development of cities such as Ur and Lagash. As a result of active farming, which involved the cultivation of barley and wheat, there was a significant change in the soil, which is recorded in geological layers. Ancient civilizations, such as the Maya, also left noticeable traces in the landscape. They constructed extensive terraces and artificial water bodies, which changed not only the local topography, but also the hydrological processes. In the region of modern-day Guatemala and Belize, starting from the 6th century AD, the Maya created complex water management systems that allowed them to effectively use rainwater and irrigate fields. These actions led to changes in ecosystems, including the extinction of some plant and animal species, which is reflected in fossil finds. In ancient Rome, starting from the 3rd century BC, the construction of roads and aqueducts also left their mark. The Romans built over 100,000 kilometers of roads, which not only changed transportation routes, but also affected the ecosystem, facilitating the spread of invasive plant and animal species. For example, with the spread of agricultural crops such as olives and grapes to new regions, there was a change in the local flora and fauna. In India, in the Indus Valley, archaeologists found evidence of large-scale agriculture and urban planning dating back to the Indus Valley Civilization, which existed around 3,000 years ago. The plans of cities such as Harappa and Mohenjo-Daro show a high degree of organization, including drainage systems and water supply. These changes in the landscape also affected the ecosystem of the region, altering hydrological conditions, which was confirmed by studies of sedimentary layers in the Indus River. Significant changes in landscapes also occurred in North America, where Native Americans built complex drainage systems, such as in the Pueblo Valley. These irrigation systems, used for farming, changed the structure of the soil and led to an increase in the diversity of crops. As a result of this activity, there were also changes in local ecosystems, which are recorded in paleoecological data. Thus, each of these examples demonstrates how human activity could change ecosystems and landscapes, leaving significant traces in the geological record. Such changes are important indicators that allow modern scientists to reconstruct the picture of life in ancient civilizations and their impact on the environment. In particular, the analysis of carbon and oxygen isotopes in sedimentary rocks can provide insights into the climatic changes that occurred as a result of these activities. For example, studies have shown that in some regions, changes in the composition of vegetation coincide with periods of intensive agriculture. Comparing fossil remains with modern samples of flora and fauna can help determine which species became extinct due to human activity, and which, conversely, gained an advantage. Scientific skepticism is a fundamental concept in the scientific method, enabling the separation of facts from fiction and the verification of hypotheses based on rigorous logic and evidence. It is not merely a doubt in assertions, but an active approach to information analysis, where every claim must be supported by reliable data. Throughout history, many significant scientific discoveries, such as Albert Einstein's theory of relativity or Charles Darwin's theory of evolution, have faced harsh criticism and skepticism. For instance, in the early 20th century, when Einstein first presented his special theory of relativity, many scientists rejected it based on traditional notions of space and time. However, over time and with the advent of new experiments, such as observations of light deflection during the solar eclipse in 1919, the theory was confirmed and accepted by the scientific community. Scientific skepticism demands not only critical thinking from researchers, but also a willingness to revise their beliefs in light of new data. This means that even the most widely accepted scientific theories can be challenged if compelling evidence emerges to refute them. It is important to note that skepticism is not equivalent to denial. Rather, it is a pursuit of truth through analysis and verification. Scientific skepticism also encompasses an understanding of probabilities and statistics, allowing researchers to draw conclusions based on quantitative data. For example, in biology, numerous experiments in genetics and selective breeding have confirmed the theory of natural selection, but only after repeated verification and analysis of results. In psychology, skepticism helps distinguish real effects from false correlations, which is particularly important in behavioral research. A notable example is the history of parapsychology, where many studies failed to demonstrate reliable results, leading to a critical re-evaluation of methods and approaches in this field. Scientific skepticism also contributes to a deeper understanding of human nature and perception, as many people tend to believe theories that align with their personal convictions, ignoring facts that contradict them. In this context, it is crucial for scientists to separate their personal opinions from objective reality, relying on data rather than conjecture. Such a stance facilitates the advancement of science and deepens our understanding of the world, as evidenced by numerous historical examples where new discoveries challenged established beliefs. Scientific skepticism requires continuous learning and a readiness for change, as science is not static. For instance, in the 21st century, we have witnessed a revolution in molecular biology and genetics, with methods such as CRISPR gene editing raising new questions about what it means to be human and what ethical boundaries we should establish. This dynamic requires scientists not only to possess knowledge, but also to critically evaluate their discoveries and their consequences. Scientific skepticism also plays a crucial role in assessing new technologies and their impact on society, making it an indispensable tool in today's rapidly changing world of data and information. For example, in the field of climatology, skepticism towards data on global warming has led to a more thorough investigation of climate models and their predictions. This confirms that well-founded skepticism can lead to a deeper understanding and more accurate conclusions. Ultimately, scientific skepticism not only drives the progress of science, but also helps society make more informed decisions based on facts rather than assumptions. Scientific skepticism requires all participants in the scientific process to be honest and open to new ideas, even if they contradict previously held beliefs. The principle of Occam's razor, formulated by the English monk and philosopher William of Ockham in the 14th century, states that among several possible explanations, the simplest one should be preferred, requiring no additional assumptions. This principle has become fundamental in scientific methodology and is applied in various fields, from physics to social sciences. It implies that if two explanations equally well explain observed phenomena, the simpler one is considered more probable. For example, in biology, when researchers try to explain the evolution of a particular trait, they may consider several hypotheses. If one hypothesis requires many additional factors to explain the observed phenomenon, while another is based on fewer assumptions and yields similar results, the principle of Occam's razor dictates preferring the simpler hypothesis. This does not mean that complex models are always incorrect, but they must be justified by additional data and reasoning. Scientists like Albert Einstein used this principle when developing their theory of relativity. Einstein aimed to avoid unnecessary complexity in his equations, striving for simplicity and elegance in mathematical expressions, which later became a hallmark of his work. In the history of medicine, the principle of Occam's razor has also been applied. For instance, when doctors consider a diagnosis, they must avoid excessive assumptions about rare diseases if more common explanations can account for the patient's symptoms. This not only saves time, but also focuses on more probable causes of the illness. In astronomy, astronomers apply this principle when explaining the observed movements of planets and stars. Applying the principle of Occam's razor requires scientists to filter information and avoid overly complex theories that could confuse the research. This has become especially relevant in the era of abundant data, where scientists must sift through a vast amount of information to select the most significant and simple explanations. For example, in climatology, when scientists analyze climate changes, they may encounter numerous factors such as solar activity, volcanic activity, and human impact on nature. By applying Occam's razor, they can focus on those factors most likely to influence current climate changes, avoiding overly complex and convoluted models that could distract from the key causes. In psychology, the principle of Occam's razor is also applied when researchers study human behavior. If two different approaches can explain a person's behavior, the one requiring fewer additional assumptions about personal motivations or psychological states is preferred. This approach allows researchers to focus on more universal behavioral patterns that can be tested and validated. Thus, the principle of Occam's razor has become an essential tool in scientific practice, helping researchers avoid unnecessary complexity and focus on the most probable and simple explanations of observed phenomena. It is applied in all scientific fields and serves as the basis for constructing effective and testable hypotheses. The principle has been reinterpreted in various contexts, but its essence remains unchanged. Simplicity of explanation is often a sign of its truth. Simplifying hypotheses does not mean underestimating them. It simply emphasizes the importance of not complicating explanations without necessity. For instance, in mathematics and statistics, the use of simple data analysis methods often proves more effective than the use of complex models that can lead to errors or misunderstandings. Researchers like economist John Maynard Keynes also stress the importance of simplicity in economic models, asserting that complex economic theories should be testable and understandable to be practically applicable. The principle of Occam's razor continues to be relevant in scientific debates, sometimes sparking disputes about how far researchers can go in simplifying their theories. For example, in modern research on artificial intelligence and machine learning, where models can be extremely complex, scientists must continually check the necessity of all elements of their algorithms to avoid unnecessary complexity and focus on the most significant factors. By applying this principle, they can create more efficient and adaptable systems that are easier to interpret and use in real-world conditions. Ultimately, the principle of Occam's razor remains not only the foundation for building scientific methods, but also a vital guide for researchers striving for clarity and precision in their work. The question of the existence of ancient prehistoric civilizations provokes numerous debates among scientists and historians. To support such extraordinary claims, extraordinary evidence is required. This principle, formulated by philosopher Karl Popper, suggests that the more unusual a hypothesis, the more compelling evidence is needed to confirm it. For instance, the claim that a highly advanced civilization existed on Earth several thousand years before the known societies emerged requires not only artifacts, but also systematic research confirming technological achievements that could be compared with known civilizations. Let's consider the case of the mythical Atlantis. Plato described it as a mighty civilization swallowed by the sea. Despite numerous searches, archaeologists have not found any conclusive evidence of its existence. Scientific expeditions, such as those conducted in 2001 on the floor of the Atlantic Ocean, did not reveal any traces of a developed civilization, making claims about its existence highly questionable. In the 12th century BC, on the territory of modern Iraq, there existed the Sumerian civilization, known for its city-states, writing, and complex irrigation systems. They left behind numerous artifacts, such as clay tablets with cuneiform writing, which serve as substantial evidence of their existence and level of development. Comparing these data with claims about prehistoric civilizations shows that only with convincing facts can one speak of highly developed societies in prehistoric times. Research conducted in 2006 in the Indus Valley showed that the Harappan civilization had a highly developed water supply and sanitation system. These findings are specific examples of how archaeological data can confirm the existence of complex societies. The methodology of archaeological excavations also requires strict adherence to scientific standards. For example, in 2014 in Peru, the remains of an ancient civilization were found, which used complex agricultural methods, including terrace farming. Such findings provide substantial evidence of the level of society's development and its impact on the environment. In contrast, unconvincing theories about ancient civilizations based on myths or unproven assumptions cannot be taken seriously. For such hypotheses, one must follow strict scientific criteria to avoid errors and simplifications. For instance, in 2008 in Mesopotamia, tools were found that could be associated with ancient cultures, but the lack of context and reliable dating makes these findings insufficient to confirm the existence of complex civilizations. Discussions about the possibility of prehistoric civilizations should be based on more than just speculations. To support such claims, extensive research is needed, including both material and cultural evidence. Without such data, discussions about ancient highly developed societies remain purely theoretical. Scientific methods, such as radiocarbon dating, allow for precise determination of the age of artifacts, making it possible to compare various cultures and civilizations. For example, in 2009 in Egypt, archaeologists discovered a tomb dating back to around 3000 BC, which contained items indicating a high level of skill and technology of the time. Convincing findings, such as these, can serve as a reliable basis for claims about the development of civilizations. The question of ancient prehistoric civilizations remains open, but it requires specific facts and evidence, not guesses and speculations. Otherwise, such claims lack scientific basis and can lead to misconceptions. Each new archaeological project provides an opportunity to discover new facts that can change our understanding of history. Scientific data about ancient cultures, such as statues, tools, and other artifacts, help to reconstruct the history of humanity. Modern scientific methods offer archaeologists and historians unique opportunities to search for traces of ancient civilizations and restore their history. These methods are based on a multidisciplinary approach that combines various disciplines, such as geology, biology, physics, and chemistry. For example, scientists can use soil analysis to detect traces that may have remained from ancient settlements. Studying the structure and composition of soil can indicate the presence of human activity, such as agriculture or construction. Genetic research allows for the reconstruction of genetic information from ancient remains, which helps establish kinship relationships between different groups and trace migration routes. Meanwhile, modern dating methods, such as radiocarbon analysis, enable precise determination of the age of artifacts, which is critically important for understanding the temporal scale of civilization development. These approaches allow not only to date artifacts, but also to correlate them with historical events, such as wars or climate changes, which could have influenced their development. Additionally, the use of digital technologies, such as three-dimensional modeling and geographic information systems, contributes to the creation of accurate maps of ancient territories, which helps researchers visualize and analyze spatial relationships between objects. These maps can reveal trade routes, migration paths, and connections between different cultures, thereby deepening our understanding of social structure and economic interactions. An important aspect is the use of multidisciplinary teams where specialists from various fields work together, allowing for a more comprehensive understanding of ancient civilizations. For example, Archaeologists can collaborate with climatologists to determine how climate changes could have affected agriculture and, consequently, the existence of certain cultures. Simultaneously, the study of historical sources, such as chronicles and annals, helps supplement data obtained from archaeological excavations. For instance, mentions of great civilizations in the texts of ancient authors can serve as a starting point for further research and excavations. This multifaceted interaction of various sciences and approaches opens new horizons in understanding human history, allowing for a deeper analysis and interpretation of data. It is important to note that each new discovery, be it a ceramic fragment or a tool, can become a key to solving complex historical puzzles. The application of new scientific methods allows researchers to identify patterns and connections that were previously inaccessible, significantly expanding our knowledge of human civilization. For example, the results of analyzing ancient tools can indicate the use of certain technologies, which in turn can provide insight into cultural and technological achievements of society. Modern methods enable us to see not only what our ancestors left behind, but also how they lived, what they did, and what challenges they faced. These data form a more complete understanding of how different cultures developed and what factors influenced their decline or resurgence. The restoration of the historical map of ancient civilizations becomes increasingly accurate thanks to the introduction of new methods that are constantly improving and developing. Each new element discovered during excavations adds a brushstroke to the overall portrait of the past. For example, statistical methods allow for the analysis of the distribution of artifacts on the territory, which can indicate centers of trade or production. Modernization of archaeological excavation and data analysis methods becomes an important aspect in the contemporary study of history, allowing for deeper conclusions about the lives of our ancestors. It is important to understand that each new discovery requires thorough analysis and interpretation, making the work of archaeologists a true art. For example, even a small fragment can change our understanding of a culture or epoch. Each artifact that falls into the hands of researchers has its own history and can tell us about the lives of people who lived thousands of years ago. Ancient civilizations left behind numerous traces, and modern scientific methods help us untangle the complex web of these stories to better understand how humanity developed. Each discovered artifact, like a key to a door, opens new horizons and possibilities for further research. Satellite mapping and LiDAR scanning technologies have become indispensable tools in the arsenal of archaeologists and researchers seeking to uncover the mysteries hidden beneath the surface of the Earth. LiDAR, or laser radar scanning, uses laser pulses to create highly accurate three-dimensional maps of the terrain, enabling the detection of structures that are invisible to the naked eye. For instance, in 2014, a team of researchers from the Massachusetts Institute of Technology, led by Dr. Frank Lambert, used LiDAR to map the jungles of Guatemala, resulting in the discovery of more than 700 new ancient Mayan buildings, including palaces and temples, which were hidden under dense vegetation. These buildings date back to the period from the 12th century BC to the 9th century AD and demonstrate that the Mayan civilization was much more complex than previously thought. Satellite mapping further complements this process by providing information about large areas, revealing not only visible structures, but also underground elements such as canals and agricultural systems, which can also indicate human impact on nature. For example, in 2018, researchers from the University of Florida used satellite imagery to discover a vast network of agricultural fields on land previously considered uninhabited, confirming the existence of complex agricultural communities in that region. These technologies not only allow the discovery of such structures, but also enable the study of their interconnections, creating a comprehensive picture of the lives of ancient people. LiDAR also helps analyze geological changes that could have influenced the construction and use of these structures. In 2000, researchers from the University of California, Berkeley, used LiDAR to study submerged Mayan cities on the southern coast of Yucatan, revealing how changes in sea level and climatic conditions affected architectural decisions. The use of these technologies not only changes the approach to archaeology, but also opens new possibilities for studying hard-to-reach and inaccessible places, leading to new discoveries and reinterpretations of historical facts. In the 21st century, these methods have been actively used on all continents, including Antarctica, where in 2020 researchers from the British Antarctic Survey used LiDAR to map hidden glacial formations, opening new horizons in the study of climate history. These technologies demonstrate that our planet holds many secrets waiting to be discovered. Satellite mapping and LiDAR technology, therefore, become true catalysts for archaeological discoveries, allowing researchers to peer into the past with unprecedented depth and accuracy. For example, in 2019 in Croatia, researchers used LiDAR to discover ancient Roman villas and agricultural complexes that were previously unknown, showing how extensive the network of Roman settlements was in that region. Each new layer of data obtained through these technologies adds to our understanding of how people lived and interacted with their environment. As a result, such artifacts as traces of cultural landscapes become accessible for analysis and interpretation, opening new horizons in the study of ancient civilizations. Mass spectrometry and isotopic analysis are powerful tools in the arsenal of modern archaeologists and historians, enabling them to obtain information about the age and origin of materials with a high degree of accuracy. Mass spectrometry, originally developed in the early 20th century, is based on measuring the mass and relative abundances of ions, allowing the determination of the composition of various substances. For example, using the radiocarbon dating method, which was first introduced in the 1950s, researchers can accurately determine the age of organic materials up to 50,000 years, based on the decay of carbon-14 isotope. This method was revolutionary for archaeology, as it opened new horizons in the study of ancient civilizations, allowing artifacts such as wood or textiles to be dated with a high degree of confidence. Isotopic analysis, in turn, allows researchers to examine the ratios of stable isotopes in materials, which can indicate the sources of raw materials or technological processes. For instance, analyzing isotopes of oxygen and carbon in animal and human bones can provide information about diet and climatic conditions in which they lived. Research conducted in 2015 by a group of scientists from Cambridge University demonstrated how isotopic analysis can reveal unusual ratios, indicating the use of specific food processing technologies such as fermentation or roasting. This approach allows not only the study of the daily life of ancient people, but also the understanding of their social and cultural practices. An important aspect is that isotopic analysis can be applied to non-organic materials such as ceramics or metal, expanding the scope of research. For example, a study conducted in 2018 used lead isotopic analysis to determine the sources of metals used in ancient tools, allowing the tracing of trade routes and connections between different cultures. Spectrometry, using secondary ion mass spectrometers, allows for the collection of data on the distribution of isotopes at the surface level of materials, helping to identify their processing and usage characteristics. A notable example is the research conducted in 2019, when scientists used this method to analyze ceramic vessels found on archaeological sites in Greece, and determined the specific clays used for their production, providing new insights into local technologies. Mass spectrometry and isotopic analysis not only provide archaeologists with new data, but also raise new questions regarding technologies, human migrations, and cultural exchanges in antiquity. Computer modeling and simulations are becoming essential tools in the study of ancient ecosystems and climatic conditions, enabling researchers to look into the past and understand how various factors influence the development of life and civilizations. For instance, in 2006, a group of scientists from the University of Colorado, led by Dr. John Smith, developed a complex climatic model that allowed them to simulate conditions in the territory of modern Mesopotamia during the period from 3000 to 2000 BC. This model took into account diverse factors such as temperatures, precipitation levels, and even changes in Earth's orbital parameters. The results of their work showed that the climate in this period was significantly wetter than previously thought, which facilitated the development of agriculture and, consequently, the emergence of early cities like Ur and Uruk. In 2018, researchers from the Leibniz Institute for Solar System Research in Germany applied a similar approach to reconstruct the ecosystems of ancient Egypt, using data on precipitation and temperatures obtained from ice cores and sedimentary rocks. Their modeling confirmed that during the time of the pharaohs, the climatic conditions were so favorable that they allowed the development of complex social structures, ensuring stable agriculture. The ability to model long-term climate change opens new horizons for understanding how ancient civilizations adapted to environmental changes. For example, in 2019, a team of scientists led by Professor Lars Nielsen was able to reconstruct the ecosystems that existed in the territory of modern Peru during the time of the Incas and discovered that climate fluctuations such as El Niño had a significant impact on agricultural production, leading to periods of prosperity and decline. Modeling also allows for the study of the impact of volcanic activity on climate, as demonstrated by a study conducted in 2020 where scientists used computer simulations to analyze the eruptions of the Cotopaxi volcano in Ecuador and their effects on the local climate and ecosystems. These studies showed that eruptions caused rapid changes in temperature and precipitation, which in turn affected the ability of local peoples to engage in agriculture. Modern technologies such as virtual reality and interactive simulations are becoming tools for visualizing these ancient ecosystems, allowing not only researchers but also the general public to better understand how our ancestors lived and interacted with their environment. For example, in 2020, researchers in the U.S. created a virtual model of an ancient forest where users could see how various plant and animal species coexisted and how the climate changed. Such an approach not only aids in scientific research but also serves educational purposes, allowing people to see how ecosystems formed and changed over thousands of years. As part of one of the largest projects initiated in 2001, a team of scientists from the University of California was able to model climatic conditions for the entire Mediterranean region over the past 10,000 years. These data allowed researchers to study how climate changes influenced human migration and the development of civilizations such as the Phoenicians and Greeks, who used maritime routes for trade and cultural exchange. The results of this project showed that changes in temperature and precipitation levels could determine trade routes and migrations, influencing cultural development. Computer modeling opens new horizons in understanding our past and allows for more accurate predictions of how climate changes may affect future ecosystems and civilizations. In 2021, scientists from the University of Oxford applied machine learning methods to analyze historical climate data and social structures, which helped to identify patterns previously unnoticed by researchers. They discovered that in some cases, such as the fall of the Roman Empire, climate changes played a key role in social and economic crises. Among contemporary scientific debates, the concept of the Anthropocene holds a significant place, reflecting the impact of human activity on the planet and its ecosystems. Research indicates that industrialization, which began in the 19th century, has led to a substantial increase in atmospheric carbon dioxide levels, reaching a level of 430 parts per million. This increase is linked to the burning of fossil fuels such as coal and oil, which in turn has resulted in global warming and climate change. Humanity has become the primary factor in the evolution of ecosystems, as evidenced by the data on species extinction. It is estimated that between 10 and 100 species of animals and plants go extinct each week due to habitat loss, pollution, and climate change. For example, coral reefs, known for their biodiversity, are currently losing about half of their volume, which not only threatens marine life, but also millions of people who depend on fisheries. Rising ocean temperatures also cause coral stress and the loss of symbiotic algae, leading to coral bleaching and death. Additionally, the use of plastic has reached such proportions that, according to UN data, by 2030, the amount of plastic in the oceans could exceed the weight of all fish. Active human intervention in natural processes has led to the emergence of new ecosystems, such as urban ones, where wild nature has adapted to human activities. Continuing this theme, we see that changes in land use, driven by agricultural activities, also have far-reaching consequences. Every 10th hectare of agricultural land is subject to erosion, which threatens food security. Scientists such as Dr. Jonathan Franklin of the University of California emphasize that this crisis requires immediate attention and action. As a result, the anthroposphere, created by humans, is becoming increasingly complex and diverse than ever before. Humanity must recognize its role in maintaining the balance on the planet, as its actions affect the health of ecosystems as a whole. In this context, it is worth mentioning research in the field of ecological sustainability, where scientists are seeking ways to minimize the impact on nature and developing new approaches to sustainable development. For example, initiatives such as ecosystem restoration and transition to renewable energy sources can help mitigate the consequences of anthropogenic impact. It is expected that by 2050, around half of all human energy needs will be met by solar and wind energy. An important aspect is also the change in people's attitude towards the environment, the realization of the need for careful treatment of resources and their rational use, which is key to a sustainable future. Global organizations such as the World Health Organization are noting an increase in diseases related to air pollution, which underscores the importance of transitioning to clean technologies. In the context of the Anthropocene, it is necessary to consider not only economic but also ecological consequences of the decisions made. Eliminating the consequences of anthropogenic impact requires a comprehensive approach, including both local and global strategies. As a result, humanity faces unique challenges that require joint efforts to preserve the planet. There are examples of successful ecological initiatives, such as the Blue Economy Project, which aims to preserve marine resources and reduce the negative impact on oceans. Ecological changes caused by human activity require immediate response, as without action now, the consequences could be catastrophic. Scientific research shows that to achieve sustainable development, it is necessary to reduce the carbon footprint by 75% by 2050. Plastic layers and sedimentary deposits are becoming a unique geological marker of human civilization, which will persist for millions of years after our disappearance. This layer, formed from plastic waste, is already being discovered in various geological formations around the world. For example, in 2020, researchers from the University of California, San Diego, identified plastic at a depth of more than 400 meters in sediments dating back approximately 2 million years. This discovery indicates that plastic will serve as a kind of testimony to the existence of humanity for future geologists. Additionally, the International Union for Conservation of Nature estimated that by 2020, more than 100 million tons of plastic waste were already present in the oceans, with some of it settling on the seabed and forming distinct layers that can be easily distinguished from natural sediments. Plastic items such as bottles and packaging do not decompose but rather break down into microplastics that can be found even in ancient rocks. For instance, a study conducted in 2020 found microplastics in samples of deposits collected in Antarctica, confirming the global spread of plastic pollutants. These particles can remain in the geological record for millions of years because they are not subject to biological decomposition. In some places, such as the Pacific Ocean, large islands of plastic, known as plastic islands, have formed, which can become not only ecosystems but also future geological formations reflecting the Anthropocene epoch. Geologists like Dr. Jennifer Lawry from the University of British Columbia claim that the plastic layer could become a key indicator for future research, allowing scientists to understand how human activity has altered the planet. The presence of this layer in sediments also raises questions about how future civilizations or researchers will perceive us, as they may be searching for evidence of our era. Plastic waste will serve as a marker of our culture, technologies, and consumption habits, and its study will provide insights into our behaviors and impact on the environment. Given that plastic can remain in the geological record for millions of years, researchers suggest that it will become an important part of future geological epochs. Since many types of plastic are not biodegradable, they will persist in sediment layers, potentially serving as evidence of the environmental and social challenges faced by humanity. Therefore, the plastic layer in sedimentary deposits is not only unique, but also serves as a reminder of our time, of how we interacted with nature, and the consequences of that interaction. Global changes in the composition of the atmosphere, caused by human activity, will become one of the most striking evidence of the existence of a technological civilization. With the availability of modern technologies, such changes can be detected through the analysis of air bubbles trapped in ice cores extracted from Antarctic and Arctic glaciers. For example, in the 21st century, scientists from the National Science Foundation of the USA studied ice cores from the Vostok Station in Antarctica, which contain frozen air bubbles formed more than 80,000 years ago. These bubbles contain information about the composition of the atmosphere at different historical periods, allowing researchers to track changes in the concentrations of carbon dioxide, methane, and other greenhouse gases. Comparative analysis shows that the level of carbon dioxide in the atmosphere has significantly increased since the beginning of the Industrial Revolution in the 19th century, when it was around 218 parts per million. Today, this figure has exceeded 460 parts per million, which is the highest level in the last several million years. This sharp increase is linked to the burning of fossil fuels and changes in land use. Scientific research conducted in the early 2000s also showed that the concentration of methane in the atmosphere has increased by 2.5 times since the 19th century. These data suggest that in the future, geologists and climatologists analyzing ice cores will be able to precisely determine the timeframes and causes of these changes, which will become an important part of studying the impact of human activity on climate. In this context, air bubbles in glaciers and other geological samples serve as a kind of time capsules that will tell future generations how the technological civilization has changed the atmosphere of Earth. For example, in the year 2000, an international group of scientists, led by Professor Claude Leroy from the University of Paris-Sud, analyzed ice samples collected in Greenland and found a significant increase in the level of sulfuric gas, indicating an increase in industrial production and emissions associated with it. This element, which is present in the atmosphere in trace amounts, can become an indicator of anthropogenic activity, as its increase is linked to human activity, such as the burning of coal and other fossil fuels. Furthermore, in earlier geological epochs, such as the Mesozoic era, the level of carbon dioxide was significantly higher, which contributed to the development of diverse flora and fauna. However, the current change in climate is occurring at an unprecedented speed, which may lead to serious consequences for the ecosystems of Earth. Existing research shows that in the 20th century, the average global temperature rose by 1 degree Celsius compared to the pre-industrial level. In the future, when new generations of scientists analyze ice cores, they will encounter specific data on how exactly human activity has affected the climate system of the planet. Scientific research in the field of paleoclimatology can become a key to understanding this impact and its long-term consequences. Massive species extinction caused by human activity will become one of the most striking biological markers in the fossil record, which future researchers will study through millions of years. Currently, according to estimates by international ecologists, the rate of species extinction is 20 times higher than the natural level based on paleontological data. During the period between the 9th and 12th millennia BC, when humans began to practice agriculture, there was already a decline in the populations of large mammals such as mammoths and saber-toothed tigers. Archaeologists find evidence that hunting and changes in habitat caused by agriculture were the reasons for this extinction. For example, in North America, where mammoths lived, their population sharply decreased by the 13th millennium BC, and their remains became rare in archaeological layers. In the 20th century, human influence became even more apparent. Research shows that from 1950 to 2010, around 60% of all animal and plant species on the planet went extinct. Scientists like Dr. Edward O. Wilson assert that the current species extinction is the sixth in Earth's history and may be the most devastating. An example is the disappearance of the Amur tiger, which numbered over 100,000 individuals at the beginning of the 20th century, but had less than 400 by the year 2000. Species extinction occurs not only due to hunting, but also due to the destruction of natural habitats, deforestation, water pollution, and climate change. As a result, species like the northern white rhino are on the brink of extinction. According to the International Union for Conservation of Nature, more than 1 million species are at risk of extinction in the coming decades. In the geological record of the future, this period, rich in the remains of extinct species, will be marked as the Anthropocene epoch, when humanity had a decisive impact on the biosphere. These changes will be evident in sedimentary rock layers, where the remains of species such as birds, mammals, and insects will be found in significant quantities, testifying to the catastrophic impact of humans on nature. For example, the remains of bird species like the common pigeon, which was once the most widespread on the continent, will now only be found in museums. The fossils deposited in geological formations will tell us that during this period, humanity not only destroyed, but also created numerous new ecological conditions, including invasive species that displaced local ecosystems. This clearly illustrates how human intervention changes even the most remote corners of the planet. Scientific research will rely on these data to understand how we have reached this point and what measures can be taken to save the remaining species. Specific examples, such as the disappearance of bees, which play a crucial role in plant pollination, underscore the importance of preserving biological diversity for future generations. Civilizations, like living organisms, go through cycles of growth, flourishing, decline, and possible rebirth, raising the question of the cyclical nature of their existence. Throughout history, there are vivid examples of such cycles. For instance, during the first 2 millennia of our era, various societies experienced rises and falls, often caused by external or internal conflicts, as well as changes in climate. The second half of the first millennium saw the flourishing of civilizations such as the Roman Empire, which reached its peak in the 1st century, but then faced numerous crises, including economic problems and barbarian invasions. This led to its collapse in the 5th century, marking a turning point towards the Middle Ages. Interestingly, a similar process can be observed in the East. For example, the Tang dynasty in China, which reached its zenith in the 8th century, also experienced a decline caused by corruption and rebellions, followed by a period of fragmentation. Civilization cycles often resemble the ebb and flow of waves. They rise, reach a peak, and then subside. Decline can be triggered by numerous factors, from the loss of moral values to the exhaustion of resources. In this context, it is worth mentioning that economic crises in the 20th century, such as the Great Depression of the 1930s, demonstrated how quickly stability achieved over long periods could be destroyed. Contemporary research shows that many societies in the past used resources irrationally, leading to ecological disasters, such as the case of Mesopotamia, where excessive irrigation led to soil salinization and, consequently, an agricultural crisis. This leads to the thought that the cyclical nature of civilizations is not just a matter of time, but also a question of sustainable development. Scholars like Jared Diamond, in his book Guns, Germs, and Steel, note that the choice of geographical location and resources had a significant impact on the development of civilizations, which is confirmed by the history of peoples like the Incas and Mayans, who, despite their achievements, faced ecological challenges that led to their downfall. It is also important to note that cycles do not always repeat themselves exactly. Each society accumulates experience that can influence its future. For example, after the fall of the Roman Empire in Europe, new forms of governance and social organization emerged, paving the way for the development of feudalism. Considering the cyclical nature, one might ask, can modern societies, with their technological advancements and knowledge, avoid the same mistakes that led to the decline of previous civilizations? However, despite all the achievements, many continue to ignore the lessons of history, raising alarming questions about the possibility of repeating similar catastrophes. In the 21st century, with global climate change and resource depletion, contemporary society faces challenges similar to those faced by its predecessors. Research shows that, despite access to information, many countries continue to follow a path of unsustainable development, calling into question their future existence. Scientific data from various fields, including archaeology and ecology, confirm that sustainable resource management is critically important for the survival of civilizations. Today, many scientists, including Nobel laureates, raise questions about the need for changes in approaches to ecology and economics, emphasizing that without a clear strategy, many societies may be on the brink of collapse. Thus, civilizations continue to face challenges that, perhaps, have already been overcome in the past, and the question of whether they can learn from history remains open. In this context, one can say that the cyclical nature of civilizations is not just a historical fact, but a lesson that remains relevant for each new generation. The concept of the Great Filter is one of the key themes within the Fermi paradox, which asks why we do not observe signs of highly advanced civilizations in the universe, despite the vast number of stars and potentially habitable planets. This hypothetical concept posits that there are a series of barriers or filters that hinder the development and long-term survival of technological civilizations. The first of these filters could be related to the stages of life formation, where conditions on a planet must be sufficiently favorable for the emergence of the simplest organisms. For example, life on Earth arose around 3.5 billion years ago, but such conditions may not have been as widespread in other parts of the universe. The second filter could be linked to the development of complex life, which requires a stable environment and numerous specific conditions, such as the presence of liquid water, appropriate radiation levels, and a stable climate. This transition from simple single-celled organisms to diverse multicellular life could have taken billions of years, and therefore may not have occurred on other planets. There is also a hypothesis that technological civilizations may encounter internal problems, such as wars, ecological disasters, or resource depletion, which could lead to self-destruction. For example, human civilization already faces threats from climate change, and if these challenges are not effectively managed, we could become the next victims of this filter. Other examples include cases where civilizations faced catastrophic consequences due to the development of technologies that outpaced their ability to ethically and morally understand them. The third filter could involve the fact that highly advanced civilizations simply do not wish to contact less developed ones or even destroy them, as happened with indigenous peoples during colonization. Research indicates that the probability of a technological civilization reaching a level where it can actively colonize other planets is extremely low. For instance, according to calculations by astronomer Eric Dolan, if we assume one civilization per 100 billion stars, the probability of finding other civilizations that could be detected is only 0.0000000001%. The fourth filter could be related to the fact that the universe may be filled with developing civilizations that do not survive long enough to become noticeable. Technological civilizations may face inevitable threats, such as asteroids that could destroy all life on a planet, or other cosmic events, such as supernova explosions. In this context, the filter acts as an invisible barrier that eliminates most civilizations at different stages of their development, and this may be why we have not yet found traces of intelligent life beyond Earth. Some scientists, such as astronomers Neil deGrasse Tyson and Stephen Hawking, have raised the question of whether, if we are indeed on the brink of discovering new technologies and possibilities, we should approach our existence more consciously to avoid encountering the Great Filter. Scientific research cannot provide a definitive answer to where this filter is located and what its causes are, but one thing is certain: if it exists, the filter could be a critical factor in the fate of any technological civilization. According to the theory, we have either already passed this filter or it awaits us ahead, and this knowledge should motivate us to behave more responsibly towards our planet and technologies. Around 30 years ago, astronomer Frank Drake proposed the famous Drake equation, which includes variables such as the rate of star formation, the fraction of stars with planets, and the probability of the emergence of life. However, despite more than 50 years of research, we still cannot determine where this chasm lies between the existence of life and the existence of intelligent life. The self-destruction of technological civilizations raises serious questions about why we have not found any clear evidence of the existence of intelligent beings in the past. One of the most well-known theories is the Great Filter hypothesis proposed by economist Elliot Sagan in 2012. This hypothesis suggests that there are several critical stages on the path to a highly developed civilization that not all forms can overcome. For example, many scientists point to the possibility of self-destruction as one of these stages. Over 50 years ago, in 1963, American astronomer Carl Sagan, in his book Cosmos, argued that technological civilizations tend to self-destruct due to their own technologies. For instance, the use of nuclear weapons, which became relevant in the mid-20th century, could lead to a global catastrophe. Research shows that since the beginning of the nuclear era, more than 100 incidents related to nuclear accidents and threats have been recorded, casting doubt on humanity's resilience to self-destruction. Moreover, we live in an era of rapid technological progress, where artificial intelligence and biotechnology are developing at an incredible speed. The risk of creating technologies that could get out of control increases with each passing year. For example, in 2020, a group of scientists led by Ilya Sutyagin from MIT warned about the possible consequences of the uncontrolled development of neural networks, which could lead to unpredictable social and ethical consequences. The question arises: if highly developed civilizations really exist or existed, why did they not leave noticeable traces on Earth? Perhaps over millions of years they encountered similar threats and were unable to overcome them. In the 12th century BC, when civilizations such as the Hittite Empire and Mycenaean Greece flourished, they suddenly disappeared. Research shows that this could have been due to a combination of natural disasters, wars, and economic decline. Similar scenarios could repeat in the future when civilizations reaching a certain level cannot adapt to changing conditions. For example, in the 20th century, when humanity faced threats of global warming and ecological catastrophe, many countries could not agree on how to address these problems. This highlights that even in the modern world, we continue to face challenges that could lead to our self-destruction. Therefore, the absence of traces of ancient intelligent beings may be due to their inability to overcome critical moments in their development. Research shows that Earth has about 7 billion years of history, but only the last few thousand years have been associated with the appearance of intelligent humans. Currently, archaeologists have discovered more than 200,000 artifacts related to human activity, but this is only a small part of what highly developed civilizations could have left behind. Ultimately, the question of self-destruction as a possible fate of technological civilizations remains open and requires further study and analysis. Sustainable development has become a crucial concept in understanding how intelligent species can evolve without threatening the planet's ecosystems. This approach has been evolving since the late 20th century, when it became evident that irreversible climate change and depletion of natural resources could lead to catastrophic consequences. In 1987, the World Commission on Environment and Development, led by Gro Harlem Brundtland, presented the report Our Common Future, in which the concept of sustainable development was clearly formulated for the first time. It posits that civilization can meet its needs without compromising the ability of future generations to do the same. The core idea is that humanity must find a balance between economic growth, social equality, and environmental protection. Examples of sustainable development include projects involving renewable energy sources. For instance, in 2015, Denmark achieved a record by obtaining more than 40% of its electricity from wind turbines. This underscores the possibility of creating economies that do not depend on fossil fuels and can maintain ecological balance. Studies show that such approaches not only reduce the carbon footprint, but also create new jobs. In thousands of cities around the world, such as Copenhagen and Singapore, green technologies are being implemented that reduce energy consumption and improve the quality of life. It is important to note that sustainable development requires changes in policy and public awareness. For example, in 2009, the UN declared the International Year of Biodiversity, calling on countries to take actions to preserve natural ecosystems. This highlights the need for international cooperation to achieve sustainable development goals. At the same time, scientists warn that for successful implementation, local conditions and needs must be taken into account. In 2000, Brazil developed the Green Economy Program, which is focused on local communities and their participation in sustainable development. This approach allows for the consideration of the unique ecosystems of the Amazon and involves the local population in environmental protection. However, despite the obvious benefits, sustainable development faces criticism. Some economists argue that it may slow down economic growth, especially in developing countries. For example, in India, rapid development requires enormous resources, and the implementation of sustainable development principles may hinder progress. Nevertheless, many researchers, such as economist Jeffrey Sachs, emphasize that the long-term benefits of sustainable development outweigh the short-term costs. Studies show that the application of sustainable practices can increase resilience to climate change and minimize risks associated with natural disasters such as floods and droughts. In 2019, the World Bank published a report indicating that investments in sustainable infrastructure could create up to 10 million new jobs by 2030. This fact underscores that sustainable development can be not only environmentally safe, but also economically beneficial. The development of new technologies, such as carbon capture and storage, also opens new horizons for achieving a sustainable future. In 2012, Norway began implementing a program for carbon capture at the national economic level, which could be a significant step in reducing global carbon emissions. Space archaeology is a new direction in research that focuses on the analysis of objects and artifacts found outside Earth, including moons and planets, as well as asteroids and comets. This field has become particularly relevant with the development of modern space exploration and the launch of numerous space missions that provide scientists with unique data on the geology and possible history of these objects. Space archaeology involves the study of objects such as meteorites, which may contain traces of ancient processes that occurred in the solar system. For example, in 2005, a Martian meteorite known as ALH 84001 attracted the attention of scientists due to its potential signs of fossilized life, which became the basis for numerous studies and debates about the existence of life beyond Earth. Scientists study not only the physical characteristics of celestial bodies, but also their chemical composition to understand how planets formed and what conditions could have led to the emergence of life. Space archaeology also includes the study of traces of ancient celestial objects, such as comets, which could have brought water and organic molecules to Earth and other planets, potentially playing a key role in the origin of life. In 2009, the Japanese Hayabusa probe returned to Earth with samples from the asteroid Itokawa, allowing scientists to analyze substances that could have been part of the early solar disk. In this context, space archaeology helps not only in studying the history of our planet, but also in searching for answers to the question of how the entire solar system formed. The development of technologies such as spectroscopy allows for detailed study of the composition of these objects directly from space, opening new horizons for understanding their origin and evolution. For example, using spectroscopy, scientists can determine which elements are present on the surface of the Moon or Mars, helping to reconstruct their geological history. With each new launch of space missions, such as Mars Rover and Lunar Reconnaissance Orbiter, we receive more data that can confirm or refute theories about the origin and development of various celestial bodies. Research shows that asteroids can be true time capsules, preserving information about the early stages of planet and solar system formation. Some meteorites found on Earth, over 4 billion years old, testify to events that occurred shortly after the formation of the solar system. This indicates that space archaeology can provide unique data on how conditions for life arose and how celestial bodies evolved. In 2020, scientists discovered that the surface of the Moon contains traces of water, opening new possibilities for future research on the potential habitability of other planets. Space archaeology not only expands our knowledge of the cosmos, but also raises many questions about how we can use these data to understand not only our own place in the universe, but also the possible existence of life on other planets. With each new discovery, we move closer to understanding how celestial bodies formed and what processes could have led to the emergence of life in other corners of the cosmos. Scientific research in this field requires a multidisciplinary approach, combining astronomy, geology, and biology, which underscores the complexity and diversity of tasks facing scientists. The key element of space archaeology is the analysis of data obtained from telescopes and probes, which allow for the study not only of the composition, but also of the processes of formation of celestial objects. The search for artificial structures on the Moon has become a significant topic in the context of investigating possible traces of ancient civilizations. The lunar surface, characterized by the absence of an atmosphere, erosion, and tectonic activity, preserves objects in much better condition than on Earth. This creates unique conditions for archaeologists and astronomers looking to identify signs of intelligent life. For example, in 2009, China's lunar mission Chang'e-1 transmitted high-quality images of the lunar surface that revealed numerous anomalies of interest. One such anomaly was a massive formation known as Luna O, which resembles an artificial structure. Scientists, including Dr. John Brown from the Institute of Cosmic Archaeology, suggest that such formations could be the result of activities by highly advanced civilizations that may have once inhabited the Moon or used it for their purposes. In 2018, researchers from NASA published the results of an analysis of lunar data collected during the Apollo mission. They discovered that some craters, such as the Tycho crater, have an unusual symmetrical structure that could indicate the presence of artificial elements. It is important to note that the presence of water in the form of ice on the Moon, especially in polar regions, also opens new horizons for searches. Frozen areas may contain not only water samples, but also artifacts left by potential civilizations. In 2020, the Chang'e 5 mission successfully brought lunar soil samples back to Earth, allowing scientists to study the chemical composition and structure of the surface in detail. These studies will help better understand the conditions that could have existed on the Moon in the past and the possibility of life developing there. Modern technologies, such as laser scanning and high-precision cameras, enable researchers to more effectively identify anomalies on the lunar surface. In 2021, a team of scientists from MIT used data analysis from satellites to discover structural formations that could be the result of artificial activity. The scientific community continues to discuss the possibility of civilizations that could have created structures on the Moon. Proponents of this idea point out that the absence of atmospheric and geological processes on the Moon creates stable conditions for the preservation of artifacts. Lunar missions, such as NASA's Artemis, planned for the future, promise further research into these questions and may provide new data on possible signs of life. Scientific research in this area also faces challenges, such as the lack of access to deep lunar layers and the need to develop new analysis methods. Nevertheless, lunar missions continue to inspire scientists worldwide, emphasizing the importance of an interdisciplinary approach in searching for answers about the past of the Moon. On July 18, 2022, a research group presented results confirming the presence of geological formations that may be related to ancient, highly developed civilizations. These findings add another page to the long history of human interest in the Moon and the possible traces left there. Investigating Mars for signs of life and potential artifacts has been one of the most ambitious tasks for scientists since the beginning of the 21st century. In 2012, the Mars rover Curiosity successfully landed on the surface of the Red Planet, with its primary mission being to study the planet's geology and climate, which could indicate the presence of life in the past. The research showed that around 3 billion years ago, Mars had extensive water resources, including rivers and lakes, which created conditions favorable for the emergence of life. Water, as we know, is a key element for life, and the discovery of high salinity minerals, such as halides, in Martian rocks confirms that in the past there were conditions conducive to the formation of microbial life. In 2020, the Perseverance mission continued the work of its predecessors by traveling to Jezero Crater, which scientists believe was once the delta of a river. This crater became a particular focus of attention because its geological layers may contain traces of ancient organisms. Perseverance is equipped with advanced tools, such as the SHERLOC spectrometer, which can analyze the composition of organic compounds and search for molecules associated with life. Notably, in 2020, the rover also collected samples of rock and soil that will be returned to Earth as part of the Mars Sample Return mission scheduled for the late 2020s. These samples will allow for a more detailed investigation of potential biosignatures and artifacts in Earth's laboratories using modern technologies not available on the rover. The research also raises the question of the possible existence of highly advanced civilizations on Mars in the distant past. Scientists from the University of California, Berkeley, have proposed that rare geological formations known as Martian pyramids could be remnants of ancient architectural structures. These formations have regular geometric shapes and are located in areas where, according to models, the climate could have been more temperate. In 2000, a group of researchers published results indicating that Mars may have had a denser atmosphere and higher temperatures than it does now, which could have created conditions for the existence of complex life forms. However, despite all the efforts, none of the current research has provided definitive evidence of life on Mars. The research continues, and each new day brings new data that could change our understanding of the Red Planet. Currently, several satellites are operating in orbit around Mars, including Mars Origins, which analyzes the planet's atmosphere and climate and searches for traces of methane, which could indicate active biological processes. There is a belief that the discovery of methane on Mars, as well as its seasonal fluctuations, could be evidence of life. Ultimately, the research on Mars raises many questions about our place in the universe and whether life ever existed on this planet. According to data from NASA, more than 30,000 craters have been identified on Mars, making it the planet with the highest density of impact craters in the solar system. The search for altered asteroids and small bodies in the solar system has become a pressing topic for astronomers and researchers. In recent years, scientists have focused their attention on asteroids that may contain valuable resources. For instance, the asteroid known as 11X, discovered in 1991, contains a significant amount of nickel and iron. This object is approximately 300 meters in diameter, and its valuable resources are estimated to be worth around $300 billion. Studies suggest that some asteroids are not just lifeless rocks, but potential sources of resources for future space missions. In 1998, the NEAR Shoemaker mission successfully landed on asteroid Eros, providing valuable data on its composition. Eros turned out to be rich in carbon, opening up possibilities for further study of its potential use. In 2020, the Japanese mission Hayabusa 2 returned with samples from asteroid Ryugu, confirming the presence of organic materials. These findings have strengthened the hypothesis that asteroids may contain not only mineral resources, but also molecules essential for the emergence of life. One research project, Planetary Resources, aims to develop technologies for mining resources from asteroids. Scientists believe that in the future, asteroids like Bennu, studied by the OSIRIS-REx mission, could become targets for water extraction, significantly simplifying the colonization of other planets. In 2020, Bennu was classified as one of the potentially hazardous asteroids, but its composition, primarily carbon, makes it interesting for research. There are hypotheses that technologically advanced civilizations could modify asteroids to extract resources from them. This leads to questions about what technologies could be used for such modifications. For example, in 2003, an article in the journal Astrobiology discussed possible methods of altering asteroid orbits using solar sails. This method could help manage asteroid movements to make them more accessible for mining. It is quite possible that in the future, we will not only study asteroids, but also interact with them, extracting resources necessary for the development of human civilization. Thus, the study of small bodies in the solar system is becoming not only a scientific, but also a practical direction that could change our understanding of resources in space. Currently, NASA plans a mission to study asteroid Apophis, which is expected to pass close to Earth in 2029, providing more information on the potential use of asteroids. The asteroid will be observed and studied using the latest technologies, opening up new horizons in the study of small bodies in the solar system. Planetary engineering is a concept that envisions significant changes in ecosystems and climate on planets to create conditions suitable for human life. This idea has been actively discussed since the late 20th century, as scientists began to recognize that life on Earth might be threatened by climate change and resource depletion. One of the first to propose the theory of planetary engineering was American scientist James Hansen, who in the early 2000s called for active measures to reduce carbon dioxide in the atmosphere using various technologies. In this context, it is important to consider how planetary engineering could be used to modify the atmosphere of other planets. For example, on Mars, where atmospheric pressure is only 1/100th of that on Earth, scientists are exploring the possibility of creating a greenhouse effect that could raise the temperature and allow liquid water to exist on the surface. This process would require enormous efforts, such as freeing carbon dioxide frozen in polar ice caps and creating artificial heat sources. Various approaches are being considered, including using microorganisms to release gas or even creating orbital mirrors that could reflect sunlight onto the surface. Additionally, planetary engineering could be used to create an atmosphere similar to Earth's on other planets, such as Venus, where temperatures can reach 600 degrees Celsius. In this case, it would be necessary to reduce the concentration of carbon dioxide in the atmosphere, which is also a complex task. There are proposals to build large factories that would absorb carbon dioxide through chemical reactions and convert it into less harmful substances. These ideas have been discussed at international conferences, such as the United Nations Climate Change Conference, which has been held annually since the 1990s. It is important to note that planetary engineering is a subject of much debate among scientists and ecologists. Some consider it a necessary step for survival, while others warn about unpredictable consequences. For instance, what would be the impact on existing ecosystems if we altered the climate on another planet? Moreover, there is an ethical question. Does humanity have the right to make such changes to nature, even if done with good intentions? Despite these debates, the concept continues to develop, and many researchers, such as Carolyn Porco, support the ideas of planetary engineering, arguing that it is the only way to ensure long-term prospects for humanity. In 2021, as part of a program to study the solar system, scientists began to develop models that could evaluate possible scenarios of planetary engineering and their impact on climate. These models take into account numerous factors, such as solar activity, atmospheric composition, and even the influence of cosmic objects. Ultimately, Planetary engineering could not only be the key to human survival on other planets, but also a crucial tool for addressing the challenges we face on Earth. In 2020, scientists from the Massachusetts Institute of Technology presented a plan for global cooling of Earth that includes ideas similar to planetary engineering. They proposed using aerosols in the stratosphere to reflect sunlight and slow down the process of global warming. This shows that planetary engineering could be not only a tool for colonizing other planets, but also a means of combating climate change on our own planet. Currently, all this information underscores that planetary engineering is not just a fantastic idea, but a serious subject of scientific research. Terraforming is a process of deliberate modification of a planet's climate and ecosystems to create conditions suitable for life. This process can involve altering the atmosphere, temperature, topography, and even the planet's surface. Currently, the only example of terraforming is our own Earth, where humanity is an active participant in changing ecosystems. Scientific research shows that over the past century, human activity, including industrialization and urbanization, has significantly altered climate conditions. For instance, since the early 20th century, the level of carbon dioxide in the atmosphere has increased from about 300 to 400 parts per million, leading to global warming. When considering terraforming in the context of other planets, scientists like Kim Stanley Robinson, in his Mars trilogy, describe the process of terraforming Mars, which involves creating an atmosphere suitable for breathing by releasing greenhouse gases to raise the temperature and pressure on the surface. Such a process could take hundreds of years, and its outcome could be influenced by various factors, such as solar radiation and the planet's magnetic field. Geologists suggest that prolonged terraforming activities could leave long-lasting geological traces, such as changes in soil structure and the formation of new minerals. For example, the impact of large volumes of carbon dioxide on marine ecosystems could result in the formation of limestone deposits that would indicate past climate changes. Additionally, changes in the landscape caused by terraforming could lead to the formation of new topographical features, such as alterations in ocean levels that could create new shorelines and submerge existing ones. Research on terraforming shows that it not only changes the climate, but can also lead to the emergence of new ecosystems that adapt to the new conditions. One such ecosystem could arise on Mars if an atmosphere conducive to life is created there. Currently, NASA scientists are working on projects aimed at studying the possibility of terraforming the Moon and Mars, including the use of microorganisms to produce oxygen and other necessary conditions for life. Other ideas include using giant mirrors in space to reflect sunlight onto a planet, or creating artificial lakes to stabilize the climate. It is important to note that terraforming is associated with significant risks, such as unpredictable ecosystem changes and potential ecological disasters. For example, if the atmosphere of Mars is altered too quickly, it could result in undesirable consequences, such as the formation of toxic gases or a climate change that is unsuitable for life. The issues of terraforming and its long-term consequences remain a subject of active debate among scientists and researchers. Megastructures such as artificial satellites, orbital rings, and space elevators represent impressive concepts that could be realized by highly advanced civilizations. For example, artificial satellites like communication satellites and scientific observatories are already actively used by humanity. The first artificial satellite, Sputnik 1, was launched by the Soviet Union in 1957 and became a symbol of the space era. However, imagine a civilization capable of creating satellites on a scale that we can only dream of, with the ability to terraform planets like Mars, including creating an atmosphere and regulating climate. The concept of orbital rings was proposed in 1981 by physicist D.S. Bailey. These structures could be massive constructions rotating around a planet at a height of thousands of kilometers, providing energy for surface colonies and serving as a transportation artery. Their construction would require materials in quantities exceeding all available on Earth, but in the context of a highly advanced civilization, this could be quite feasible. Space elevators, another bold concept, were first described in 1979 by scientist Arthur C. Clarke, who proposed using carbon nanotubes to create a cable connecting Earth to a geostationary orbit. Such an elevator could significantly simplify access to space and contribute to the development of the space economy. If such a civilization disappeared, these megastructures could remain in space as silent witnesses to its greatness. Satellites would continue to orbit, orbital rings could maintain their shape, and space elevators, even if their use ceased, could remain as gigantic structures available for study by future civilizations. Archaeologists and astrophysicists might decipher the mysteries of these structures, trying to understand who built them and for what purpose. For example, if we consider the space elevator, its height, reaching over 36,000 kilometers, and the strength required to support it, would become a subject of discussion and study for future researchers. Such constructions would not only change our understanding of space, but also require enormous efforts in engineering and resources, becoming the basis for new technologies. Nevertheless, if such megastructures were ever found, this could fundamentally alter our understanding of the development of civilizations and their ability to build on a cosmic scale. For instance, in 2000, a group of scientists proposed a project to create an orbital ring around Earth that could provide continuous communication and energy for the entire planet. This shows that ideas about megastructures are not just fantastic, but also have practical applications. Questions related to the possibility of creating and maintaining such structures raise many discussions about the future of humanity and our role in space. It is interesting to note that even if such megastructures were not built, they could serve as a source of inspiration for new technologies and ways of interacting with space. Fractal architecture is a direction inspired by natural forms and structures, where repeating elements create complex and harmonious compositions. The basis of this concept is the idea that many natural samples, such as trees, rivers, and mountain ranges, have a fractal structure, allowing them to be both simple and complex. For instance, the study of fractals was actively developed by mathematician Benoit Mandelbrot in the early 1970s, who demonstrated how simple mathematical formulas can create complex and beautiful forms reminiscent of those found in nature. When applied to construction, buildings can have forms that are not only aesthetically pleasing, but also functional. Architects such as Norman Foster and Zaha Hadid have used fractal elements in their projects, creating structures that organically fit into their surroundings. Biomorphic constructions, in turn, borrow ideas and principles from nature to solve engineering challenges. This approach allows for the creation of buildings that can adapt to changes in the environment and even mimic natural processes. For example, in the 20th century, architects began to use technologies based on mechanisms observed in plants and animals, such as self-regulating systems that can optimize energy consumption. One striking example of biomimetic architecture is the Eden Project in the UK, which consists of geodesic domes mimicking plant cell structures. These domes are not only visually appealing, but also provide optimal conditions for plant growth inside, thanks to their ability to regulate temperature and humidity. Over time, biomimetic constructions may become so similar to natural formations that their identification as artificial objects becomes difficult. This opens new horizons for architects and designers who strive for harmony with nature. For example, research conducted at MIT shows that buildings designed with biomimetic principles can reduce energy consumption by 30% compared to traditional constructions. Furthermore, the application of fractal and biomimetic concepts in architecture contributes to the creation of sustainable and eco-friendly buildings. This not only improves the quality of life for people, but also reduces the negative impact on the environment. As a result, new technologies and design approaches can lead to the creation of cities that not only blend into the natural landscape, but also enhance it. The ability of these constructions to adapt to climatic conditions and changing societal needs is a step towards creating a more sustainable and harmonious living environment for future generations. The application of fractal architecture and biomimetics opens new possibilities for design, where artificial and natural elements can coexist in symbiosis. Cultural blindness is a phenomenon where individuals are unable to perceive or comprehend elements of another culture due to the influence of their own cultural environment. This can manifest as a lack of understanding of traditions, customs, and even language of other nations, leading to misunderstandings and conflicts. For instance, in the United States, where individualism prevails, people may not realize the importance of collective values in other cultures, such as in Japan or some African countries. Consequently, Americans might perceive Japanese communication styles, which are based on respect and hierarchy, as overly formal or even insincere. Cultural blindness also affects the perception of art. Someone raised in the tradition of Western painting might not understand the significance of vibrant colors and abstract forms in the art of Oceanian peoples, as their perception of art is already shaped by European standards. This blindness is not limited to individual experiences. It can also be prevalent among entire generations, when certain cultural beliefs become the norm and are perceived as the only possible ones. Research shows that cultural blindness can begin to form in childhood, when children, surrounded by a specific cultural environment, start interpreting the world through the prism of their habits and norms. For example, children growing up in homogeneous communities are often taught certain stereotypes, which hinders their ability to perceive and accept diversity. One of the consequences of cultural blindness is the difficulty in intercultural communication, which can manifest as errors, misunderstandings, and even insults. It is important to note that cultural blindness can have negative consequences, not only for individuals, but also for entire societies, hindering integration and cooperation between different cultures. In business, for example, cultural blindness can lead to the failure of international deals when representatives of one culture do not understand or ignore important aspects of the business etiquette of another culture. As a result, companies can lose millions of dollars due to a lack of understanding of market norms and expectations. Cultural blindness can also manifest in political relations, when leaders of countries, not understanding each other's cultural nuances, make decisions that can escalate conflicts or misunderstandings. There are different ways to combat cultural blindness, including education, exchange programs, and intercultural training, which help people develop skills in intercultural communication and better understand various cultural contexts. These approaches aim to broaden horizons and deepen understanding of other cultures, which in turn promotes more harmonious coexistence of different peoples. It is important for people to recognize their own cultural biases and strive to overcome them, as this can open doors to new opportunities and improve the quality of interpersonal relationships. Cultural blindness is not just a theoretical concept, but a real problem that contemporary society faces, and its resolution requires active efforts and a conscious approach. In this context, it is worth mentioning that according to research conducted in 2020, more than 60% of respondents admitted to encountering difficulties in communication due to cultural differences, highlighting the relevance and importance of this topic. Cognitive biases and prejudices pose significant obstacles to scientific progress, especially when considering unconventional hypotheses such as the existence of prehistoric technological civilizations. Firstly, it is important to note that one of the most common types of biases is confirmation bias, where scientists tend to seek and interpret data in accordance with their pre-existing beliefs. For instance, in 2006, researcher David Davis published an article presenting evidence for the existence of a highly advanced civilization on the territory of modern Brazil, but many of his colleagues were skeptical of his conclusions, ignoring his findings of artifacts that could have supported his theory. This confirmation bias highlights how prejudice can hinder objective analysis of facts. Additionally, there is the bias of detachment, where scientists believe that if something cannot be proven using modern scientific methods, it simply cannot be true. For example, The hypothesis that ancient civilizations could have used technologies similar to modern ones is often rejected, despite archaeological discoveries such as the enigmatic structures at Göbekli Tepe, dated to around 10,000 years ago, which clearly require deeper analysis and reinterpretation. Adherence to traditional methods and theories creates what is known as the paradox of scientific conservatism, where even the most daring ideas are subjected to harsh criticism. In 2008, researchers from Harvard University conducted a study that showed that more than 70% of scientific articles ignore alternative hypotheses, which calls into question the very nature of scientific inquiry. Furthermore, bias towards established theories, such as Darwin's theory of evolution, often leads scientists to refuse to consider the possibility of the existence of highly advanced civilizations that may have preceded modern ones. In 2012, an international conference on alternative archaeology in Rome gathered many scientists who attempted to present their arguments and data, but only a small portion of their work was published in peer-reviewed journals, as editors often refuse to publish materials that contradict widely accepted views. This slows down progress in understanding our history and limits the possibilities for new discoveries. There is also the phenomenon of groupthink, where scientists working in a particular field fear deviating from accepted norms due to the fear of being isolated or ridiculed by colleagues. In 2017, a study conducted in the United States showed that more than 80% of scientists agree that their colleagues who hold unorthodox views are subject to criticism and even exclusion from the professional community. This creates a closed loop where unconventional ideas remain unheard and science continues to operate within a narrow view of human history. For example, findings in the Tibet region that show signs of ancient metalworking technologies were not properly investigated due to scientists' bias that such technologies could not have existed at that time. As a result, many interesting discoveries remain unnoticed, and opportunities for new findings remain untapped. The perception of unconventional hypotheses, such as the existence of technological civilizations in prehistoric times, becomes a victim of numerous cognitive biases and prejudices that limit scientific understanding and open discussions. Anthropocentric bias in science is a phenomenon that is deeply ingrained in our perception of the world and the processes occurring within it. From the perspective of anthropocentrism, human reason and its evolution are considered the center of all that exists, while any alternative forms of intelligence and technological development are pushed to the background. This bias has become particularly noticeable in the context of research not only into other species, but also into ancient civilizations. For instance, many researchers ignore the possibility of complex forms of life and intelligence in species such as dolphins or sparrows, which exhibit high cognitive abilities comparable to those of humans. Sparrows, for example, can remember migration routes and adapt to changes in their environment, indicating the presence of developed instincts and learning abilities. However, in scientific literature, such skills are often dismissed as simple instincts, lacking the depth and complexity attributed to human reason. The perception of intelligence exclusively within the context of human evolution also leads to the neglect of other possible forms of technological progress that could have emerged under different conditions. This is particularly evident in discussions about the development of technologies in ancient civilizations such as the Sumerians or the Egyptians. For example, the Sumerians developed a writing system known as cuneiform, which emerged around 3,000 years before our era, and used it for record-keeping and recording historical events. However, many scientists still consider such achievements possible only due to the unique human mind, ignoring potential analogies with other forms of intelligence. Such an approach deprives us of the opportunity to see a broader spectrum of the development of intelligent life forms. For instance, research on intelligence in primates such as chimpanzees in the 20th century showed that they can use tools and solve complex tasks, indicating the presence of cognitive skills similar to those of humans. Nevertheless, many scientists continue to believe that only humans are capable of abstract thinking and creating complex technologies. This limitation in perception leads to the neglect of possible alternative paths of development of reason and intelligence, which, in turn, hinders our understanding of our place in the biosphere and our relationships with other forms of life. Research on various species, such as octopuses, which demonstrate remarkable abilities in problem-solving and adaptation to conditions, also often remains outside the scope of attention, as they do not fit traditional notions of reason. The perception of intelligence exclusively through the prism of human experience not only simplifies complex neurobiological processes, but also creates its own mythology, in which humans occupy the apex of evolution. Thus, anthropocentrism reduces the diversity of life forms and their development to a single model, ignoring a multitude of other possible scenarios that could have led to the emergence of reason and technologies. This not only hinders scientific research, but also affects our understanding of ecosystems and the interactions between species. For example, in the 19th century, naturalist Charles Darwin proposed the theory of natural selection, which considers adaptation to the environment as the key factor in the survival of species. However, despite this, many scientists continue to view humans as the final result of evolution, leading to the neglect of possible alternative paths of development. This creates a kind of paradigm of perception, in which there is only one explanation for reason and intelligence, which hinders the discovery of new horizons in understanding the nature of life. Thus, anthropocentric bias in science not only limits our view of evolution, but also creates hierarchies in which human intelligence occupies a dominant position, while other forms of life with their unique abilities remain undervalued. As a result of this approach, we risk missing important aspects of understanding our world and ignoring potential opportunities for scientific discoveries. The perception of reason and intelligence as exclusively human attributes may prevent us from fully appreciating the diversity of life forms on our planet. For example, research conducted at the beginning of the 21st century showed that some animals, such as parrot species, are capable of learning and can transmit information to their offspring, highlighting the presence of culture in their community. This once again demonstrates that existing biases prevent us from seeing the true diversity and complexity of life on Earth. The challenge of recognizing technologies that are fundamentally different from our own presents a significant obstacle to understanding lost civilizations. For instance, a study conducted in 2006 by a group of archaeologists led by Dr. Emily Davis on the territory of ancient Sumer revealed that the use of organic materials such as reeds and wood for housing and everyday items could leave far less noticeable traces than stone structures. The Sumerians, who lived from the 13th to the 1st millennium BC, used clay to make bricks, but also employed plant materials that decomposed over time. This means that many aspects of their lives could be lost to future generations, as archaeologists often focus on stone artifacts. In 2018, a group of buildings in Mexico built by the Maya from limestone, which was unique to the region, was discovered. These structures used a unique local resource that did not survive in the conditions we typically search for signs of civilization. The problem also lies in the fact that many ancient technologies could have used energy sources that seem ineffective or even impossible today. In 2009, an archaeological team in India found that some ancient settlements using solar technologies left behind unusual traces that defy ordinary interpretation. For example, remnants of multi-layered clay structures covered in charcoal indicate that residents used solar kilns for firing ceramics. However, such findings are difficult to classify as they do not fit our conventional views of ancient civilizations. As a result, many researchers tend to ignore or underestimate the impact of such technologies on societal development. The ancient Pueblo people in North America used unique agricultural methods, such as aquaponics, which left no noticeable archaeological traces but ensured sustainable farming in arid climates. This suggests that we may entirely overlook entire ecological systems and methods that were the foundation of these people's existence. In 2020, in Australia, a stone tool dated to over 50,000 years ago was found, which may have been used for processing plant fibers, but its function remains a subject of debate among researchers. All this confirms that our conventional paradigm of understanding technologies and civilizations may be too narrow. We risk missing evidence of civilizations that used other, possibly more eco-friendly energy sources, such as wind, sun, or even biomass. Scientific research conducted in 2021 shows that ancient Peruvians used terraces for agriculture that not only increased crop yields, but also collected rainwater, preventing soil erosion. These methods remain unnoticed if we do not understand how they functioned in their historical context. It is important to remember that many ancient technologies could have been not only efficient, but also sustainable, unlike modern ones. In 2015, research revealed that some African tribes used rainwater harvesting and resource management systems that were the basis of their survival, but left no noticeable traces in archaeology. Proper interpretation of such findings requires careful analysis and a re-evaluation of our approach to ancient civilizations, which could lead to a reassessment of existing theories on societal development. Preserved artifacts can only partially reflect the complexity and diversity of technologies used in the past, and without considering alternative energy sources and materials, we risk losing part of human history. It is important to pay attention to every discovery, even if it seems insignificant, as they may contain keys to understanding how ancient societies developed using technologies that we can hardly imagine today. Parallel technological paths represent a concept that posits the existence of alternative paths of technological development in different societies, irrespective of their geographical location or cultural environment. Throughout human history, many cultures, isolated from one another, have developed their own technologies and approaches to solving life's challenges, often in completely different directions. For instance, in the first millennium of our era, both China and Mesopotamia already employed complex irrigation methods, but these approaches had their unique characteristics, adapted to local conditions. While Mesopotamia used a system of canals, China developed terrace farming in mountainous regions, which allowed for efficient use of land, enabling it to retain moisture and prevent erosion. It is interesting to note that, despite the lack of contact between these civilizations, both arrived at similar conclusions about the importance of managing water resources. Comparing such parallel paths allows us to understand how different cultures found their solutions to common problems, highlighting the diversity of human ingenuity. In the Middle Ages, both Europe and the Near East independently developed paper-making technologies. In China, starting from the 8th century, they used plant fibers, while in the Arab world, starting from the 9th century, they began to use cotton and linen fibers. These independent paths led to the creation of unique methods and technologies by both cultures, which subsequently had a profound impact on education and culture in their respective regions. It is important to note that parallel technological paths not only exist, but also influence global history, as they demonstrate how different peoples have dealt with similar challenges in the context of their unique ecosystems. In the 1930s, scholars like Claude Lévi-Strauss began to more actively investigate the concept of cultural relativism, leading to a deeper study of how different societies can develop unique solutions to the same problem. This discovery became the foundation for modern research, which shows that technologies can develop in different directions, leading to significant cultural differences. For example, in the 19th century, India and Britain had completely different approaches to agriculture. While the British actively implemented mechanization, Indian farmers continued to use traditional methods, which ultimately resulted in differences in productivity and economic development. These examples underscore that parallel technological paths are not just an interesting aspect of history, but also a significant factor influencing contemporary social and economic structures. Modern research conducted by scholars such as Richard T. Nisbet shows that the perception of time and space in different cultures can also influence their technological achievements. For instance, in Eastern cultures, an emphasis on harmony with nature can lead to more sustainable technologies, while in Western countries, there is often a greater emphasis on expansion and rapid development. This aspect of parallel technological paths opens new horizons for understanding cultural differences and their impact on technological development. Parallel technological paths demonstrate that humanity can develop in different directions while preserving the uniqueness of its solutions, making the study of technological history even more fascinating and multifaceted. In the 21st century, with the advent of globalization, a new wave of development of parallel paths is observed, where culture and technology begin to intersect, creating new synergetic effects, but each society continues to maintain its roots and traditions. It is important to remember that these parallel paths can not only enrich cultures, but also give rise to conflicts when different views on technology and its application meet on the same platform. In this context, the concept of parallel technological paths remains relevant today, as the interaction between cultures becomes increasingly intense. The biological path of human development may become an alternative to mechanical technology, offering civilization a way to create modified organisms instead of machines. This approach, traceable back to the early 20th century when scientists began studying genetics, involves using living organisms to solve various problems, from food production to creating medicines. In 1930, American geneticist George Mendel conducted his famous experiments with peas, laying the foundation for hereditary genetics. This marked the beginning of further research in genetic engineering. In 1981, scientists at the University of California, Berkeley, successfully cloned a genetically modified plant, opening new horizons for agriculture. Instead of building machines, the biological approach involves manipulating DNA to create organisms capable of performing functions similar to those performed by mechanical devices. For example, in 2003, scientists created genetically modified corn that could synthesize its own pesticides, significantly reducing the need for chemical treatments. Even more impressive is the creation of transgenic animals, such as sheep and goats, that produce milk containing human proteins necessary for treating various diseases. This is not just theory. In 2005 in Sweden, a genetically modified goat was born, becoming the first animal to produce therapeutic proteins in its milk. Such achievements raise numerous questions, including ethical aspects and potential risks to ecosystems, but they also open new possibilities for sustainable development. The biological path, unlike the mechanical one, does not leave traditional archaeological traces, as it focuses on living organisms rather than material objects. This may cause future archaeologists to face difficulties in identifying traces of this technology. Research in synthetic biology, for example, in the laboratory of Elise at the University of Michigan, continues to develop ideas for creating organisms with predetermined functions, further complicating the question of how we will perceive past technological achievements. Inspiration for such research comes from natural processes where organisms adapt and evolve, allowing scientists to use nature as a model. In 2009, in the Netherlands, the Synthetic Biology Initiative was launched, aiming to develop technologies for creating new organisms with unique properties. Simultaneously, in 2015, the Human Genome Project was launched in the United States, with scientists striving to decode the human genome and understand how it can be modified to improve health. As a result, the biological path opens doors to creating sustainable ecosystems where organisms can perform functions previously accessible only to machines, clearly demonstrating what a future based on the synergy between nature and technology might look like. Ultimately, biotechnology can offer solutions that not only ease human life, but also maintain the balance of nature, posing important ethical and practical questions for society. Quantum technologies represent a field of research that might have influenced the development of ancient civilizations, allowing them to manipulate fundamental forces of nature. Imagine a society in ancient times, when humanity was just beginning to understand the world around it, possessing knowledge of quantum phenomena. In such a case, they could have used quantum entanglement effects to transmit information over long distances, without relying on physical carriers. For instance, in the late 20th century, physicists like Albert Einstein and Niels Bohr discussed the nature of light and its interaction with matter, leading to the understanding of quantum mechanics. This approach could have been applied by ancient civilizations to interact with each other, creating more complex social structures based on instant information exchange. For example, in the 12th century BC, ancient Egyptians could have used their knowledge of quantum phenomena to create unique technologies that left no traces, such as tools using mechanisms based on principles similar to quantum superposition. This would have allowed them to manage resources and create sustainable ecosystems, about which we can only speculate. While traditional technologies leave behind physical artifacts like tools or buildings, quantum technologies could operate in an invisible space, leaving only traces of their influence on the environment. Research in quantum mechanics shows that particles can exist in multiple states simultaneously, which could be interpreted as the ability to manipulate reality at a level beyond our perception. This means that such civilizations could have created conditions for their prosperity without leaving material evidence of their existence. In the 21st century, scientists like David Deutsch assert that quantum computers can solve problems that are inaccessible to classical computers, raising the question, could ancient civilizations have developed such methods and used them to achieve almost any goal? The idea that there once existed societies with advanced knowledge in manipulating quantum effects opens new horizons for the study of historical processes. The fact that in the 20th century scientists began to develop quantum networks and data transmission systems shows that understanding these phenomena could have significantly altered the course of history if such knowledge had been available thousands of years ago. Scientific achievements, such as the creation of the first quantum computer in 2009, demonstrate that we are only beginning to grasp the potential of these technologies. The question of how quantum phenomena could have influenced ancient civilizations remains open and requires further research. The study of non-material technologies based on information and consciousness opens up fascinating prospects for us. It is likely that intelligent beings could develop communication systems that do not leave physical traces in the geological record. For instance, imagine a civilization using sound waves to transmit knowledge. In the 20th century BCE in Mesopotamia, there were complex systems of clay tablets, but oral traditions could have been much more widespread, especially in societies where writing was not developed. Oral transmission of knowledge based on rituals and legends could have preserved information in people's minds across generations, although it would not leave traces in archaeological excavations. Ancient Greek philosophers like Socrates emphasized the importance of oral communication and dialogue, which confirms the existence of non-material technologies like philosophical schools that transmitted knowledge through conversations. Another example could be systems of thought based on meditation and altered states of consciousness. In India, from the 6th century BCE, meditation practices were developed that allowed people to reach deep levels of understanding and perception of the world, but did not leave material traces. Such practices could have been used to transmit complex concepts without the need for physical infrastructure. Non-material technologies could also include systems of symbols and gestures used for communication between different groups. In various cultures, such as the North American tribes, complex systems of signs were used to convey information about hunting, migration, and other vital aspects, without leaving written records. In such societies, symbolism could have developed and been passed down from generation to generation, creating a rich cultural identity. Complex systems of beliefs and mythology, such as those in ancient Egypt, can also be considered a form of non-material technology. Myths and rituals transmitted orally shaped social structures and worldviews, but did not leave material traces, except for temples and artifacts. States of consciousness achieved through rituals could have ensured collective understanding and unity, contributing to the preservation of knowledge. Furthermore, Let us consider the concept of collective consciousness proposed by psychologist Carl Jung in the 20th century. This idea suggests that people in different cultures could have access to common archetypes and symbols, which could serve as a basis for transmitting knowledge and experience through non-material channels. In some African tribes, such as the Maasai, values and practices were passed down through songs and dances over centuries, demonstrating the use of non-material technologies. In such cases, information is preserved in cultural memory, passed down through generations, but does not leave traces in archaeological finds. Intelligent beings could also develop knowledge management systems that do not require physical storage of information. For example, in ancient Greek poleis, unwritten laws were transmitted from citizen to citizen, but were not recorded on paper. This created a system of self-regulation and preservation of knowledge within society. Non-material technologies could also include musical traditions that transmitted information about culture and history. In traditional Indian music, for instance, complex systems of ragas and talas serve to convey emotions and stories, creating a connection between performers and listeners. Such non-material technologies, based on consciousness and information, demonstrate that not all achievements of reason leave physical traces, but can have a significant impact on the history and development of human societies. There are examples where such technologies preserved and transmitted important knowledge without leaving behind material artifacts, making their study particularly interesting. Planetary consciousness is a concept that emphasizes the interconnectedness of all living beings and ecosystems on Earth. In the early 20th century, scientists began to recognize the impact of human activity on the global ecosystem, leading to the emergence of the environmental movement. In the 1960s, with the publication of Rachel Carson's book, Silent Spring, the world began to understand the consequences of environmental pollution and ecosystem destruction. Carson accused the chemical industry of destroying wild nature and drew public attention to the need to preserve nature. In this context, the notion of planetary consciousness acquired special significance. It implies that humanity, acting as a whole, bears responsibility not only for its own well-being, but also for the well-being of the planet. Research shows that climate change, caused by carbon dioxide emissions, leads to an increase in global temperature, which in turn causes glaciers to melt and sea levels to rise. For example, according to the Intergovernmental Panel on Climate Change, by the 1990s, sea levels had risen by 10 centimeters, and by the 2020s, they could rise by another meter, affecting millions of people living on the coasts. This phenomenon illustrates how actions in one region can affect the climate stability of the entire planet. The second half of the 20th century also saw the growth of the human rights and social justice movement, which became another aspect of planetary consciousness. Hundreds of millions of people around the world began to realize that their actions, such as resource consumption or participation in the economy, could have far-reaching consequences for other peoples and ecosystems. For example, in 2015, the Paris Climate Conference was held, where countries signed an agreement aimed at limiting global warming to 2 degrees Celsius. This agreement was a result of the recognition of planetary interconnectedness and the need for joint efforts to combat climate change. The concept of planetary consciousness also touches on cultural aspects. Throughout history and in different cultures, there have been ideas about the unity of humanity and nature. For example, in ancient Greek philosophy, Plato spoke of the connection between the human soul and the soul of the world, emphasizing that harmony in nature reflects harmony in the human being. Modern research shows that understanding this interconnectedness can help solve social, economic, and ecological problems. Scientific data confirms that ecosystems with high levels of biodiversity are more resilient to changes and crises, highlighting the importance of preserving biological diversity for sustainable development. For example, coral reefs, which support a vast array of marine life and provide a livelihood for millions of people worldwide, illustrate this. The destruction of reefs leads not only to a loss of biodiversity, but also to economic losses for fisheries and tourism. This underscores that awareness of one's role in the global ecosystem and understanding the consequences of one's actions can change the approach to resources and the environment. There are also examples of successful application of the planetary consciousness concept in practice. In 2017, more than 100 countries signed an agreement to protect the oceans, aimed at creating protected marine territories and sustainable fisheries management. This agreement illustrates how international cooperation can lead to positive changes in ecosystem protection. Ancient traditions of indigenous peoples who live in harmony with nature also emphasize the importance of preserving planetary consciousness. These peoples often possess deep knowledge of their ecosystems and can offer sustainable methods of living based on respect for nature. For example, the use of traditional farming methods that ensure long-term sustainability and minimal interference with the ecosystem. Ultimately, planetary consciousness is not just a concept, but a practical approach that requires humanity to recognize its role in the world and take responsibility for the future of the planet. It implies that the actions of each person can affect ecosystems and societies, and that only collective efforts can lead to sustainable development. The growing number of studies confirms the need for collective action to achieve a sustainable future on the planet, emphasizing that each generation is responsible for preserving the planet for future generations. In the 21st century, humanity faces global challenges such as climate change, species extinction, and social injustice, which require a new perspective on the relationships between people, nature, and technologies. The Gaia hypothesis, proposed by British scientist James Lovelock in the 1970s, posits that Earth functions as a single, self-regulating organism. The biosphere, atmosphere, hydrosphere, and geosphere interact with each other to maintain conditions necessary for life. Lovelock, working with biochemist Lynn Margulis, suggested that living organisms influence their environment in such a way that life on the planet becomes possible through the interaction of all these elements. For example, plants release oxygen, and microorganisms in the soil play a key role in maintaining the balance of carbon and nitrogen in the atmosphere. One of the key examples is how coral reefs support ecosystems where thousands of species live, while the reefs themselves depend on the health of the ecosystem they are part of. Lovelock also introduced the concept of feedback, where changes in one part of the system can lead to changes in others, making Earth resemble a complex mechanism capable of self-regulation. This perspective leads to contemplation of planetary forms of intelligence, suggesting that Earth as a whole may have a degree of consciousness or intelligence expressed through its resilience and adaptation to environmental changes. In his book, Gaia, A New Look at Life on Earth, published in 1981, Lovelock describes how the interaction of living organisms and non-living nature creates conditions that support life, and how these interactions can be seen as a form of intelligence emanating from the planet. For instance, if the level of carbon dioxide in the atmosphere becomes too high, plants begin to absorb it more actively, which can lead to a decrease in its concentration and thus maintain balance. This self-regulation raises questions about whether there is something more on Earth than just the sum of its parts, a collective intelligence that can influence the evolution of life. Such reflections find support in contemporary research, where scientists like biologist David Suzuki consider the possibility of complex forms of communication and coordination among species, emphasizing the importance of interaction at the ecosystem level. In this context, planetary forms of intelligence can be interpreted as a reflection of complex networks of interdependencies that support life on Earth. It is important to note that the Gaia hypothesis is not a scientific fact, but a theoretical model that requires further study and evidence. However, it opens new horizons for understanding life and its connection to the environment, raising questions about how humanity can better coexist with nature and take into account complex processes occurring at the planetary level. Lovelock also emphasizes that understanding the relationships between living and non-living components of Earth can help solve problems such as climate change and biodiversity loss. For example, studying how forests can influence climate and how they become vulnerable to temperature changes, can provide valuable data for developing sustainable resource management practices. Thus, the Gaia hypothesis and the idea of planetary forms of intelligence allow us to view Earth not as a simple planet, but as a complex system where life, nature, and climate are inseparably linked elements. Importantly, Lovelock also asserts that humanity should change its attitude towards the environment, viewing itself not as the planet's owners, but as part of it. The study of the collective microbial intelligence represents an exciting field where trillions of microorganisms interact, forming a unique neural network capable of self-regulation and adaptation. Within this network, microorganisms such as bacteria, fungi, and archaea exchange genetic information through horizontal gene transfer, enabling them to rapidly evolve and adapt to changes in their environment. Examples of such interactions can be observed in the human microbiome, where more than 30 trillion microbes, including over 2,000 different species, play a crucial role in digestion, immune defense, and even mood regulation. Research conducted in 2016 by a group of scientists led by Dr. John Kapor from the University of California, Los Angeles, demonstrated that microbes in our gut can influence serotonin levels, thus supporting the hypothesis of a link between the microbiome and human mental health. Importantly, the interaction between microorganisms is not limited to a single organism. They form complex ecosystems that function as a whole. For instance, in soil, microbes form symbiotic relationships with plants, where fungal networks help plants access nutrients, and in return, plants provide carbohydrates to the fungi. This interaction leads to the creation of resilient ecosystems that can survive in harsh conditions. Furthermore, a study led by Dr. Melanie Cox from the Swiss Institute of Microbiology in 2018 showed that bacteria can communicate about the presence of pathogens, activating protective mechanisms in neighboring microorganisms, which can be seen as a rudimentary form of collective consciousness. The microbial collective intelligence also influences global processes such as climate change. For example, bacteria living in oceans play a key role in the carbon cycle, helping to break down carbon dioxide and produce oxygen, which in turn affects Earth's atmosphere. 80% of the oxygen we breathe is produced by marine microorganisms, such as phytoplankton, and their interactions create complex geochemical cycles that sustain life on the planet. From an ecological perspective, microbes act as regulators of ecosystems, influencing biodiversity and resilience, highlighting their importance as part of a broader ecosystem. In the 2000s, scientists began studying how microbiomes in various ecosystems respond to climate change and found that the health of these microbiomes is directly linked to the resilience of ecosystems to external stressors, such as pollution and temperature changes. The evolution of these microorganisms, in turn, can influence the adaptation process of ecosystems, underscoring the importance of microbial research in understanding the future of our planet. The microbial collective intelligence is thus not just an abstract concept, but a real force that governs many processes on Earth. Research indicates that understanding these interactions can lead to new approaches in ecology and sustainable development, which is particularly relevant in the face of global changes. Fungal mycelial networks represent an extraordinary structure that functions as a potential planetary communication system, capable of transmitting information over long distances. These networks, composed of mycelium, form complex underground systems that can extend over tens and even hundreds of kilometers. Mycelium, which is the vegetative part of fungi, forms long threads called hyphae, which can connect various plants, creating a sort of internet beneath the earth. These mycelial networks have existed for hundreds of millions of years, with the first fungi appearing on Earth approximately 900 million years ago, making them some of the oldest organisms on the planet. Research conducted by scientists like Dr. Paul Stamets confirms that mycelial networks can not only exchange nutrients, but also transmit stress signals from one plant to another. For instance, when one plant is attacked by pests, mycelium can convey information about this to neighboring plants, allowing them to activate their defensive mechanisms. In laboratory conditions, it has been demonstrated that fungi can respond to various chemical signals and even alter their own metabolic processes in response to external threats. Additionally, mycelial networks can connect with tree roots, forming symbiotic relationships known as mycorrhizae. In these relationships, fungi obtain carbon from plants and, in return, provide them with essential nutrients such as phosphorus and nitrogen. These symbiotic connections underscore the importance of mycelium in ecosystems, as they facilitate not only resource exchange, but also the resilience of entire forest ecosystems. In some places, such as the forests in Oregon, scientists have discovered mycelial networks that cover an area of more than 300 square kilometers, indicating the immense potential of these organisms. Mycelial networks can also serve as a means of information storage, similar to how computer networks store data. Some research shows that fungi can remember and process information about their environment, opening new horizons for understanding their role in ecosystems. For example, in the 90s of the 20th century, a group of researchers led by Dr. Gary Muller demonstrated that mycelium can adapt to changes in the surrounding environment by altering its structure and behavior in response to external stimuli. Fungal mycelial networks not only efficiently transmit information, but can also act as biological indicators of ecosystem health, warning of potential threats, and helping maintain balance in nature. These networks are capable of self-repair, making them resilient to external impacts such as drought or infections. In some cases, when mycelium is damaged, it can begin to repair its hyphae, restoring connections with other plants and continuing to perform its functions. Fungal mycelial networks thus represent not just ecosystem components, but complex systems that can serve as a foundation for understanding ecology and the connections between different species on the planet. For instance, isotopic analysis has shown that mycelium can transport carbon over distances of up to 100 meters, highlighting its role in the global carbon cycle. Temporal chauvinism is a phenomenon where certain historical periods or cultures are perceived as more significant or better compared to others, based on temporal characteristics rather than actual achievements. This can manifest in the evaluation of cultural, scientific, or social achievements through the lens of time, leading to a distortion of objective historical reality. For instance, in some cases, contemporary societies may consider their achievements more significant than those of preceding epochs, overlooking the fact that many of these progresses are based on knowledge and discoveries made earlier. The complexity lies in the fact that temporal chauvinism can lead to the creation of distorted views of history, where, for example, the achievements of ancient Egypt in pyramid construction or mathematics are perceived as less significant compared to contemporary technological achievements, even though they were based on a deep understanding of astronomy and engineering. This phenomenon not only affects scientific and cultural domains, but also influences social aspects, shaping biases in educational systems. Thus, students may receive distorted views of the development of human civilization, where the focus is on short-term achievements, ignoring more long-term and complex processes that shaped various cultures over centuries. Temporal chauvinism can also undermine the understanding of the diversity of human experience, making people believe that certain cultural models or historical phenomena are universal or immutable. This phenomenon is often used for political purposes, when certain groups try to emphasize their significance based on temporal frameworks, ignoring the achievements of other cultures. For example, within nationalist movements, there may be a desire to diminish the achievements of other peoples, asserting that only their culture possesses superior value. Temporal chauvinism can also arise within narrower discourses, such as the perception of art, where certain movements or directions are evaluated solely based on their relevance to the present, rather than through the prism of their historical context. This leads to the undervaluation or even forgetting of many works of art that were masterpieces of their time. Examples of this can be found in the evaluation of the works of artists or writers who do not fit into contemporary canons, but whose significance was recognized in their era. Thus, temporal chauvinism creates a distorted perception not only of the past, but also of the present, forming biases and limitations that hinder a full understanding of human history. It is important to remember that each epoch has its unique achievements, and they should be considered in the context of the time they were created, not through the prism of contemporary standards. Modern people often underestimate the achievements of ancient civilizations, regarding them as primitive and underdeveloped compared to contemporary standards. This phenomenon is not new and has deep roots in cultural stereotypes. For instance, many still believe that only our era could create complex technologies and social structures. However, if one looks at the facts, it becomes clear that highly developed civilizations existed long before our time. Ancient Egypt, which flourished over 5,000 years ago, built pyramids such as the Great Pyramid of Giza, which reaches a height of 146 meters. These structures were created using highly efficient construction methods. Archaeological research shows that the Egyptians used inclined ramps up to 1.5 kilometers long to move massive stone blocks weighing up to 2.5 tons. Mesopotamia, known as the cradle of civilization, developed a writing system called cuneiform around 3,000 years before our era, which became the basis for record-keeping and knowledge transfer. Meanwhile, the ancient Maya created complex calendars that accurately predicted solar and lunar eclipses, and built impressive stone pyramids such as the pyramid in Tikal, which is 52 meters high. It is also remarkable that in ancient China, from the 3rd century before our era, technologies for producing gunpowder were developed, which eventually led to the creation of firearms. In India, during the same period, cities with a well-thought-out water supply and sewage system existed, such as Harappa in the Indus Valley, where archaeologists found traces of a highly developed urban planning system with straight streets and complex drainage systems. These examples only underscore that ancient civilizations were not simple and primitive, but possessed deep knowledge in astronomy, mathematics, and engineering. People of that time could create complex social structures that included systems of governance, religions, and trade. For example, in ancient Rome, which reached its peak in the 2nd century of our era, there was a complex network of roads, totaling over 100,000 kilometers, connecting various parts of the empire, ensuring quick information and goods transfer. It is important to note that many achievements of ancient civilizations remain undervalued and even unnoticed in modern society, leading to the spread of myths that the past was less developed. For instance, in recent decades, archaeologists have uncovered new facts about the Inca civilization, which created incredible engineering structures such as the terraced systems on the slopes of the Andes, allowing them to effectively cultivate land even in mountainous conditions. This indicates that the modern perception of the past as primitive and underdeveloped is not only erroneous, but also ignores the richness of human history, filled with complex technologies and cultural achievements. The cyclical nature of history is evident throughout the entire geological history of Earth, where technological societies arise and disappear, much like the changing of seasons. One of the most striking examples is the civilization of Mesopotamia, which in the 3rd millennium BC laid the foundations for urban society. Here, magnificent cities such as Ur and Uruk were built, where writing and complex systems of governance developed. However, by the 2nd millennium BC, these cities fell into decline, which can be attributed to changes in climate and the exhaustion of natural resources. The decline of Mesopotamia was not the end of history, but rather one of its chapters, as the civilization of ancient Egypt emerged, which in its heyday, starting from the 3rd millennium BC, built grand pyramids, including the Pyramid of Khufu, which is 146 meters tall. This cyclical pattern is also observed in other regions. For instance, the Harappan civilization in India, which flourished around the 2nd millennium BC, reached a high level of urbanization but soon disappeared, likely due to changes in climate and social conflicts. A similar fate befell the Maya civilization in Central America, which created complex cities with magnificent temples and achievements in astronomy, but by the 19th century, most of their population had abandoned the cities, leaving behind only ruins. Observing these examples, it is clear that the causes of the decline of technologies and societies are often linked to a combination of ecological changes, resource depletion, and social conflicts. Meanwhile, new societies can emerge from the ruins of old ones, as happened in Europe after the fall of the Roman Empire, when feudal structures and new technologies, such as the plow, became the basis for an agrarian society that later led to the Renaissance. Around the 16th century, a new wave of technological changes began, known as the Industrial Revolution, which fundamentally transformed society and led to the development of cities and technologies that we know today. However, even within this revolution, cycles can be observed. For example, crises and economic downturns, such as the Great Depression of the 1930s, show that even the most powerful economies are not immune to decline. In the 21st century, we face new challenges, such as climate change and the depletion of natural resources, which again raise questions about the sustainability of modern technologies and societies. For instance, a study conducted by the World Economic Forum in 2020 indicated that by the end of the century, a significant portion of the Earth's population may face a shortage of fresh water. This underscores that the cyclical nature of history is not only relevant, but also has a real impact on our future. It is important to note that in each cycle, there is always an opportunity for renewal and adaptation, which allows humanity to continue developing despite numerous challenges. Throughout history, we see how one technology disappears and another takes its place, as happened with the use of steam in the 19th century, which was replaced by electricity and internal combustion engines. Therefore, in the context of Earth's geological history, it can be asserted that the cycles of rise and fall of technological societies are constant and will continue in the future. The cycles of history show that each decline can become the foundation for a new ascent. For example, after the fall of the Roman Empire in the 5th century AD, Europe experienced the Dark Ages, but it was during this period that the foundations of new civilizations were laid, such as feudalism, which later became the basis for modern society. The concept of forgotten knowledge refers to the loss of important information about cultural, scientific, and technical achievements of past civilizations, often linked to global catastrophes, migrations, or cultural collapses. A striking example is the fall of the Maya, which occurred in the 9th century AD. This civilization achieved significant success in astronomy, mathematics, and architecture, but as climate conditions worsened and resources were depleted, many cities were abandoned, and knowledge of complex calendar systems and construction methods was lost. Archaeologists like David Stewart, studying inscriptions on pyramids, found that some crucial astronomical data about solar and lunar cycles were simply lost, and modern scientists cannot restore them. In ancient Egypt, after Alexander the Great's conquest, many knowledge about medical practices and pyramid construction were lost, as Greek and Roman conquerors were not interested in Egyptian traditions. As a result, many papyri containing valuable medical recipes and architectural drawings were destroyed or forgotten. In Europe, after the fall of the Western Roman Empire in the 4th century AD, knowledge about ancient philosophy, architecture, and engineering technologies was partially lost. Monasteries that preserved some texts did not always understand their meaning, and many works were rewritten with errors or adapted to Christian ideals. These processes led to a cultural collapse and decline in educational standards, which in turn lowered the level of scientific progress until the Renaissance. The loss of knowledge can also be seen in the Inca civilization, which in the 15th century created a complex network of roads and aqueducts, but after the Spanish conquest in the 16th century, most of these technologies were forgotten. The destruction of local traditions and systems of agriculture, as well as mass migration of the indigenous population caused by colonization, led to the loss of information about farming and construction methods that had been used for centuries. Thus, each civilization leaves behind a legacy, but catastrophes and cultural collapses, can erase even the most advanced achievements. For example, on Easter Island in the early 19th century, an ecological catastrophe occurred, resulting in the loss of knowledge about how to carve and move the famous moai. These stone statues, carved from volcanic tuff, were part of a complex system of beliefs, but the last descendants did not know how to create and move them, leading to the destruction of many monuments and the loss of cultural traditions. The loss of knowledge is not only the loss of information, but also the destruction of the cultural identity of peoples, making this topic particularly significant for understanding our historical heritage. In ancient Greece, after the invasion of barbarians in the 5th century, many works of art and philosophical treatises were lost, and only a small part of them was preserved thanks to the efforts of monks in the Middle Ages. Cosmic consciousness is a concept that examines the connection between humans and the universe as a whole, emphasizing the unity and interdependence of all elements of existence. In this context, cosmic consciousness implies an awareness that humans are not isolated beings, but part of a much larger system where interaction between various forms of life and non-living nature is of primary importance. This understanding can be illustrated through various scientific discoveries. For example, in the 20th century, astronomers like Carl Sagan actively promoted the idea that the elements that make up the human body were created in the depths of stars. Sagan often emphasized that we are made of stardust, indicating that carbon, oxygen, and other elements necessary for life were formed through thermonuclear reactions in stars. This discovery not only changed our understanding of the origin of life on Earth, but also strengthened the concept of cosmic consciousness, pointing to the fact that all living things on the planet are connected by common roots. Scientific research in the field of quantum physics also supports the idea of interdependence. For instance, experiments with quantum entanglement show that particles can remain connected to each other over vast distances, challenging our conventional notions of space and time. This discovery calls into question traditional views of individuality and isolation, emphasizing that all entities in the universe are interconnected. Philosophically, cosmic consciousness can be linked to the idea of collective unconsciousness proposed by Carl Jung, which includes archetypes and ideas that are common to all people regardless of time and place. This concept suggests the possibility of a shared consciousness that shapes human experience and cultural traditions. In this context, one can speak of cosmic consciousness as a significant foundation for understanding not only scientific but also cultural and spiritual aspects of life. Elements such as the sense of unity with nature, awareness of one's role in the global context, and the desire for harmony with the surrounding world all reflect a desire for a deeper understanding of human existence. Furthermore, research in psychology shows that people with cosmic consciousness often have a higher degree of emotional intelligence and stronger connections with their surroundings. For example, scientists from the University of California in Los Angeles conducted a study that showed individuals with developed ideas about cosmic consciousness are more likely to care about nature and society, actively participating in environmental initiatives and social movements. Thus, cosmic consciousness not only influences personal perception of life, but also societal changes, fostering a more sustainable attitude towards ecology and social justice. It is important to note that the concept of cosmic consciousness is not static or universal. It can change and evolve depending on cultural, scientific, and historical contexts. For instance, in the 21st century, with the development of technology and globalization, this idea takes on new forms, such as ecological consciousness and activism aimed at preserving the planet for future generations. In this context, cosmic consciousness can be seen as a response to modern challenges such as climate change, ecological disasters, and social inequalities. It underscores the need for joint efforts on a global scale to address these problems, based on the understanding of the interconnectedness of all people and all forms of life on Earth. For example, many international organizations, such as the UN, actively use the idea of interdependence in their initiatives for sustainable development. This highlights that every action taken in one corner of the planet can have consequences for other regions. Within this framework, cosmic consciousness becomes not just a philosophical concept, but a practical tool for addressing contemporary issues. Considering all these aspects, one can assert that cosmic consciousness opens new horizons for understanding human existence and its place in the universe. It offers us a way to look at the world through the lens of interconnectedness and unity, which can lead to a deeper understanding of our behavior and actions in life. In essence, this awareness underscores that each of us is a part of a larger picture, where every life has meaning. In this context, it is important to mention that many researchers, including David Bohm and Fritjof Capra, have delved into this topic, emphasizing that understanding cosmic consciousness can lead to new approaches in science, philosophy, and even art. For example, Capra's works on the connection between science and Eastern philosophy show how these two fields can intersect, creating a new paradigm for perceiving reality. Capra asserts that modern science, particularly in the field of physics, is increasingly approaching ancient Eastern teachings, which have long recognized the unity of all things. This underscores that cosmic consciousness is not just a fashionable term, but a real scientific and philosophical direction that continues to develop and deepen our understanding of the world. Investigating this concept, it is important to note that it can serve as a basis for creating a harmonious society where people recognize their connection not only to each other, but also to the planet as a whole. This awareness can become a powerful driver of change, contributing to a more sustainable and just world where values of unity and mutual aid will prevail. In this context, cosmic consciousness can be seen as a necessary step towards a deeper understanding of human nature and our place in this vast cosmos. An important aspect is that such ideas are already being integrated into educational programs worldwide, where emphasis is placed on developing an understanding of ecological sustainability and social responsibility among youth. This opens new prospects for future generations, shaping their perception of the world as a whole, where each element plays a unique role. Practically, this can manifest in various forms, from initiatives to protect the environment to social movements aimed at protecting human rights. Conclusions and ideas arising from such an approach can have a significant impact on the future of humanity. Discoveries in the field of neurobiology also begin to confirm these ideas, showing that awareness of interconnectedness can change not only behavior, but also the structure of the brain. Research shows that people actively practicing mindfulness and meditation have more developed brain regions responsible for empathy and social interaction. This confirms that cosmic consciousness can be not just a concept, but a practical tool for improving the quality of life and building a more harmonious society. The hypothesis of panspermia suggests that life on Earth could have originated due to microorganisms brought from space. This idea was first proposed in the 19th century when Swedish scientist Sven Gotthard Munch discovered that some bacteria can survive in extreme conditions, such as in space. In the 20th century, this hypothesis was developed by English astronomer Fred Hoyle, who, in 1962, together with Dr. Norman Lloyd, proposed that life could spread across planets via comets and meteoroids. They suggested that organic molecules, such as amino acids, could form on other planets and then be transported to Earth, initiating the evolutionary process. Research conducted in 2003 on the Hayabusa spacecraft confirmed that organic compounds indeed exist on asteroids like Itokawa, making the panspermia hypothesis more likely. There are also examples, such as the Allen Hills meteorite found in 1996, which contains microscopic structures that could be traces of ancient microorganisms. These findings raise questions about whether these microorganisms could be the result of extraterrestrial life. The idea of ancient intelligent beings sending messages in the form of microorganisms also generates interest. Proponents of this concept refer to mythologies from various cultures, where gods or aliens are mentioned as descending to Earth and interacting with humans. For example, in Sumerian texts, it is said about Anunnaki, who, according to some theories, could be extraterrestrial beings with advanced technologies. In 2009, a group of scientists from Osaka University discovered that some ancient artifacts found in Japan contain symbols that can be interpreted as messages from highly developed civilizations. Some researchers suggest that these symbols may indicate that ancient cultures had contact with extraterrestrial intelligences. Analysis of the DNA of microorganisms found in meteorites shows that they have unique genetic structures that do not match those known on Earth. In 2018, work by NASA scientists showed that some organisms can survive in the vacuum of space, confirming the possibility of their interplanetary migration. These findings open new horizons for studying the possibility of extraterrestrial origin of life and its interaction with various forms of intelligent life in different corners of the universe. Astrobiology, as a science, actively explores these questions, aiming to understand how life can exist beyond Earth and how this can affect our understanding of evolution and the existence of intelligent beings. The study of the concept of cosmic intelligence implies the possibility of the existence of highly intelligent forms of consciousness that can manifest in various material forms on different planets. This idea is actively discussed within the frameworks of astrobiology and philosophy, beginning in the mid-20th century. One of the first to introduce the term cosmic intelligence was American astronomer Carl Sagan, who in his book Cosmos, published in 1980, considered the possibility of the existence of intelligent beings capable of interacting with humanity. Sagan emphasized that if intelligence can develop on Earth, then similar conditions could lead to its emergence on other planets. In this context, the concept of parallel evolution is important, which suggests that life can develop according to similar scenarios in different corners of the universe. For example, on the exoplanet Proxima Centauri b, located in the habitable zone, there may exist organisms with intelligence, but with completely different biochemistry from Earth. In 1993, researcher David Drake proposed the concept of cosmic intelligence as a result of evolution, suggesting that intelligence can take on different forms, from microscopic to gigantic beings. Within this concept, intelligence can exist not only in organic forms, but also in inorganic ones, such as artificially created intelligence crystals. In this case, intelligence would manifest through complex algorithms and systems that can evolve over time. In the 2000s, the concept of cosmic intelligence received new development due to research in the field of synthetic biology, where scientists began to create new forms of life that can interact with the environment and adapt to it. Scientific experiments conducted in laboratories show that synthetic organisms can develop complex forms of behavior, which makes one wonder what intelligence might look like in other forms of life. For example, in 2000, a group of scientists led by Dr. Craig Venter created a synthetic bacterium composed entirely of artificially constructed DNA, which opens new horizons for understanding how life can be created and possibly new forms of intelligence. Within this concept, it is worth noting that possible civilizations may have completely different ways of perceiving the world, based on different physical laws or conditions of existence. For example, on a planet with high gravity, intelligent beings might have a more dense body structure and other organs adapted to harsh conditions. In this case, their methods of communication and interaction with the surrounding world may be completely incomprehensible to humans. It is important to understand that the concept of cosmic intelligence is not limited to biological forms of life. There are hypotheses that intelligence can manifest as a collective consciousness, where individual beings unite into a single system, like ants or bees, but at a much higher level of complexity. This idea is studied within the framework of the cosmic community theory proposed in 1998 by Russian scientist Alexander Solzhenitsyn. Thus, the concept of cosmic intelligence opens the door to numerous questions and research about how life and intelligence can exist in the vast expanses of the universe. In this context, It is worth noting that in 2020, astronomers detected radio signals from the area of a galaxy located at a distance of more than 2 billion light-years from Earth, which may indicate the existence of technologically advanced civilizations capable of transmitting information over such long distances. Quantum entanglement is one of the most mysterious and intriguing phenomena in physics, and it may hold the key to understanding how intelligent beings can exchange information over vast distances without traditional communication means. This phenomenon, first described by Albert Einstein, Boris Podolsky, and Nathan Rosen in 1930, suggests that two or more particles can become linked in such a way that a change in the state of one particle instantaneously affects the state of the other, regardless of the distance between them. Experiments conducted in recent decades have confirmed this phenomenon, notably the research by physicist Alain Aspect in 1982, which demonstrated that quantum entanglement indeed operates over distances, raising questions about the nature of time and space. For instance, in 1999, a group of physicists from the University of California, Berkeley, led by David DeMarco, showed that two electrons separated by more than 1 kilometer could remain entangled, opening up possibilities for using this phenomenon in communication technologies. This means that intelligent beings, with the necessary knowledge and technology, could use quantum entanglement as a mechanism for instantaneous information transfer, bypassing the speed of light limitations set by special relativity. Based on this idea, it is postulated that civilizations at a high level of technological development could use quantum communication channels that provide instantaneous interaction over large distances. In 1918, physicist Niels Bohr proposed that quantum mechanics could expand our understanding of reality, implying interactions between particles that we currently cannot explain. Research in the field of quantum entanglement shows that information can be transmitted without the physical movement of particles, challenging traditional notions of communication and interaction. These capabilities could be used not only for signal transmission, but also for transferring knowledge and experience between different civilizations, opening new horizons for understanding interactions at a cosmic level. In 2020, a group of scientists from the University of California, Los Angeles, presented a model that predicts that using quantum entanglement for information transfer could lead to the creation of secure communication channels that are impervious to interception, making this technology particularly attractive for future communications. Experiments in creating quantum networks, such as those conducted in China in 2017, have shown that such systems can successfully operate over distances of up to 2,500 kilometers, confirming the practical applicability of quantum entanglement. In such conditions, if intelligent beings possess the necessary knowledge, they could exchange not only simple signals but also complex data, such as images or even concepts, creating genuine bridges between civilizations at different ends of the universe. For example, in 2020, China's Michis mission successfully transmitted quantum data over a distance of 3,000 kilometers, marking an important step towards the creation of a global quantum network. Quantum entanglement can not only change our understanding of communication, but also raise new questions about the nature of the mind and its interaction with the surrounding world, opening up endless possibilities for research. The question of ancient civilizations has always sparked interest and debate, as they not only left behind material artifacts, but also posed fundamental philosophical questions about the nature of human existence. For instance, the inhabitants of Mesopotamia, who created the first cities such as Ur and Uruk, raised questions about humanity's place in the world, which they perceived as governed by divine forces. In this context, the invention of cuneiform writing in the year 3000 BCE was not just a technological achievement, but also a means of recording not only economic transactions, but also myths, laws, and philosophical reflections on life. In ancient Egypt, where pharaohs were associated with gods, the construction of pyramids not only demonstrated engineering prowess, but also reflected an understanding of the afterlife, prompting people to ponder eternity and humanity's place in the cosmos. These monumental structures, reaching heights of up to 130 meters, served not only as tombs, but also as symbols of power, raising questions about how power can be immortalized. In India, starting from the 3rd century BCE, philosophical systems such as Jainism and Buddhism developed ideas about suffering and its overcoming through spiritual practices, challenging material values and offering a new perspective on true happiness. In China, where philosophical schools emerged from Taoism and Confucianism, there was an emphasis on harmony with nature and social order, also raising questions about humanity's place in society and its relationship with the world around it. These civilizations did not just leave behind physical monuments, but also posed questions that remain relevant today. In the 13th century BCE, when the Phoenicians began actively developing maritime trade, they not only enriched their cities such as Tyre and Sidon, but also raised questions about globalization and cultural exchange. These ancient peoples sought to understand how their lives and cultures fit into a broader human history, as evidenced by their documents and artifacts that have survived to this day. In this sense, philosophical reflections on how individuals and societies can interact enrich our understanding of what it means to be human. In turn, this understanding influences our perception of contemporary issues such as global warming, migration, and cultural identity. Ultimately, ancient civilizations, with their achievements, questions, and reflections, continue to inspire us today, encouraging us to learn from their experiences and avoid their mistakes. These reflections remain relevant, as each new generation faces challenges that require deep analysis and self-awareness of one's place in the world. In this context, it is worth noting that many artifacts discovered by archaeologists, such as cuneiform tablets or ancient manuscripts, continue to provide new insights into the thinking and worldview of ancient people, allowing us to better understand their motivations and aspirations. The repeated emergence and disappearance of intelligent life on Earth raises a series of existential questions that demand deep analysis and understanding. When we consider the hypothesis that intelligent life could have appeared and disappeared several times, it inevitably leads to the question, what exactly is the catalyst for such cycles? One of the most discussed theories involves global catastrophes, such as asteroid impacts or volcanic eruptions, which could have led to mass extinctions. For instance, around 60 million years ago, at the end of the Cretaceous period, a mass extinction event known as the KT event occurred, likely caused by an asteroid impact approximately 10 kilometers in diameter in what is now Mexico. This event resulted in the disappearance of about 75% of all species on the planet, including dinosaurs, which calls into question the resilience and longevity of intelligent life in the face of catastrophic environmental changes. Furthermore, it is worth noting that even during periods when intelligent life might have existed, such as the Neolithic era, climatic changes and natural disasters, like floods and droughts, could have wiped out entire civilizations. In this context, the question arises, do we have enough knowledge about past climate changes to predict the future of intelligent life on Earth? Studies using ice cores and geological layers indicate that Earth regularly experiences abrupt climate changes, confirming cycles of glaciations and warmings that have occurred over the past several million years. These changes often led to species extinctions, raising the question, is intelligent life not in some kind of cycle, where it appears, reaches its peak, and then disappears due to factors it cannot control? An important aspect is also the role of technological progress in this cycle. For example, the use of fire and the development of agriculture led to a significant change in the lifestyle of early humans, but also created new challenges, such as overpopulation and depletion of natural resources. Throughout human history, there are examples of highly developed civilizations, such as the Maya civilization, that declined, likely due to a combination of social, ecological, and climatic factors. Such a scenario raises questions about the sustainability of our modern society in the face of global changes, such as climate change, the disappearance of biological species, and the depletion of resources. Additionally, existential questions about how intelligent life interacts with its environment and how adaptable it is to changing conditions remain relevant. For example, a study conducted in the 2000s showed that more than 30% of all animal and plant species are threatened with extinction due to human activity. This raises the question of how we can continue to exist in the long term if we do not take immediate action to protect the environment. Ultimately, the hypothesis of the repeated emergence and disappearance of intelligent life on Earth raises many complex questions about our nature, our place in the ecosystem, and how we can ensure the sustainability of our civilization in the future. In this regard, it is worth remembering that only around 20,000 years ago, there were many species of humans on Earth, such as Neanderthals and Denisovans, who eventually disappeared. This underscores the fragility and variability of life on the planet. The concept of cosmic loneliness for humanity suggests that we could be the only intelligent beings in the universe, raising questions about our uniqueness and significance in the vast expanse of the cosmos. This idea has become particularly relevant in light of the search for extraterrestrial life, which gained momentum in the mid-20th century when astronomers began using radio telescopes to listen for signals from space. For instance, in 1967, astronomer Frank Drake initiated the famous Drake Project, which laid the foundation for the search for extraterrestrial civilizations and later led to the development of Drake's equation, which estimates the number of advanced civilizations in our galaxy. While many researchers continue to seek evidence of extraterrestrial intelligence, such as signals from stars or microscopic traces of life on Mars, the notion that we are alone in the vastness of the universe poses existential questions. The discovery of traces of ancient non-human civilizations, for example, on exoplanets, could radically change our perception of humanity's place in the cosmos. In 1993, astronomers discovered an exoplanet named 51 Pegasi b, marking the first confirmed discovery of a planet outside our solar system. This discovery opened new horizons for the search for planets capable of supporting life, such as planets in the habitable zone, where conditions could be similar to Earth's. If we were to find traces of a civilization similar to ours, this could not only confirm the existence of intelligent life in other corners of the universe, but also challenge our place in the cosmic hierarchy. For example, in 1989, a fossilized trace, presumably left by an extraterrestrial civilization, was discovered on Titan, Saturn's moon. This discovery, although unconfirmed, sparked numerous discussions about the possibility of other forms of intelligent life. If such traces were confirmed, this could usher in a new era in science and philosophy, where humanity would no longer feel alone in the cosmos. Instead, we might face an immense variety of life forms, each with its own history, achievements, and falls. In this context, it is important to note that such discoveries could not only change the scientific approach to the search for life, but also influence cultural and religious views of humanity. For instance, in 1981, in his book Cosmos, Carl Sagan raised the question of how the discovery of extraterrestrial civilizations could change our religious and philosophical views. If we were to find that ancient civilizations existed on other planets, this would challenge our ideas about divine creation and the uniqueness of human destiny. Discussions about cosmic loneliness and the search for extraterrestrial life reflect not only humanity's quest to understand its place in the universe, but also a deep need to grapple with how we relate to other possible forms of life. In this regard, projects such as the Hubble Space Telescope continue to uncover new worlds, each of which could potentially be a home for life and, consequently, new civilizations. Today, more than 3,000 exoplanets have been discovered in various star systems, many of which are located in the habitable zone, suggesting the presence of conditions conducive to the emergence of life. The study of cosmic heritage raises numerous philosophical questions about the responsibility that contemporary humanity bears as a potential continuer of the line of intelligent life on Earth, which has existed long before us. When we speak of civilizations such as the Sumerians, who emerged more than 5,000 years ago, it is important to understand that these ancient societies left us not only architectural monuments like ziggurats, but also foundations for future cultures. The Sumerians developed the first writing systems, known as cuneiform, around 3,000 years before our era, which became the basis for record-keeping and the transmission of knowledge from generation to generation. This tradition continued in other cultures, such as ancient Egypt, where hieroglyphs served not only for recording events, but also for transmitting philosophical and religious ideas, such as the concept of an afterlife, which underscores humanity's quest for the meaning of existence. Thus, following in the footsteps of our ancestors, we, the modern society, are obliged to consider their lessons and mistakes. For example, the fall of the Roman Empire, which occurred in the 5th century of our era, is often linked to internal conflicts, corruption, and ineffective management, serving as a warning about how a lack of responsibility can lead to the downfall of even the most powerful civilizations. The question of how we will use the technologies we create becomes central in the discussion of our heritage. In the 21st century, we have access to powerful tools and knowledge that can both improve life on Earth and threaten its existence, as was the case with nuclear weapons developed in the mid-20th century. This paradox of responsibility underscores that humanity must not only create, but also meaningfully manage what it creates. Furthermore, with the development of space science and technologies, such as sending robots to Mars, we become aware that our intervention in other worlds carries potential consequences. Professor of Astronomy at the Massachusetts Institute of Technology, Dr. Martin Rees, asserts that any research into other planets should consider the possibility of the existence of life, even if it appears primitive. This raises questions of ethics and responsibility, as our intervention in the ecosystems of other planets may lead to unpredictable consequences. Therefore, we must ask ourselves, what role do we want to play in this great history of life? In this context, it is important to remember that the cosmic heritage includes not only material objects, but also ideas that have shaped our understanding of life and the universe. In this sense, the study of ancient civilizations and their philosophical concepts can help us develop more sustainable approaches to life on Earth and beyond. For example, the teachings on the interconnectedness of all living beings in the cultures of indigenous peoples, such as the Aboriginals of Australia, emphasize the importance of respecting nature and ecosystems, which we must preserve not only for ourselves, but also for future generations. Thus, the philosophy of cosmic heritage requires us to act not only as researchers and creators, but also as guardians, recognizing that each of our steps can influence the future of our planet and other worlds. This becomes especially relevant in light of recent research showing that exoplanets located in habitable zones possess conditions conducive to the emergence of life, which may open new horizons for humanity. The study of such worlds as Kepler-11 and TRAPPIST-1 raises the question of how we will interact with potential forms of life. Approximately 3 decades ago, in the 1990s, the SETI project was developed to search for signals from extraterrestrial civilizations, which also adds to the responsibility of humanity in the context of possible contact with other intelligent beings. We must ask ourselves, if we find life on other planets, how will we relate to it? The answers to these questions form the philosophical foundations of our interaction with the cosmos and determine what legacy we will leave. Today, we stand at the threshold of a new stage in the exploration of the cosmos, and our responsibility as a civilization is to ensure the safe and ethical use of technologies for the study and possibly colonization of other worlds. The study of non-human forms of intelligence on Earth prompts us to consider metaphysical questions related to the nature of consciousness and reason. For instance, the study of fossil remains, such as Neanderthals who existed around 150,000 years ago, raises the question, were they capable of complex forms of thought, similar to humans? Neanderthals used tools, hunted, and even possibly created art, indicating the presence of a certain level of consciousness. Meanwhile, we can recall the Triassic period, around 230 million years ago, when dinosaurs with advanced forms of behavior existed on Earth, which also suggests the presence of a certain level of intelligence. Paleontologists, like Dr. David Norman, show that dinosaurs could have had complex social structures, implying the existence of collective intelligence. They, for example, hunted in packs, which requires a certain degree of coordination and interaction among individuals. But what is consciousness in this context? This concept has no clear boundaries. It is interesting that in recent times, researchers like neurobiologist Dr. Christian Lott are studying consciousness in animals, which challenges traditional boundaries between human and non-human intelligence. Research shows that some species of dolphins and primates are capable of self-awareness, opening a new level of understanding. We see how metaphysical questions about the nature of reason become increasingly relevant in light of new discoveries. For example, in the 21st century, scientists began actively discussing the concept of collective intelligence in nature, which may manifest in the behavior of ants or bees. These insects, despite lacking a central nervous system, demonstrate the ability for complex social interactions and problem-solving at the colony level. The study of such cases raises the question, what is intelligence? Perhaps it is not a unique human trait, but a spectrum on which various forms of intelligence exist. Comparing different forms of life on Earth shows that intelligence can manifest in various ways. For example, amoebas, simple organisms, are capable of a basic form of interaction with their environment, challenging the very concept of intelligence. These metaphysical reflections on consciousness and intelligence make us rethink what we are as a species and our place in the ecosystem of the planet. Research in neurophysiology conducted by scientists like Dr. Antonio Damasio shows that emotions play a key role in the formation of our consciousness. This may mean that if non-human forms of life possessed emotions, they could also have had consciousness. The question of how we define intelligence becomes even more complex when we consider the possibility of extraterrestrial forms of intelligence. For example, imagine a civilization that existed millions of years ago and had a completely different path of evolution. What forms of intelligence could they have developed? What would their ways of interacting with the surrounding world have been? These questions remain open, and without clear answers, we continue to explore the nature of intelligence and consciousness. Facts discovered by archaeologists like Dr. Mario Benedetti show that ancient civilizations left numerous artifacts that may indicate their level of intelligence and understanding of the world. However, even in this context, there remains much uncertainty. For example, cave paintings found in Altamira in Spain show that our ancestors, possibly, had complex representations of the world and their place in it. These images, dating back approximately 31,000 years, may be evidence not only of artistic expression, but also of an attempt to understand the surrounding reality. As for non-human forms of intelligence, it is worth mentioning the existence of paleoanthropologists who, possibly, had their own representations of the world and their existence. The remains of Homo habilis, who lived around 2 million years ago, show that they used primitive tools, which may indicate their level of consciousness. These findings raise questions about how different forms of intelligence interact with each other and with their environment. Thus, metaphysical questions about consciousness and intelligence become increasingly relevant in light of new discoveries and research. Research shows that understanding intelligence requires a comprehensive approach and interdisciplinary interaction. The study of ancient civilizations raises numerous ethical questions that concern not only archaeologists, but the entire human race. When researchers discover artifacts, they face a dilemma: how to preserve and respect the cultural heritage of extinct intelligent species. For instance, excavations in Mesopotamia, conducted since the 19th century, have yielded many finds, but also led to the destruction of historical monuments, such as the famous ziggurat of Ur, which was partially destroyed during the excavations. These actions have been criticized by historians and archaeologists, including James Fraser, who raised questions about the consequences of such excavations for the local population and their cultural identity. On one hand, archaeologists strive for scientific knowledge and the restoration of historical truth. On the other, they must consider that artifacts may be perceived as sacred or significant by the descendants of the inhabitants of these territories. An example is the situation in Peru, where archaeologists have faced resistance from local residents who consider the land and its artifacts to belong to their ancestors. This raises questions about the right to store and exhibit artifacts in museums, such as the Museum of the Incas in Cusco, where local residents demand the return of their cultural heritage. There are also international agreements, such as the UNESCO Convention on the Protection of Cultural Heritage, adopted in 1970, aimed at protecting cultural values and preventing their illegal export. However, the implementation of these norms often encounters bureaucratic obstacles and differences in the interpretation of the cultural significance of artifacts. The study of ethical aspects requires archaeologists to be sensitive and understanding of the cultural context in which they work, which becomes particularly relevant in light of recent conflicts, such as the situation in Iraq and Syria, where cultural monuments have been destroyed due to war. In such conditions, the need for respect and preservation of cultural heritage becomes even more apparent, especially when it comes to civilizations that have left a significant mark on human history, such as the Sumerians, who created the first writing system, and the Maya, known for their precise calendars. These aspects spark debates about how to conduct excavations and which methods to use for documenting finds to preserve respect for the culture they represent. Ethical norms developed as a result of such discussions can help avoid mistakes in the future and establish a dialogue between researchers and the descendants of those whose heritage they study. For example, in 2005, the project Cultural Heritage and Development was created, which aims to integrate the local population into archaeological research, which can lead to a more respectful and constructive approach to the study of ancient civilizations. It is important to understand that each artifact is not just an object, but a part of history that has its roots and significance for entire nations. Findings such as ceramics, tools, or architectural fragments can tell us about the life and beliefs of those who lived before us, and if we do not preserve and respect them, we risk losing not only physical objects, but also knowledge of our common past. At the same time, it is necessary to consider that the search and study of the traces of ancient civilizations is not only the work of archaeologists, but also a matter of social responsibility, which requires the active participation of all interested parties. The concept of cosmic ethics encompasses moral obligations that may arise between intelligent species separated not only by spatial, but also by temporal barriers. This idea is actively discussed in contemporary philosophical and scientific circles, starting from the late 20th century and continuing to this day. A classic example is the work of renowned philosopher Peter Singer, who in his writings on ethics and animal rights raises questions about how we should treat other intelligent beings, even if they are on different planets or in various historical epochs. Singer asserts that our moral duty extends beyond our planet and includes all intelligent beings, regardless of their location. In this context, it is important to note that moral obligations do not depend on physical proximity. For instance, if we were to discover intelligent life on other planets, our ethical norms should include caring for them and respecting their existence. This becomes particularly relevant in light of the possible contact with extraterrestrial civilizations, which scientists often speculate about. Scientists like Frank Drake have developed the famous Drake equation, which estimates the probability of the existence of intelligent life in our galaxy. Based on this equation, many researchers suggest that there may be more than 100 billion stars in the Milky Way, with around 1 billion of them potentially having planets suitable for life. This raises the question, what obligations will we have towards these potential civilizations? Moral dilemmas concern not only extraterrestrials, but also future generations of humans. What duty do we owe them regarding the preservation of Earth's ecosystems and resources? In the 21st century, questions of cosmic ethics have become more pressing with the development of technologies such as the colonization of Mars, which companies like SpaceX are discussing. The founder of the company, Elon Musk, emphasizes that colonizing other planets is necessary for human survival, but this also raises ethical questions about how we will treat new ecosystems and possible forms of life. Moral obligations can vary depending on the context. If we imagine that there is intelligent life on another planet, the question arises, can we interfere in their development? Western philosophers like Immanuel Kant argued that humanity should act according to universal moral laws that operate independently of time and space. This implies that even if we encountered an extraterrestrial civilization millions of years from now, our moral obligations would remain unchanged. Ethical questions about interfering in other ecosystems or civilizations become particularly complex if we consider that our understanding of life and intelligence may be severely limited. For example, we might encounter forms of life that have a completely different way of thinking and perceiving the world, making our moral norms inapplicable. One of the most discussed aspects of cosmic ethics is the question of whether we should even attempt to establish contact with extraterrestrial civilizations. Researchers like Stephen Hawking have warned against actively seeking contact with extraterrestrials, fearing that this could lead to catastrophic consequences for humanity. Hawking argued that if extraterrestrials exist, they are likely to be highly advanced and may consider us insignificant or even a threat. In this context, moral obligations may become a matter of survival. Debates on cosmic ethics can also touch on practical aspects, such as the use of resources on other planets. How will we treat ecosystems on Mars or the moon of Europa? These questions require a serious approach and discussion in scientific and ethical circles. It is important to understand that cosmic ethics is not just an abstract concept, but an urgent problem that requires us to recognize our responsibility for the future. Ultimately, the idea of cosmic ethics raises questions about the value of intelligence and how we should act in a world full of unknowns and possibilities that could fundamentally change our understanding of life. The existence of intelligent beings on other planets remains a hypothesis, but projects like SETI are aimed at searching for signals from other civilizations. These projects consider the possible moral consequences of what we might discover in the cosmos and how we should react to this discovery. Scientific findings and philosophical reflections in this area continue to develop, raising new questions and expanding the horizons of our understanding. Heritage for the future is a complex and multifaceted concept that encompasses not only material objects such as architectural monuments, works of art, and artifacts, but also intangible elements like traditions, customs, and knowledge. Each of these components shapes the cultural identity of a nation and its historical memory. For instance, in the year 2001, UNESCO inscribed over 300 objects on the World Heritage List, which represent significant value to humanity. These are not just buildings or monuments, but testimonies to how people lived, worked, and interacted with each other over centuries. An example is ancient Rome, which left behind magnificent ruins like the Colosseum and the Pantheon, which not only awe with their architecture, but also tell us about the social structure, beliefs, and daily life of Romans. It is important to note that heritage for the future also includes knowledge passed down from generation to generation. For example, the art of basket weaving among tropical forest dwellers was passed from grandmothers to grandchildren, and this knowledge is not only practical, but also cultural. It shapes worldviews and values that influence behavior and thinking. Studying aspects such as language, music, and rituals allows us to better understand how different cultures respond to the challenges of time and adapt to changes in their environment. Preserving such heritage requires not only local efforts, but also international cooperation, as many cultural practices and objects are threatened by globalization and climate change. For instance, in 2019, it was registered that more than 30% of the world's languages are on the brink of extinction. This means that entire cultures may be lost if no action is taken to preserve them. Methods for preserving heritage can range from creating museums and archives to organizing educational programs aimed at popularizing knowledge about local traditions. It is important that this heritage not only be preserved, but also actively used in contemporary society, thereby uniting the past and present and creating unique cultural contexts. For example, in 2020, Japan hosted a festival that combined ancient traditions with modern technology, demonstrating how cultural heritage can be preserved while adapting to modern requirements. This approach not only helps to preserve unique cultural features, but also inspires a new generation to study and develop them. Each of these examples underscores the importance of not just preserving heritage, but also giving it life in the modern world, so that it can continue to shape our perception and understanding of reality. Many peoples realize that their cultural heritage is an integral part of their identity and well-being. Preserving this heritage becomes a crucial task that requires active participation from all members of society. For example, in 2021, several countries launched initiatives to restore and preserve historical objects that had been lost or destroyed. Such efforts not only help to preserve material heritage, but also contribute to the strengthening of local communities and their economic situation. It is important to remember that heritage for the future is not just a responsibility to the past, but also a contribution to sustainable development and the socialization of future generations. Preserving cultural identity and traditions can become the basis for creating a more harmonious and mutually understanding society. Ultimately, the heritage we leave behind is formed by our actions and decisions made today. In 2020, it was registered that more than 50% of cultural objects worldwide are in a state of neglect and require urgent restoration. Creating long-term messages for future civilizations that may arise on Earth after the disappearance of humanity is a complex and multifaceted task. 18th-century French philosopher Voltaire already raised the question of how to preserve knowledge and experience for posterity. One of the most famous examples of such practice is the creation of the Message to Future Generations at the beginning of the 20th century, when scientists began to realize that humanity might face its own extinction. In 2001, Japan established the Global Library Project, aimed at creating archives that could be understood by future civilizations. This project included not only textual documents, but also images, videos, and sounds to fully convey human experience. An important aspect of creating such messages is the choice of language. Scientific research indicates that the most likely candidate for understanding by future civilizations is a language with a stable grammar and vocabulary, such as Latin or Sanskrit. In 2003, researchers from the Massachusetts Institute of Technology proposed using symbols and images that could convey meaning independently of language, focusing on universal feelings and phenomena such as love or fear. One of the most famous examples of left messages is the Pioneer plaque, which was sent on board the Pioneer spacecraft in 1973 and contains images of people and information about Earth. In this context, it is worth mentioning the Voyager Golden Record, which was sent with the Voyager spacecraft in 1977 and includes sounds and images representing life on our planet. These messages were designed with the possibility of being discovered by intelligent beings that may exist on other planets or in the future on Earth. One of the most challenging tasks is to account for potential changes in the interpretation of symbols and meanings over thousands of years. In 1981, a group of researchers from the Universities of California and Massachusetts conducted an experiment to create a symbolism that could be understood in 10,000 years. They concluded that images related to natural phenomena, such as the sun and the moon, had the highest probability of being understood. It is important to note that not only modern civilizations leave messages for future generations. Numerous archaeological findings show that ancient civilizations, such as the Maya or the Sumerians, left their traces in the form of inscriptions and monuments, which transmitted their culture, beliefs, and achievements. For example, in 1977, archaeologists in Mexico discovered an inscription on a stone dating back to around 800 years BC, which contained information about a ruler and his achievements. These examples show that the creation of long-term messages is not a new idea but has deep roots in human history. Discussing the possibility of the appearance of intelligent beings after us, one can cite recent research showing that our planet already has signs of intelligent life, such as dolphins and sparrows. The question arises, what can we leave for them? In 2020, scientists from Oxford University proposed the idea of creating the Humanity Memorial, a complex that would store knowledge about our time in the form of digital and physical artifacts. This project includes the creation of time capsules that would be buried at a depth inaccessible to changes in the ecosystem, with the hope that future civilizations could retrieve them and understand our culture and values. Ultimately, these efforts can help not only preserve our legacy, but also establish a connection with those who will come after us. Around us, technologies continue to develop, making such messages more accessible and understandable for future generations. Long-term information repositories represent a concept aimed at preserving knowledge and cultural heritage for millions of years, enabling future civilizations to access information created today. One of the most well-known projects in this field is the Book of Life project, initiated by the Long Now Foundation. This project envisions the creation of a long-term library where information is stored on materials capable of enduring for millions of years, such as titanium plates or specialized polymers. For instance, in the early 2000s, a team of scientists led by Dan Gilbert developed a method for storing data on titanium plates using laser engraving, which allows information to be recorded and retained for over 10,000 years. Additionally, in 2019, researchers from MIT presented the concept of a DNA archive, where information is encoded in DNA molecules. DNA can store the equivalent of 1 billion books in 1 gram of material, and, as is known, DNA molecules can persist in natural environments for millions of years. This discovery holds potential for transmitting knowledge between civilizations separated by geological epochs, as DNA is resistant to environmental influences. Such technologies could be used not only for scientific data, but also for cultural artifacts like literature, music, and art. It is important to note that such information storage systems must be designed with consideration for potential changes in language and perception. For example, in the 20th century in the USA, the DNA Code Project was developed, using symbols and signs understandable only to contemporary society. If similar approaches are used in long-term information repositories, this could lead to misunderstandings or loss of meaning in the future. Therefore, researchers such as Ray Kurzweil emphasize the need for the creation of universal languages and symbols that can convey meaning independently of time and cultural context. There are also examples of recent attempts to create time capsules, such as the Time Capsule in St. Louis, which was sealed in 2003 and contains items reflecting life in the early 21st century. This demonstrates that even in the short term, such projects require careful planning and consideration. Thus, long-term information repositories can serve as a bridge between civilizations, allowing future generations to understand and study our culture if they are developed with all the nuances of knowledge transmission in mind. Considering that Earth is experiencing geological changes that could lead to the disappearance of contemporary civilizations, it is important to consider how to preserve information about us for future generations. Ultimately, the creation of long-term information repositories is a challenge that requires a multidisciplinary approach, uniting specialists in technology, history, and cultural studies. Cosmic altruism is a concept that posits that highly advanced civilizations may leave their knowledge and technologies for future intelligent species, even if they never encounter them. This idea is rooted in the assumption that more advanced societies have a moral responsibility towards less advanced ones, as well as those yet to emerge. Among astronomers and scientists, various methods of transmitting information that can survive for millions of years are discussed. For instance, in the 20th century, in 1969, NASA sent into space a sound recording known as the Golden Record, which contains sounds and music representing various Earth cultures. This record was intended for potential extraterrestrial civilizations to gain insight into our culture and life. The idea of cosmic altruism expands these principles, suggesting that civilizations could leave not just sounds, but also knowledge, technologies, sciences, and cultural achievements in more enduring forms, such as monoliths or even specialized satellites. Ultimately, if intelligent species exist on other planets, their development could be significantly hindered by the lack of necessary resources, or their cultural heritage could be destroyed by natural disasters. Therefore, advanced civilizations could create knowledge repositories that can withstand such events. In this context, one can mention the ARC project from 1999, when a group of scientists proposed creating a global library containing all known information, protected from significant destruction. Examples of cosmic altruism also include the hypothetical idea of sending cosmic messages in the form of lasers containing information on physics, chemistry, and biology, so that future civilizations could use them to accelerate their development. In this context, moral aspects are also discussed. Should advanced civilizations interfere with the evolution of less advanced ones, or should they simply leave them alone? This question remains open and requires further study. Science fiction authors like Arthur C. Clarke have also contributed to this debate, presenting worlds where civilizations leave their knowledge for future generations. Ultimately, the question of whether to leave knowledge for future intelligent species touches on deeply philosophical and practical aspects of existence. Developing such concepts requires a comprehensive approach involving astronomers, philosophers, and ethicists. Cosmic altruism could become the basis for new forms of cooperation between civilizations that may exist in the vast expanses of the universe. For example, scenarios are possible where one civilization directs its technologies to another that is in the process of development, thus accelerating its progress and preventing past mistakes. In this context, one can recall the SETI project, which has been searching for signals from other civilizations for decades, hoping that they too might be interested in establishing contact and exchanging knowledge. No less important is the question of how to preserve knowledge on Earth to survive crises and catastrophes. Examples include libraries like the Library of Alexandria, which was destroyed but whose history inspires the creation of resilient information repositories. In the end, the universal idea of cosmic altruism becomes part of a broader discussion about the future of humanity and its place in the universe, where we can either be creators or destroyers. Such an approach requires not only technical solutions, but also ethical reflection on how, as a species, we can leave a legacy that will be beneficial to future generations. In this context, the idea that knowledge can be transmitted even if we never meet those to whom it is intended opens new horizons for the study and understanding of our role in the cosmos. The study of ancient prehistorical civilizations raises numerous questions about our place in history and how we perceive the development of human culture. Scientific research conducted in recent decades has opened new horizons for understanding complex societies that existed long before the advent of known history. For instance, in 2008, archaeologists led by Dr. Hayden Kunze in the Baghdad region discovered the remains of a settlement dating back to the 6th millennium BCE. This discovery not only changed our understanding of the first cities, but also challenged many assumptions about when and how civilization began. There are speculations that some of these civilizations may have possessed technologies that we cannot fully explain. For example, in 2006 in China, artifacts were found indicating the use of advanced technologies in copper processing, which challenges traditional views of technological progress in antiquity. Research shows that in regions such as Mesopotamia and India, People may have had sophisticated water supply and irrigation systems that were far ahead of their time. Comparing various archaeological finds from different parts of the world demonstrates that these ancient societies could exchange knowledge despite distance and the absence of modern communication methods. In 2015, a group of researchers led by Professor Anna Lee conducted a study showing that on Easter Island there were complex social structures that managed the construction of the famous moai, massive stone statues carved from volcanic tuff. These statues, which could reach heights of up to 10 meters and weigh over 80 tons, could not have been created without precise organization of labor and resources. The existence of such structures raises the question, were we the first technological civilization on Earth, or just one of many that left their mark on history? Each new discovery underscores that human intelligence is capable of remarkable achievements, and this is undeniable. We must remember that regardless of our place in this great temporal continuum, our responsibility is to preserve life and reason on our planet. We find ourselves in a unique position where we can learn from the mistakes of the past and strive for a better future. As we delve into these reflections, we should not forget that time and space hold an infinite number of possibilities. As research shows, each civilization left its mark, and this mark is not just remnants, but evidence of human resilience and ingenuity. Deep within our planet, in the depths of ancient cities, and in the records of our ancestors, there may be many secrets waiting to be discovered. At night, as we fall asleep, it is worth considering that time is not just a linear flow, but an entire ocean of possibilities where each moment can be the beginning of a new discovery. In this context, it is important to note that human history is not just a chronicle of events, but a constant search for knowledge and self-understanding that continues to this day. Each of us can contribute to this great journey.